So welcome to this workshop on memory-centric computer systems. This is going to be a full-day workshop, and we have a lot in the agenda. Before we start, there's some quick logistics. So who am I? So I'm Geraldo. I'm a PhD in the Safari Research Group. I'm conducting research on memory-centric computer systems for a while right now, about to graduate. So a lot of the work that you're going to see here is from my PhD thesis, but also you're going to cover the broad aspect of memory-centric computer systems in the literature as well. So in the website for this tutorial or the workshop, you can scan this QR code and download the slides that we are going to cover over here, just in case you want to follow up. In case there is any problem with the QR code, the website tutorial is linked to ASPLOS website, or it's just ASPLOS 25/MCCSys. And over there, all the slides that we are going to talk here today are over there, and then you can follow up as needed. So this is just an overview of the organizers. So I'm one of the main organizers, and together we have Dr. Mohammad, that's going to give a talk later on, Ataberk Olgun, which is a PhD student in the Safari Research Group, and Professor Onur Mutlu. So the agenda for today is quite extensive. This is our first instance of this workshop, and we decided to do it as a mixed tutorial and workshop. So during the morning, we are going to have a series of lectures related to processing in memory. Start with Professor Onur Mutlu lecture. And then we are going to have 2 breaks. And then in the afternoon, we are going to have the workshop aspects of this combined workshop and tutorial. Then we are going to have several invited talks from other people from academia and industry as well. All of this is available in your website. So in case you still are so excited about memory-centric computer systems that you want to have a second tutorial or workshop on it, we are going to have another instance of this workshop presented in ICS 2025 in Salt Lake in June, and then a follow-up in ISCA 2025 in Japan, in Tokyo. So I'm going to be doing a lot of traveling, and hopefully I don't get too jet lagged. So without further ado, we are going to get to the first talk from Professor Onur Mutlu. And then we are going to continue as we go. Let me just stop share here. Okay, cool. The mic.
Oh, I need the mic. Okay. Hey, welcome everyone to the first workshop. We've had these tutorials on memory-centric computing for a couple of years now, and we decided to switch the workshop style to invite more talks from the community. So hopefully this will be interesting in the first instance. It's a bit early in the morning at the beginning of the conference, so maybe it's not the ideal time, but let me share my slides, Geraldo, and see how this works. Does it look good? Do I need to turn on my camera or no?
No, it's okay.
Okay, cool. Okay. Can people in the back see the screen? A bit far away, but yeah, there are empty seats over here too. If people are coming in, feel free to sit. There's a lot in the front. Okay, as I mentioned, this is our first workshop, and it's going to be a full-day workshop. In the morning, we'll have tutorial material, and in the afternoon, we'll have invited speakers. So I'm looking forward to it. Hopefully, you guys are looking forward to it also. And I'm going to start with an overview talk, and I don't know how much time Geraldo gave me, but I'm probably going to exceed it. Is that okay? Okay, we have enough time in this, enough slack in the time. Okay, and everybody online can hear me? Rakesh, is all good? Okay. Okay, and I'm going to focus especially on processing in DRAM in this talk. a lot of the concepts that I'm going to cover are going to be covered later in more detail by Geraldo, and also some of the invited talks on different topics. So this will be an overview, but feel free to ask questions. So today, computing is bottlenecked by data, and data is really key for many workloads. Important workloads are all data intensive. I'm trying to find a good place to stand over here so that I can point to things. Okay, I don't want to move your computer. It's okay. Yeah, yeah. Basically, we require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. We're actually exploding in terms of data generation capability in many systems today. And we also want more sophisticated analyses on data that we generate. So it's not only that data is exploding, we want more sophistication, the capabilities of what we would like to do with the data. So compute requirements on the data are also increasing at the same time. And this is something that's already felt quite strongly in machine learning today. Clearly, we have huge data sets today, and we're training on them. We're doing inferencing on them. And those have increased significantly, as you can see these numbers. These numbers may be continuing this way, may not be. But still, these are huge numbers today. And compute requirements on those are also increasing. And as a result, we'll need to bring together a lot of compute and a lot of data at the same time. And that's one of the reasons why doing computation near memory or in memory makes a lot of sense. But it's not just machine learning. There are a lot of other applications where this is felt. Basically, today we have very good data generators, and this device over here is a data generator that sequences genomes. And it's very efficient at doing so. So if you give these devices to lots of people in the world, you'll be exploding in terms of data generation. These are nanopore sequencing devices. So we do a lot of work on genomics. I will briefly touch upon a couple of them. But this is an area that's actually also quite exciting, where memory-centric computing can have a lot of benefits. Okay, I can go through a lot of applications, but essentially the takeaway is, and we will go through a lot of applications later on today, and also some of the invited talks will cover some applications like graph neural networks, large language model inference in the afternoon. There are going to be a lot of interesting, exciting talks. But basically, if you look at many applications, data access is the major performance energy bottleneck. And the way we design our computers today, essentially all computers, wastes a lot of energy because we're moving data all around. It also leads to a lot of performance loss. We try to do a lot to overcome that performance loss. We complicate our systems a lot. We basically add a lot of techniques like huge memory hierarchies. You will see that many times today. A lot of prefetching techniques, out-of-order execution techniques, multi-threading techniques, a lot of hardware complexity to tolerate the data movement from somewhere to the processor. And a lot of software techniques also. And we usually forget about them. That's why I put these in parentheses, right? All of these things that we added to tolerate data movement are kind of forgotten. It's sunk cost, but it's cost that we pay all the time. When these techniques don't work, it's actually pretty bad in terms of energy and performance. When these techniques do work, they somewhat work in our systems, in my opinion. And as a result, we're kind of working well to do better. But basically, there's a better way of designing systems. Today, we're moving data to the processor. Processor can be accelerator, FPGA, CPU, GPU, your favorite processor. Everything is compute-centric. It needs to move data from storage and memory and sensors into the processor. And this comes at great system cost. And in this workshop, we'll quantify that cost a little bit with some benchmarking. For example, Geraldo will talk about that. But also, we will propose techniques or discuss techniques to do better. So this is my cartoonish picture of an existing system. If you look at it, existing systems are pretty complicated, clearly. SoCs, for example, you have a lot of compute units. If you consider those red things over there as compute units, that's a very small fraction of our hardware cost today. Most of our system is really dedicated to storing and moving data. In fact, more than 95% of the area cost of a single node is dedicated to structures that store and move data, not compute. And if you actually give this picture to a 10-year-old child and ask the question, I'm actually spending almost all of my resources on storing and moving data. What should be my bottleneck? They would probably tell you memory should not be your bottleneck, but memory is bottleneck in our systems. I think this workshop is a little bit about also rethinking our systems like a maybe 10-year-old from the blank slate. Are we doing the right thing? If you're actually honest with yourself and ask the question to a 10-year-old who really doesn't have the baggage that we have, would you design the systems the way we design systems today? And I like thinking about it that way because that brings us to honesty, because we make a lot of decisions today based on business, based on business as usual, based on making money, etc. If that's the goal, maybe we're doing okay right now, right? But if the goal is something else, like if you want to fundamentally improve energy, performance, sustainability, then maybe you start from the blank slate and ask the question, are we doing the right thing with this sort of system? Okay, basically, even though we're spending a lot of resources on the structures that store and move data, system is still bottlenecked by memory. And I'm going to give you some performance numbers. Geraldo is going to give you more later on. And I'm sure later speakers will give you even more. Basically, this is a paper that was published by Google in 2015, where they evaluated all of their data centers on a state-of-the-art processor, basically top-notch Intel processor at the time. And they basically found that all of their data center workloads are limited by memory. Most of the time, the processor is waiting for memory. That backhand bound over here, most of that is accounted for with memory stalls, essentially. And the processor is doing what it's supposed to do only 10 to 20% of the time. And that's basically finishing instructions. Again, let's take the stance of a 10-year-old. I'm designing this processor, a CPU. Its goal is to finish instructions, right? That's the sole goal. Complete instructions as fast as possible. It's doing what it's supposed to do only 10 to 20% of the time. Is that a good design? Probably a 10-year-old will be very, very honest. Okay, that was performance, and we can talk a lot about performance, but let's talk about energy, because this is much worse. This is a slide that I borrowed from Bill Daly from High Peak 2015. All of these numbers are old. Even at that time, they were a little bit old, but the trends remain. Essentially, if you look at this, computation energy is very cheap today. This is a complicated arithmetic double precision floating point operation. Only 20 picojoules with some technology assumptions at the time. The DRAM read or write is 16 nanojoules. Basically, that's 800x difference. Energy of computation is not an issue today compared to the energy of data movement, essentially. So you can optimize this, of course, and essentially a memory access is about 2 orders of magnitude worse in terms of energy than a complicated arithmetic operation. It's good to ask the question then, do I really want to bring the data twice to do a operation that operates on 2 data values and write the data back once more to expend this memory energy 3 times? Of course, it's an optimization problem. You could actually formulate this as an optimization problem with your cache sizes, latencies, etc., and say, figure out how many times do I need to reuse a particular piece of data to overcome this energy cost, meaning amortize that energy cost. And that leads to thousands of times. In many workloads today, you don't have that much data reuse. Okay, I'll leave that here. But basically, this problem is getting worse. There are 2 reasons. One is operations are not always that complex. They're cheaper operations. And most of the time, you want to do cheaper and cheaper arithmetic operations. A cheaper add, for example, a 32-bit integer add is 6400x less costly in terms of energy, according to Bill Daly's numbers again. And today, we want to do even narrower bit width with adds, right? People are trying to do 4-bit machine learning, 2-bit machine learning, binary neural networks. And that's good. That's good effort, because we don't want to expend the energy on 32-bit, 64-bit, huge numbers, essentially, or 16-bit numbers. But that makes actually the disparity between computation and data movement costs even larger, because clearly reducing the bit width of operations reduces the computation energy. It also reduces data movement energy, but it reduces computation energy more than it reduces data movement energy. And there are conditions under which data movement energy can be reduced, which means that you need to pack the data nicely, which we will talk about in later works today. Okay, so we did a lot of studies to quantify this energy cost and also performance cost of moving data across the system. This is a study that we did with Google a number of years ago, ASPLOS 2018, so 7 years to be specific. We published it. You can read it. It's actually a nice analysis of mobile workloads and also where energy goes in mobile workloads that are used at the time by many users, like Chrome browser, YouTube, video encoding and decoding, TensorFlow inference, for example. And we found out that on average use cases, more than 60% of the data energy, total system energy, is spent on data movement. And we're going to talk about this paper a little bit more, I think, when Geraldo gets to it. More recently, we repeated the study on edge machine learning accelerators, Google Edge TPU, again, together with Google, using their proprietary edge models, machine learning models. And we found that this accelerator, most of the time, spends its energy on memory, especially in large machine learning models. This is DRAM and interconnect. You're basically moving data all around. I'm going to get back to this paper if we have time and if Geraldo doesn't stop me. If I'm taking too long, please stop me. Okay, but basically, this is one figure from that paper. This was published in 2021 after a few rejections. It was in PACT. But basically, you see that on proprietary machine learning models used at Google at the edge, LSTMs and transducers, these were the largest machine learning models that were put onto the edge device at the time. We find out that most of the energy is spent on off-chip interconnect and DRAM with a good machine learning accelerator at the time. And if you actually do near memory processing, if you actually design a system that's kind of heterogeneous that can do near memory processing as well as processor-centric processing, you can reduce that energy by about 5x or so. Okay, so basically the problem we have today is processing of data is performed far away from the data. If we can fix that, perhaps we can do much better. What does it mean to fix that? Essentially, we need a paradigm shift, because everything we do today is processor-centric. Every decision we make in our systems is really dictated by the fact that you have to move the data to a processor, centralized processing unit. It could be, again, CPU, GPU, accelerator, FPGA. They're all processor-centric. They have to move the data to some compute units. We want to enable computation with minimal data movement with the paradigm shift. And I call computing where it makes sense, essentially where data resides, as opposed to limiting ourselves to only a very small fraction of the hardware we designed to do computation. Essentially everywhere in the system. In the end, in the general sense, this is not just about memory. It's really about where data resides. And data resides, or data is generated in many, many places, right? In sensors, in storage, etc. Okay, basically, we want to make computing architectures more data-centric. And this is one example of a SoC-based system today, which may be similar to what you may have in your pocket. But you can see that today we're limiting computation to a very small fraction of this SRAM-dominated chiplet. But there are many other places like DRAM that are dark. Dark means that it cannot touch the data. Touch the data means it do computation. They're essentially serving the processor to send the data to it or receive data from it. Okay, so in the rest of this talk, I'm going to treat memory as an accelerator. But this is also a conscious choice, because accelerator means there is actually something that distributes work to that accelerator. Today, we know that paradigm very well. We can actually distribute work from CPU cores to other CPU cores, GPU cores, video processing engines, audio processing engines, ML processing engines, etc. All of those accelerators we know how to design, and we somewhat know how to program. We're going to basically add a different type of accelerator that doesn't have the bottleneck that all of those accelerators have. All of those accelerators are processor-centric. Why don't we have accelerators on the memory side where they have low latency, low energy, high bandwidth access to very large capacities of memory? That's the idea. In a longer term incarnation of this approach, I actually think that we should get rid of the accelerator model also. We should think of computation units as distributed computation units that are equals of each other. And you basically program things such that it's a distributed system, and everybody can offload, if you will, work to everybody else. So there's no centralized unit in that sense. That's kind of the paradise of a distributed computing person, but we're not there yet. We're still very centralized in our thinking, let's say. Okay, so our goal is this is a general slide to cover the challenges, and we're going to look at some of these challenges in this workshop. Essentially, our goal is to do processing inside memory and storage. In this workshop, we're especially going to focus on memory and storage. This doesn't mean that there are other places, there are not other places you can do computation like network, caches, sensors. They're all important, I think, and we need to figure out how to do that. But the workshop is focused on asking the memory and storage, can you actually execute this function, application, or query for me? And if the memory and storage is capable, it basically returns the results. And clear, there are many questions over here. Currently, we don't fully have the answers to, but we're getting there. Essentially, how do we design the memory and the controllers, compute-capable memory and the controllers? How do we design the processors and the communications? How can we simplify the processor once we have compute-capable memory structures and storage structures? How do we design the software and hardware interfaces to enable that? How do we design the compilers, languages, and system software to make it easy? And Geraldo is going to talk a lot about that. And there will be an invited talk that talks about compilation systems, for example, for processing in memory. And then also, it cuts even higher across the stack, because once you have compute-capable structures, how do you rethink your algorithms? Because your algorithms today are really optimized for processor-centric systems. And even within processor-centric systems, there are different kinds of algorithms you can employ based on the characteristics. But once you are doing computation, algorithms also, inside memory, algorithms also need to change. I also like to talk about the theoretical foundations, which is very important. So if you think about the theory of computation, probably most people here have a computer science background. How many people have a computer science background? Okay, quite a few. How many people have an electrical engineering background? Okay, that's good. That's the beauty of this. As you can see, we have the whole stack over here. How many people don't fit in either of those? That also happens. That's also good. So we're quite inclusive here. Everything is good. But basically, if you have taken a computer science theory course, the way we quantify the complexity or cost of algorithms is we count operations. Big O notation, big theta notation. We basically quantify the complexity based on how many operations we do as an order of magnitude. Maybe that's not that important, right? If you actually think about it, if the performance is really dictated by data movement, and we see in a lot of cases, maybe we need a different way of thinking about the theory of computation. So if you think about it, theory of computation is very processor-centric because that's the way we do computing. But if you do computing in a more data-centric manner, maybe the theory of computation needs to change as well. So if you're a theorist, I would recommend this is a good area to work on, in my opinion. I'm not a theorist, and I have a lot of other things to do before learning theory at this point, maybe, even though I like the idea. Okay, so I should also say that we're sitting on the shoulders of a lot of giants, meaning a lot of people have thought about this. We're not the first one to think about it. The earliest ideas go to 1960s, and this is a beautiful paper from Kautz that talks about logic in memory. This is going to be something processing near memory, as I will define it, and as Geraldo will go into a lot more. So people have thought about it for a long time, and people have actually proposed a lot of different mechanisms, etc. This is another paper from Harold Stone, who has a beautiful computer architecture book, if you have seen it. So what's different today, essentially? Why should we care, and why are we at a point where we could actually potentially think that we may have a much larger impact on actual systems and industry? So I think basically today we have nowhere to escape. When this idea was proposed in the past, our applications and systems were not as bottlenecked because things were scaling better in terms of both compute technology as well as applications were not that demanding. Energy and power were not big bottlenecks. Basically today, we have huge bottlenecks over here. And also we are very greedy in the sense that we cannot tolerate energy loss. We basically want to optimize performance, energy, and sustainability all at the same time. And minimizing data movement helps all of those. So we have a huge pressure from applications and systems. At the same time, and I'm going to spend a little bit of time on this because it's going to be a different topic that doesn't normally fit in this workshop as much. But at the technology level, we're having a lot of problems. Essentially, technology is very well. As a result, many scaling issues demand intelligence and memory. So how many people know about the Rollhammer problem here? Okay, that's good. Then maybe I'll discuss a little bit on that topic. Essentially, existing memory technologies are becoming much less robust. This means that in order to actually make the memory work, you need some intelligence and computation capability to make it work. And once you have computation capability to make the memory work, why not add other computation capability as well? Essentially, we have scaling problems, and also emerging memory technologies can enable new functions as well as they have some scaling problems. Basically, we're kind of squeezed in the middle today. Technology is not providing us a lot to fix the data movement problem, and also it's making it worse. And applications are pushing us with doing something else because we have a huge data movement problem. So I believe that's why we see also a lot of industry push in this direction, which I think is going to intensify, which I think also makes a lot of sense. Okay, let me talk about this technology problem a little bit very quickly. So this Rollhammer is this is one example technology scaling problem. And if you look at memory, this cartoonish picture over here, this is a small memory. As you can see, the cells are large. And as you make the memory smaller and smaller, cells smaller, so that you can have higher and higher capacity in memory, it turns out cells interfere with each other. Whenever you access one row, you interfere with adjacent rows. That's the Rollhammer problem fundamentally. Now, if you keep repeatedly accessing one row, activate precharge, or open, close, open, close, open, close, enough times before the cells get refreshed, it turns out in real DRAM chips, you can induce bit flips. So this is real. A lot of people actually have shown this problem. And we have actually done a lot of analysis on the problem, starting from ISCA 2014. And we've seen that the number of activations you need to do to induce these bit flips has reduced by more than 100x in the last 10 years because of technology scaling. Cells are becoming smaller, cells are becoming closer to each other. I'll not make this a Rollhammer talk because otherwise we'll be here for the entire day, but I'll refer you to a paper. This is a paper that we wrote about 10 years ago. There's a more recent paper that shows that the problem is actually much worse than we think. If you keep the row open a little bit longer, the disturbance you cause to adjacent rows is actually much worse. So the number of activations reduces by more than an order of magnitude if you know what you're doing. So basically, how do you fix these problems? These are some example problems. I think this is going to get worse. We're going to see more and more issues like this. Essentially, we need intelligent controllers to fix this problem. because other ways of fixing the problem, like changing the technology or doing something at the device level or circuit level, are too expensive. Otherwise, actually, DRAM manufacturers would have done it by now and should have done it by now. But it has not happened. Instead, we've always argued that you need controllers that are computation capable, that understand that things like this are happening and prevent that problem. So, and we've argued that for a long time, and people have proposed many intelligent controllers. And finally, industry is taking this direction. This is a paper from SK Hynix in ISSCC in 2023 that shows that they're putting essentially intelligent controllers in their DRAM chips. I will not go through details, but if you look at their pictures, what they have is some control logic inside DRAM that identifies how many activations happen to each row, and based on that, takes some mitigating actions. So this is something that would not happen even 10 years ago or so, because DRAM manufacturers are very cost sensitive. They would not put controllers inside the memory to fix this problem, but this is happening right now as kind of we envisioned, and it's a good thing in my opinion, because this problem needs to be fixed. But this is what I mean by essentially adding computation capability to memory to fix scaling issues. Now you have some computation capability in memory. Why not add some more, right? Why not add something to help the applications at the same time? So this could be very useful in my opinion. This also changes the thinking. That's why I like to discuss these technology scaling issues. And this is standardized in JEDEC last year. This is called per row activation counter. So I believe all DRAM manufacturers and increasingly all DRAM standards are going to incorporate this sort of intelligence inside the DRAM chip going forward. You could argue whether or not this is a good thing, but a good thing in terms of like, is this particular solution is a good solution? But I think solutions can also evolve into the future. The idea of the solution, which is intelligent control, is a good idea. And we've evaluated these. So if you're interested in this topic, we have some papers on this topic that talk about how good are these solutions. And the question to always ask is, are the solutions good? Like, will you get bit flips with these intelligent controllers? That depends on how good your controllers are in the end. And the good news is there's a lot of interest in this topic. We were at HPC at the beginning of this month, and there were 2 sessions on read disturbance, row hammer, technology scaling issues like this. And at ASPLOS, there are also 3 papers coming, not from our group, but there are actually 3 interesting papers from different groups that talk about these issues. So I'd recommend, if you're interested, taking a look at those. Okay, so I kind of hopefully motivated at the things at the both lower levels as well as the higher levels. And I strongly believe we have nowhere to escape today unless we have a magical technology shift in some way that minimizes the energy and performance cost of data movement, which is going to be really magic, probably. Now, let me introduce 2 types of processing in memory. We have a categorization of processing in memory in our long archive paper that we recently updated in January. But in terms of the nature of computation, I believe there are only 2 ways of doing processing in memory. One is processing near memory, the other is processing using memory. And processing near memory is shorter term. I believe this is much easier to adopt commercially, initially, because it's very similar to how we do things. Processing using memory is longer term because it has a lot of issues, but I believe this also needs to be done. In the end, I believe we need to combine both. In this workshop, we're going to discuss both. So what is processing near memory? I think of things like processing, logic, and memory. Today, we design them completely separate. You have a memory process flow, design flow, and design memory chips and memory structures with it. It doesn't have to be a chip, it could be structure. And then you have a logic design flow, and you design logic completely different. Even fabrication technologies are different depending on the technology, of course, but it doesn't have to be different. Basically, you design logic and memory separately. Processing near memory means that you take the logic closer and closer and closer and closer and get it as close as possible to the memory structures. It could be next to each cell, you have some computation units, but they're designed separate. You can think of it that way. In a sense, it's not different from what we're doing today because we're designing things separate. Processing using memory means you have logic and you have memory. Forget about logic. Assume we don't have logic. Assume we have only memory and the memory design flow, etc. Now, can we actually use the operational principles, analog operational principles of this memory to do also computation? And all memories actually have some operational principles that enable some type of computation. And we're going to explore that, especially within the context of processing in DRAM or processing using DRAM. And this is fascinating because it is fundamentally much more efficient and analog, but you will be probably limited by the types of computation you can do because you're really exploiting the device's natural properties and maybe enhancing them slightly. But you're not really adding complicated logic. So processing using memory is much more efficient when the computation actually fits what you want to do. But it's probably harder to do complex computations over here. processing near memory is very general. You can do anything with the logic next to memory, but it's probably a little bit less efficient because you're really still fundamentally moving the data a little bit between processor and memory. But in the end, I think both need to be examined and both need to be enabled in the long run. But the first one is probably much easier to enable, especially in today's technologies. Okay, so this is Geraldo's slide. He's going to cover this more, but essentially processing near memory can be done in many places. It could be done like in the logic layer of 3D stack memories, which could be integrated with different techniques. It could be monolithic 3D integration. It could be hybrid bonding. It could be something else. Or you could actually have processing outside, like in the memory controller, or you could have processing near the bank. You basically add logic. Processing using memory is you do analog computation inside the cells over here and the bit lines. I'm going to cover both of them, but again, I will not spend a lot of time because there's more to cover with Geraldo and others. So let me tell you one thing. If you were actually looking, having this workshop in 2018, 2019, we wouldn't see this picture today. So basically, I didn't enhance this picture also, but recently industry is also actively working on processing near memory, and they have pushed out either prototypes or commercial chips that can do computation. I'm going to talk about this 3D stacking a little bit, but essentially UpMem is probably the first company who has commercially pushed out chips that can do computation, general purpose computation. We're going to talk about that briefly. Other companies like Samsung, SK Hynix, Oliveira, they have pushed out DRAM chips that can essentially do acceleration of important computations like matrix operations, multiply and accumulate operations. And also companies like Samsung and Meta have pushed out modules where you can do FPGA acceleration near different memory chips over here for recommendation inference. So this is an area, this is an active area where industry is working on. And there are many experimental chips and startups, some of which are working on near SRAM computation, for example. So this talk is mainly focused on DRAM because DRAM is a dominant technology where you can store a lot of data. But there's a lot of work also going on in SRAM, near SRAM computation. And also, I will briefly mention flash, near flash or in flash computation as well. Okay, I think one thing that's actually useful in this is to enable having enabling interfaces that can enable offloading of computation. And I like CXL in that respect. CXL is an interface that has been recently introduced. It's actually similar to OpenCAPI, CAPI type of interfaces that people have looked at before. But the idea is to have the interface from the CPU to the other devices a little bit flexible, a little bit more flexible, such that you can do offloading of computation and also other things that people have been using CXL for. And people have been using CXL for offloading computation to memory. As you can see, there are some papers over here from SK Hynix and Samsung, which are quite interesting. Okay, now let me talk a little bit about processing near memory, and then I'll jump to processing using memory. Let me give you an idea that we had worked on like 12 years ago. It was published at ISCA 2015. And at that time, we were very interested in the integration technologies, 3D stacking integration technologies, and what it can bring to reducing data movements, improving parallelism, enhancing scalability on important applications. And we wanted to look at this sort of 3D stacking technology where you have a logic layer underneath memory layers. So you can stack memory and logic. Logic can be very nice. We assumed kind of that you can actually have very nice logic. Today, actually, we're getting there, meaning you can actually fabricate logic with a purely logic process. And you can actually have a high quality logic process like we have in CPUs and GPUs. And on top of that, you have memory layers. And the logic here can have, and memory layers are customized for memory fabrication, of course. And you can put them together, put these devices together in a 3D stack manner. And logic layer has high bandwidth, low latency, low energy access to the memory on top of it. So what can we do with this technology? And we banked on technology in the sense that, okay, at that time, technology was not very mature. We had HMC, etc. It was not very good at the time. Today, I believe HBM4, for example, will have a true logic layer as we kind of envision. Hopefully, it'll happen because that'll, I think, change how we think about systems finally. But we wanted to actually explore the possibilities we could have. And we designed a system for graph processing. We should have designed it for machine learning. But again, I think this is also applicable for machine learning. The basic idea is we want to have an accelerator that can accelerate large graph processing computations, which are actually quite dominated by random accesses. So processing near memory makes a lot of sense because you don't have a lot of locality in the computation, at least the way you bring it to the processor. So this is what we designed. We started with this cube, memory plus logic, 3D stacked memory. Inside the logic layer, we actually add an array of processing units. Each processing unit has an in-order core that owns the memory on top of it. And you partition your graph on top of these processing units such that whenever you need to do an update to a graph node with some graph algorithm, you send the function to the processor that owns that node on top of it. So you do remote procedure calls, you do function shipping to the data as opposed to moving the data all around between processors. So the programming model is slightly different in the sense that it's remote function call based, which is very similar to distributed system programming that people do in data centers today. And the idea is to minimize data moment, hopefully, by shipping functions to data as opposed to data to functions. And of course, one of these cubes is not enough because at the time the technology was 16 gigabytes or even smaller, but we assume 32, I believe. If you really want to do a large-scale computation on large-scale data sets, you need to interconnect a lot of these together such that, and then partition your graph across them such that you can do the computation in a distributed manner across these interconnected cubes, if you will. Essentially, that's the idea. And if you think about it, it's kind of like a machine learning system today, right? In a machine learning system, you can interconnect a lot of these GPUs together today, and you distribute the computation. You try to minimize data moment across the GPUs. So a lot of the principles that we use are actually, in my opinion, used in machine learning accelerators today, except you don't have this 3D stacked memory. I mean, you have HBM, but it's used in not as a computation, near memory computation. I believe that near memory computation will also happen. So this way, you can actually reduce the data moment as well as scale the application. Okay, so this is what we compared to. I'll just give you a basic result because it's an old paper. Maybe Geraldo will talk about it more, but there's a lot of work that has happened after this. So these are the systems that are processor-centric, and you can see that they have the processor and memory dichotomy, all of them. Tesseract looks like this. You don't distinguish processor and memory. Processor and memory are coupled inside this cube, and then you have a distributed system of these cubes, and then you accelerate things. At the time, we were able to achieve 8 terabytes per second based on some technology assumptions. Today, that number is much, much higher, of course. And with a very nice integration technology, that number can go even higher. This is 8 terabytes per second aggregate for 512 cores over here in order cores. And the performance improvements we saw at the time were quite significant. We basically, with slight optimization, not too much customization to graph processing, we got about 13x performance improvement on average across 5 graph processing algorithms compared to existing systems at the time. And the energy improvements were also commensurate. We got about more than 8x energy reduction. So this is, you improve performance, you also reduce energy at the same time. Essentially, your energy delay product improves by a multiplication of both of those. So this is good. If you don't want to have the trade-off, you improve performance, but you lose energy, right? So later works actually improved upon this work. This work was published, as I said, about 10 years ago. And they actually showed different ways of partitioning work, different ways of handling messaging, etc. And they basically show that you can actually get to 100x improvement in terms of performance and about 100x improvement in terms of energy. So I believe that this sort of approach is good, especially today with integration technologies that are much more capable, like hybrid bonding. We didn't have hybrid bonding at the levels that we had today, where you could actually integrate a memory chip with a logic chip with many more connections than what we assumed at the time. With newer technologies, you can have many more connections between logic and memory layers, and you can actually exploit that in a much better way. That terabytes per second actually increases to be much better. I believe there's more to be examined in this area. Okay, we did some other work in this area with a system algorithm co-design, but we don't have a lot of time, I think, so I'm going to skip some of these. If you want me to, we have time? 15? Okay, and I have like 45 minutes of slides. Okay, I can. Okay. Feel free to ask any questions. Maybe I will mention this because I believe actually this is a nice approach to exploit processing using memory and processing near memory. The idea is to define a different type of ISA that operates based on set data structures and express your algorithms in terms of sets such that you basically do a full algorithm hardware co-design with still an ISA in between. Because if you actually program using sets, and sets are actually a fundamental data structure, those sets are actually very nice in terms of implementing and processing near memory as well as processing using memory, because they are mostly bitwise operations. The key is basically expressing your algorithms in terms of sets. And this paper talks about graph algorithms. I believe there's room for machine learning also to be expressed in terms of sets. Okay, so let me quickly go over this work also with processing near memory, and then I'm going to switch to processing in memory. Again, this is the work that I mentioned that we did with Google on edge devices. We wanted to figure out what are the bottlenecks in existing edge machine learning accelerators, like the edge TPU. So we used 24 proprietary neural network models that are used at Google at the time. And we wanted to understand what is the diversity in these models in terms of computation complexity and memory complexity. And if you look at the models that are used, these are layers from different models, you can see that there's a huge diversity, meaning flops per byte, arithmetic intensity, is hugely different. You can see the number 10,000 over here, and you can see the number essentially less than 1 over here. So there's a huge variation. And also in terms of parameter footprint, how large your parameters are to different layers, input parameters and output parameters to different layers, you can see that there's a huge variation over here also on the x-axis. So the question is, does it really make sense to have a single processor-centric accelerators to try to cater for all of these diversity that happens in machine learning models? And our answer was clearly no, because if you have this huge variation, a single accelerator, monolithic accelerator, especially if it's processor-centric, is not going to be able to cater to this diversity. Okay, so if you look at diversity within the models, there's actually a lot of diversity even within a single model. So this is CNN, essentially convolutional neural network. Again, it's proprietary, used at Google. And you can see that different layers have different multiply and accumulate operation count, and also different arithmetic intensity. And that variation is like on the 2 orders of magnitude or so. Again, even within a single model, you cannot really design a single accelerator that can do well. And our idea was basically not to have a monolithic accelerator like people have been doing. I think people are still doing, but maybe adding more heterogeneity today. Essentially, instead of designing a single accelerator, have 3 different accelerators in this particular case. It doesn't have to be 3. It could be more or less, depending on your characterization. It could be reconfigurable accelerators also potentially, but there's a different dimension over there. Essentially, at the runtime, figure out which family does a layer belong to, neural network layer belong to, and ship it to different accelerators. And we designed one compute-centric accelerator that's much smaller than this one, because it doesn't deal with memory layers, memory-intensive layers. Memory-intensive layers get shipped to 2 memory-centric accelerators, which essentially do processing near DRAM, which is kind of similar to Tesseract, but a little bit less complexity because we're shipping only functions and layers at this time. That's the idea, essentially. If you design 3 accelerators this way, your compute-centric accelerators can be much simpler and much smaller because it doesn't need to deal with memory layers, memory-intensive layers. And you need to add memory-centric accelerators, which are customized for different data flows over here. Okay, so you need to have a way of determining either statically or dynamically which type of accelerators to use for which type of layers. And again, there's discussion in the paper. So you need to have a software runtime over here that is intelligent. And that's, I think, important to do. And once you do that, this is a picture that I showed you earlier, you get significant performance benefits. Essentially, we showed that this particular design reduces energy consumption by about 3x compared to the baseline HTPU. And we didn't optimize things too much in the sense that we just offload layers. And we don't actually exploit parallelism across layers as much also. You could do much better than these numbers, but these numbers were good enough for us to actually proceed with the idea. Throughput also improves significantly by about 3x, and latency reduces. And again, I'll refer you to the paper. We don't have a lot of time, but maybe Geraldo can also talk about this because he's worked on this a lot. Okay, so there's a lot of other evidence in near memory, near DRAM processing, which I will not talk about. As I mentioned, we do work on genome analysis, and we see significant improvements in near memory processing over there. And more recently, we have storage, and we have talks about in-storage computation, near storage computation later on by Mohammad and maybe others as well. But I will not talk about these. If you are interested in many examples, we have recently updated this book chapter, which used to be a book chapter. Now it's on archive. It's almost 100 pages. Sorry about that. But it has a very comprehensive treatment of a lot of things that is going on in processing in or near memory. And if you have suggestions, we're always open to getting suggestions from you and including them and making this work better and better. Because the goal of this work is to be a live reference for processing in memory. And Geraldo did a lot of effort in the latest version. Okay, I will not talk about these, but there will be 2 talks later on, and these are actually papers in ASPLOS. More recently, we've also been looking at large-scale systems for LLM acceleration using processing near memory mechanisms. This is one paper that Yintao will present later this afternoon. It's also going to be presented in ASPLOS in the processing in memory session. And I think there's a lot of potential for these large-scale LLM models or retrieval augmented generation type of models to be accelerated in a manner that's somewhat, from my perspective at least, resembling the Tesseract system that I mentioned earlier. It's a large-scale system, and how do you distribute computation across near memory units and maybe GPUs? In this particular case, we look at distributing work between two types of near memory units as well as GPUs. And we have another paper that also looks at using CXL interfaces and enabling communication mechanisms between different CXL devices to take advantage of processing near memory. And you can find these papers. It's going to be presented by Yufeng this afternoon, also in this workshop, as well as at ASPLOS. And these are the two different systems that I will not go into, but I believe there's more work to be done in this area, especially as applications scale. So this is kind of for large-scale systems, right? We're thinking of large-scale systems, terabytes and terabytes, even larger memories. This is another dimension where we should be thinking about processing in memory. But we also on the edge devices, I think there's a lot of potential. So across this board, wherever you use computing, mobile computing or data-centric computing, I think this idea makes a lot of sense, and there's a lot of evidence that's coming through. I believe there will be more. Okay, now I'll jump into processing using memory. Any questions so far? I think people are still waking up, maybe. I need to wake up also, sorry. I came very late last night, so. Okay, processing using memory. This is essentially fundamentally different. It's not going to be operations with new logic added, but we're going to talk about using the operational characteristics of DRAM or modifying it slightly so that we can do some operations, but maybe limited operations to begin with. So basically, I'm going to show you we can do block bitwise copying and initialization. We can actually do block bitwise primitive operations like AND or NOT, majority, NOR, and NAND. We can do true random number generation, purely, again, using analog properties, physical unclonable functions. And if you want to modify things and be a little bit more complicated in terms of the operations you want to do, you can use lookup tables. Because if you actually had a digital design class, I teach digital design to 550 students every other semester, every spring. And I like talking about using lookup tables and talking about using, for example, memory to do computation. Right? Essentially, it's a lookup table. You can use memory as a lookup table to implement any function in the end. Why don't we do that today? We could actually do it. The question is, what kind of functions can we implement efficiently? What kind of support do you need to add to memory, etc. So I think there's a lot more interesting things to do over here, especially because people are also figuring this out in the FPGA domain. And FPGAs, people are trying to use lookup tables for efficient arithmetic computation of neural networks. There are multiple papers on that topic more recently that I've seen, including at HPCA. I believe with larger memories, you can do even better. Okay, and we can do most of these at low cost, not all of these. The basic idea is to exploit analog computation capability of DRAM in this particular case, but emerging memory technologies are also very interesting and very important, and they also can do other things that I don't have in this picture. So the basic idea that I will discuss is we want to activate multiple rows, memory rows, either sequentially or concurrent. And this leads to data movement or computation, essentially. And it turns out, even in commodity off-the-shelf DRAM chips, even in DRAM chips that are designed today that you buy, you can see these operations. DRAM manufacturers will not tell you that you will see these operations, but we discovered using our infrastructure, testing infrastructure, that you can do block bitwise copy, initialization, and or not, NAND, NOR, all of those operations in real DRAM chips. I think this is fascinating to me because even though somebody did not design this chip to do this computation, we can see this computation. Okay, and you see significant performance energy improvements. Those numbers are somewhat stale over there, but we'll see some examples. Well, let me give you some examples very quickly, and then Geraldo will go into a lot more detail on some of these. Especially, we will also look at programming aspects, which I will kind of gloss over in my talk. Let's start simple. Essentially, if you're thinking about like doing this sort of computation, one of the resistances is this is mostly analog computation, and there could be variability and noise issues. We'll get to that, and that's true. And that needs to be solved, and that's one of the reasons why this is difficult to adopt in real life. But there are some operations that you can do using these principles that are quite robust. And I'm going to mention these first, which is essentially copying initialization of data. This is important. There are many applications that copy and initialize block data. Imagine initializing terabytes of database. Today, you go through entire memory and write zeros to memory. What a waste. And Google, in their work that I mentioned earlier, in ISCA 2015, they basically show that only these two function calls, memmove and memcopy, occupy 5% of cycles across their data center. That's a huge number for two function calls. This doesn't cover, of course, all of the other function calls that could be used. Okay, so again, let's think about this as a 10-year-old child. You give a picture to a 10-year-old child, tell them, when I want to copy a 4 kilobyte page, white page, to the black page or gray page over here, the way I do it today is I go through memory. I go through the CPU. I go through everything byte by byte, bring every byte, do the write and do the write inside the CPU and write back the destination. Should I be doing this? Probably, maybe, or maybe you should ask the question with a blank slate. Tell them how I should be copying this white thing to the gray thing. Probably they will be honest and they will tell you that, why not just do this? That sounds good, right? Because they're not bound by everything that we're bound by today. Essentially, that's the idea. Just do that. This is low latency, low bandwidth, no cache pollution, no unwanted data movement, no need for involving the CPU at all, in fact, except for maybe initiating the operation. Right? And I'm going to show you a mechanism that takes 1,000 nanoseconds copy, 4 kilobyte copy, to 9 nanoseconds, and 3.6 microjoule copy to 0.04 microjoules. And the idea is very simple. At the best case, you have DRAM consists of subarrays. Think about this as a subarray. A subarray may have a 4 kilobyte or 8 kilobyte row. Granularity is always an issue, and that's something that needs to be solved. Essentially, the idea is to first activate the source row, which brings the entire row or page, let's say, to the row buffer. Now the data is in the row buffer and strong. This is the structure of DRAM. You have sense amplifiers over here. If you haven't seen DRAM before, you have sense amplifiers that are much stronger than the cells at this point that store the data. They've captured the data. And basically, we then activate the destination row, which is not supported today officially by DRAM devices, which implicitly deactivates the source row and connects the data and the sense amplifiers to the destination. This basically overwrites the data in the cells and destination row with the data that was captured in the row buffer with the previous activate. So by doing 2 consecutive activates, by exploiting the principles of operation of DRAM, you move the data from one row to another row through the row buffer. Yes, you do move the data, but you don't go off chip. Because, and this is block data movement. You actually copy the entire row. If you want to go off chip, you have to go 8-bit by 8-bit, or 16-bit by 16-bit, depending on the chip that you have. If you're lucky, maybe 32-bit by 32-bit. But you cannot go 8 kilobyte by 8 kilobyte. Okay? And this is negligible hardware cost. And if you do that, you get significant latency reduction and energy reduction on relatively small copies, 4 kilobyte copies. And the paper, we have actually ways of doing smaller copies, etc., bank-to-bank copy, inter-subarray copy, etc. I'm not going to talk about those. And there's more work in this area. But this is the original paper that introduced the idea. Now, I'm going to show you soon that you can actually do this in real DRAM chips with almost perfect reliability. But before we get to that, let's talk about computation. This was consecutive row activation, as you can see. If you actually do concurrent row activation, you can actually do computation. Basically, I'm showing you 3 DRAM rows over here, A, B, C. I'm showing you 1 cell in each row. And each cell is represented as a capacitance. If the capacitor is full, it's a 1. If the capacitor is not full, it's a 0. That's by convention, let's say. And I'm showing you 1 bit line where they're connected to, and these are the access transistors. And this is a sense amplifier kind of peeked into in a little bit more detail. It's a cross-coupled inverter, essentially. So imagine this operation happening on 8 kilobytes of data. Now, I'm going to show you only 1 bit. If you concurrently activate these 3 rows, you concurrently connect the 3 capacitors to the bit line. And based on the values or charge levels in the capacitors, if at least 2 of these capacitors are charged, you get the charge state at the end, based on the sensing circuitry and charge sharing principles. If at least 2 of these capacitors are discharged, you get the discharge state at the end. Now, that's a bitwise majority function. This way, we have actually figured out that you can actually do bitwise majority in DRAM. That's beautiful. Bitwise majority, if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you have bitwise AND, bitwise OR. This is good, and it's bulk bitwise. You can do this on millions of bits, assuming you parallelize this computation across a lot of subarrays, which Geraldo is going to talk a lot more about later on. Now, what this missing is a NOT, meaning to be functionally or Boolean complete, meaning if you're Boolean complete, you should be able to implement any algorithm by rethinking your algorithms. You're missing a NOT. But NOT is actually already there, meaning if you actually activate one of these rows only, you get the complement of the row on the other side of the sense amplifier. There's no way to connect this to the existing subarray today, but we propose some mechanisms to connect it to the existing subarray in Ambit paper, which I will briefly mention. But there are multiple ways of taking advantage of that NOT also. I'll show you some results from real DRAM chips soon as well. So you can get NOT as well with some cost. This is not a lot of cost, in my opinion. You need some structural changes. If you want to get NOT, the inverted value, you need to pay a little bit more cost because you need to route the value to the right place. Okay, assuming that you have all these operations, we simulated this, and you on data-intensive workloads like databases, you get significant performance improvements and energy reductions. This is about 2017. This is the Ambit paper. And there are also other workloads that could benefit from this significantly, some of which we evaluated, some of which we did not evaluate, some of which later works evaluated, especially graph algorithms, for example. The SISA paper that I mentioned in Micro 2021 evaluates graph algorithms and set-based operations on graph algorithms on an Ambit-like structure, and shows much higher performance improvements than we show over here, actually. Okay, so more on Ambit. That was the idea. So this is theory. If you think about it, this is theory. We don't build real hardware. We basically show that circuit-level operation, you should be able to support these. And with some circuit-level simulations, we show that you get this sort of reliability, etc., depending on the variation. More recently, we tried to make it more programmable, and this is the SimDRAM framework that Geraldo developed heavily. And the idea is, can we implement any operation on top of this sort of substrate? And essentially, the idea is you can make it easier on the programmer by having a flow or framework where the programmer specifies the operation that they want. This could be any operation, as long as the programmer can specify it using this sort of diagram and or not logic, essentially. It could be convolution, it could be matrix multiplication, it could be string copy, it could be anything you want, essentially. We take it and we form a majority inverter graph out of it. And we optimize this majority inverter graph using electronic design automation techniques that are actually developed for superconducting logic from EPFL, which is beautiful work, in my opinion. Around the same time we were developing these majority functions, they were also looking at majority functions to do other stuff, different stuff, not in-memory computing. And then we actually generate a sequence of DRAM commands based on this minimized majority inverter graph to do essentially triple row activation or row clone, and also some allocation of rows. There's a lot that goes on here. And then we associate that microprogram with the operation that you want. Again, it could be convolution, for example. And when the application is instrumented by the programmer or the compiler with an operation, that operation gets shipped, that bulk bitwise operation, that operation gets shipped to the memory controller, and the memory controller goes through the sequence of the microprogram to execute that operation. So this is a nice clean framework where the programmer doesn't need to deal with the low-level details of the DRAM and how it can be actually used to execute operations, but the programmer is shielded and they can implement any operation. And Geraldo and Nathan showed that you could actually implement many operations at the time, and you could actually have significant throughput energy improvements compared to both CPUs and high-end GPUs at both operation level as well as common real-world application level. So low bit with neural networks were an example where you could actually do well on these. But then clearly there are other things as well. Like genomics is a very good fit because you do a lot of bitwise operations where you that are essentially bitwise. You don't even need like bit by bit operations. Okay, more on SimDRAM, and I think Geraldo will talk about it. More recently, Geraldo has published this work at last HPCA, where he solved some of the issues in SimDRAM, and also prior work on this block bitwise operation paradigm. And the problem with these paradigm, one of the major problems with this paradigm is you cannot do narrower with operations because the structure of DRAM dictates you to operate on row granularity, 8 kilobytes, let's say. And the idea is to enable narrow width operations because this will actually help a lot of things. Essentially, so let me talk a bit about the enabler, which is fine-grained DRAM. If you actually modify DRAM a little bit, you can enable lower width operations, like 512-bit operations, operate on a DRAM mat. This requires some modifications called fine-grained DRAM in general. A lot of people have proposed it to save energy in DRAM. So there's another very good reason to do this. Today, we actually access a very large granularity, 8 kilobyte row, and we may need only 8 bits of it. And if you don't have a lot of locality, we bring the entire 8 kilobyte row inside the DRAM, and we take out only 8 bits out of it. This is actually a lot of waste of energy, regardless of whether or not you're doing processing near memory. Now, if you can actually enable fine-grained access like this, smaller bit width access, like to a single mat, 512 bits, you can reduce that energy. And we have a paper that was recently presented at TACO High Peak that talks about that in a nice way if you're interested. Now, essentially, if you use this idea, enable the segmented word line to enable independent access to mats, this improves SIMD utilization. If the parallelism you have in the application is not at the granularity of 8 kilobytes, but maybe 512 bits, then you can map it to only a single mat in DRAM. This way, you don't waste a lot of capability that you have. And you can use the other capability that you don't use it for this application for some other application, or for some other instruction in the same application. So you can actually pack things better across DRAM subarrays. So this is the multiple instruction, multiple data execution model. We also add some low-cost interconnects for vector reduction. This is actually processing near memory, I would say. Essentially, you add some more logic over there to do reduction operations, aggregation operations, etc. Those are, I think, important to support in DRAM going forward. And this also eases programmability by doing lower granularity bit width. You can target existing compilers that normally target AVX operations, for example. The bit width of AVX is not 8 kilobytes. It's 512 bits. And a mat width is really 512 bits. If you can directly target an AVX compiler to compile into a processing in DRAM operation, that's much better. And that's the idea that Geraldo had. He added compiler support. He may talk about that later today, and to LLVM, so that the compiler automatically extracts SIMD parallelism and maps things to the DRAM mats, and also generates the binary with appropriate data allocation and processing using DRAM instructions. I'm glossing over these because he will talk a little bit more about it. And if you have questions, there's a paper. The source code is also available completely, right? So you can actually, if you're interested in the full tool chain and the compiler, you can find the source code and improve on it. And you see significant performance energy improvements. And these are large numbers because if you think about it, what we're doing is right now we're exploiting the entire DRAM as much as possible. And if you exploit entire DRAM, you're really exploiting the entire substrate for computation. Most of the substrate is used for computation. Whereas if you look at a GPU, for example, there's a lot of stuff that goes on in a GPU that's not useful for computation. Most of the hierarchy, memory hierarchy, for example. Whenever you're really doing computation, there's a very small part of the chip is active, and you do a lot of data movement and memory hierarchy operations. As a result, you waste a lot of energy. So performance per watt is wasted a lot in existing processor-centric systems. Whereas if you do bit level parallelism in DRAM, your computation efficiency is actually very high. You not only reduce data movement, but you're using every single bit to do computation over there. Okay, it's good to think about that, I think. Okay, in the last part of the talk, unless there are questions, let me talk about some fascinating things. Meaning, okay, all of this is kind of, you can think, at least the processing using memory part, as theory, right? It's theory in the sense that, yes, these are real circuit principles, these are real operational principles, and we exploit them, and we can simulate them, and we can show good results. But can we do these in real chips? I would love to do this on a real DRAM chip, implement all of these, but that's extremely costly in academia. DRAM manufacturers tend to be extremely conservative. They don't want to do anything. They want to just sell their DRAM chips and do nothing, ideally. Sorry, if you're a DRAM manufacturer, this is not to say bad things about you, but this is the state of the art in business. It's kind of like the processor-centric system, right? You cannot get it out of it. So basically, we wanted to say, can we actually do these operations in real DRAM chips? And the idea is yes, essentially. We showed in this work, actually, an original paper from Princeton, Compute DRAM paper, showed that based on our work, violating the timing parameters in real DRAM chips, you could do row clone type of operations and some bitwise operations. We replicated their study and proposed open source an infrastructure, FPGA-based infrastructure, where we violated the timing parameters between two activates. So if you think about row clone, you activate one row, and then in quick succession, you activate another row. If they're in the same subarray, then you actually do the copy. Now, if you violate the timing parameters in existing DRAM chips do not allow you to do this, but you could violate it using an FPGA-based infrastructure. We have an FPGA-based infrastructure where we change the controller. We reduce the timing parameters between activate to activate, and you can see that you can actually, the real DRAM chip can actually perform this copy operation as we envisioned, which is nice. It can also do random number generation as we envisioned. I'll very briefly talk about that later. You can download this. You can actually use this. If you're interested, you can see these results, which is beautiful, I think. But what we do in the system is a full end-to-end design, including the operating system support to do the data mapping such that the source row and the source page and the destination page gets mapped to the same subarray. So there's some reverse engineering that we do. Essentially, we have a RISC-V system on the FPGA, and this RISC-V system executes an application. When the application encounters a page copy operation, this gets translated into operations that go into the memory controller, and the memory controller violates the timing parameters, executes the operation in DRAM, and says that I'm done, and then the processor continues. So it's essentially, it's somewhat similar to the SIMDRAM framework. And we incorporated a row clone operation. That's true for random number generation also. If the program executes a random number generation through random number generation function, rand, let's say, you send it to the memory controller. Memory controller violates some timing parameter, generates the random function, random number in DRAM, and sends the random number back to the RISC-V core. So the paper has a lot of evaluation. If you're interested, you can look at it. But we see that these are real results from this real system using some micro benchmarks, copy and initialization micro benchmarks, and you can see that the throughput improvement is significant. This is a huge throughput improvement, and the reason you get this huge throughput improvement on this infrastructure is the RISC-V processor that we have is very wimpy. It's only 50 megahertz. It has no latency tolerance mechanism. So you would not get this improvement in a, let's say, well-designed high-performance processor, but you would get still an improvement, not as much as what you see. Okay, so if you're interested, we'd be happy to support people who are working on this. We have another paper that's coming up at DSN. It's called Easy DRAM that makes some of these things easier. So we're going to release that also soon. Okay, let me talk about one more thing, and then I'm going to conclude toward the end. And this is also another paper that we published at HPCA last year. And I find these results fascinating, frankly. We wanted to understand, can you see some of these, especially the complement operation in DRAM? And let me summarize. Actually, this is the result of two papers summarized into one. Using our FPGA-based infrastructure, which I will show you, we show that existing DRAM chips, by violating the timing parameters, can open many rows. Meaning you can open up to 48 rows concurrent. You can actually do a 48 input majority function in DRAM today, which could be useful. We actually studied it in a DSM paper last year. But you could also copy one row into up to 31 other rows with almost perfect success. Meaning the reliability of this is almost perfect, as you can see. You could perform the NOT operation with up to some number of output operands, and you could perform up to 16-bit AND, NAND, OR, and NOR operations. Let me give you the basic idea. So a row clone we discussed, right? By violating the timing parameter activate, you can activate the source row, activate the destination row in a sequence very, very quickly, and you could copy from the source row to the destination row. This is the data values. SRC is the data value. If you want to do a multi-row copy, you activate multiple rows. Again, by violating specific timing parameters, you can activate 32 rows. And you can do the same thing. You can copy one source row to 31 other rows. Let me give you the key idea of the NOT operation, and then I'm going to show you some results. NOT operation is what I mentioned earlier. This is the source row. This is the destination row. It happens to be on the same different subarray. And there's a NOT gate over here, as you can see. You can connect rows and neighboring arrays through this NOT gate. You activate the source row first, and the sense amplifier senses it, and the destination, the complement is sensed over here. And once you activate the destination row, it captures the value that's sensed over here, which is the complement of the source row. So that's how you implement the NOT operation. If you generalize this, you can actually manipulate the bit-winding voltage to express a wide variety of functions. I'll give you an example. Assume that you have two rows over here, A and B, and two rows over here, X and Y. I'm showing you, of course, only one bit per row. Now, if you had a primitive to concurrently activate all of these at the same time, what happens, again, at the circuit level is, the sense amplifier compares the average voltage of A and B to the average voltage of X and Y. If the average voltage of A and B is greater than X and Y, this becomes 1, and this becomes 0, okay? Now, let's take a look at how we can take advantage of it. This way, by manipulating things carefully, you can actually implement any function. Let me give you one example over here. We're going to violate these timing parameters, act, pre-act over here, make them 3 nanoseconds. It's not allowed in today's standards, but with an FPGA-based memory controller that you can modify, you can do it. And we're going to store, this is going to be our reference subarray over here. This is going to be VDD. This is going to be VDD over 2. There's a way of setting a cell to VDD over 2 in real DRAM chips. And this is going to be our compute subarray. So these are going to be our inputs, X and Y. And these are going to be the references that we're going to use to enable the computation. Now, if you concurrently activate all 4 of these, what happens is, if the average voltage of X and Y is greater than 3 VDD over 4, which is the average voltage over here, then the result in the compute subarray will be a 1, right? Otherwise, the result in the compute subarray will be 0, and the result in the reference subarray is always a complement of the result in the compute subarray. And if you think about it, there's only one case in which the average voltage of x and y is greater than 3 VDD over 4, which is when x and y are both 1 VDD. Otherwise, the voltage over here is smaller than 3 VDD over 4. And this is an AND function, essentially. So basically, in the compute subarray, you get the AND function. In the reference subarray, you get the NAND function. Okay? So you get the NAND of x and y in the reference subarray, AND of x and y in the compute subarray. So that sounds good, right? Similarly, you can implement NOR and OR. And once you have the NAND function, you're functionally complete. You just need to figure out how to route the data, etc. So I'm waiting for some people to build compilers for this sort of thing. I think it's actually very interesting to take advantage of. Okay, our goal is not to actually propose this as a substrate that's viable. This is a substrate. This is basically to show that there is a lot of potential in existing DRAM chips to do this sort of computation. Okay, and the paper has a lot of details. Now let me give you some results because reliability is always a problem. So we actually built an FPGA-based infrastructure that's called DRAM Vendor. Before that, it was SoftMC. We open sourced it. A lot of people are using it. We're really happy to help anyone use it. And the idea was to have a programmable memory controller to test DRAM chips. You could test many different functions. You could violate timing parameters, etc. So we tested a lot of DRAM chips from many manufacturers for these works. And we found out that essentially copying one row to 1, 3, 7, 15, 31 rows is possible. And you actually get almost perfect reliability, meaning almost all of the bits are correct. Again, you may ask, why aren't all of the bits correct? Well, we don't know exactly. This is something that we're investigating right now. But it's fascinating that almost all of the bits are correct because DRAM chips are not designed for this purpose. You don't see a DRAM manufacturer telling you do this. I think the fact that we're getting only 0.02% incorrect means that we could do better than this. And actually, maybe there are some applications where you could actually take advantage of it as well, off the shelf. Who knows? Okay. So there's impact of data pattern, temperature. That's all examined in the paper. So doing AND, NAND, OR, and NOR is a little bit more difficult. You don't get 99.98% success rate. And it's also very dependent on the input operands. The variation, circuit level variation, is much larger if you actually do this sort of computation. But we still see significant success rates. For example, for this case, when you actually do 16 input operations, you can see that the success rate is 94%. Not enough for many applications, probably, but our goal is not to enable this for applications. Our goal is to demonstrate that you could actually do these things that we have been envisioning on real DRAM chips without any modification, which means that now imagine what you could do if you actually go and think about this DRAM chip as a substrate that can do computation. You can do probably much, much better than this. And that's the hope, and that's the goal. That's one thing we're working on right now. And if people are interested, I'd recommend you to think about it as well. So, of course, if you want to do this sort of study, you need to analyze what is the impact of data pattern, what is the impact of temperature, what is the impact of different things, and they all slightly affect things. And there's a lot more in the paper that I don't have time to talk about. And this is the paper, the functionally complete Boolean logic paper. The source code is all open, so people can actually develop on top of this if they're interested. There will be a presentation this afternoon on some other folks that have built on this work, and they will report their results this afternoon. Okay, this is a paper on multi-row copy if people are interested. So it's always good to ask the question, what else can we do using commodity memories? These are some examples. I think there's a lot more to do, which I don't have time to cover because I think you want me to stop soon. You can do true random number generation. These are all based on real DRAM chips. By violating the timing parameter, you can actually generate true random numbers. Very basically, key idea, you have some latency that you need to access memory reliably so that you can sense the data reliably. You reduce that latency, the bit becomes flaky, meaning sensing becomes flaky. Now, if you reduce the latency in a controlled way, in a careful way, what happens is what you're sensing becomes the sense amplifier noise. And that noise, fundamentally, as far as we understand, is truly random. So by identifying cells where you can reduce the latency by an amount, where you can actually sense the sense amplifier noise, enables you to read that cell as a random number generator. You access that cell every time, it gives you some flaky number. It's random. It's truly random because it's based on a physical process. And that's the idea over here. Identify those cells and use them as random number generators. And we did this on a lot of real LPDDR4 DRAM chips at the time. I showed that you could get true random numbers from DRAM. And there are actually other works that we built on to do better. And we have another work where we can do even better over here. And we have some system level results as well. You can do physical unclonable functions, which I'll not get into. If you want to do better, you can do a lookup table better meaning more complex operations you want to do, probably go to lookup tables. Very quickly, a lot of these things that I mentioned, you can also do in Flash, except the nature of Flash is a little bit different. So the way you actually get the AND function or function is slightly different. I don't have time to talk about it, but this is the paper that we published at Micro 2022. And in real Flash chips, we show that you can actually do bitwise AND and bitwise OR. We have a paper at ASPLOS that actually takes advantage of some of that and also proposes some improvements on top of it to do better homomorphic encryption using in-flash computation. This is going to be in the first day, in one of the first sessions of ASPLOS. If you're interested in homomorphic encryption and in-flash processing, this is an area where actually memory-centric computing matters a lot because homomorphic encryption tends to be extremely data-intensive and memory-intensive. And people have been exploring approaches for both in DRAM processing and in-flash processing. In fact, at last HPCA, IBM had a paper on in-memory processing, near DRAM processing for fully homomorphic encryption. Okay, I can talk more about that, but we don't have time. So I've covered this, let's say, taxonomy in terms of the nature of processing in memory. There's a lot more in our paper, as I mentioned. Let me quickly mention this. We're going to talk more about this in the later part of this workshop. Adoption issues are extremely important. You can design any kind of hardware. It could be useless because nobody adopts it. And there are adoption issues. If you think about the barriers of adoption, most of these are related to systems, software applications. So we need to, I think, figure out what are the killer applications, what are the better software mechanisms we can take advantage of PIM. Ease programming. We're going to talk more about that. Compiler support for PIM, interfaces, hardware support for programming support. All of these are, I think, important. System and security support, coherence, synchronization, virtual memory, etc. There are a lot of works. I think Geraldo will cover some of these. At least he will give you pointers to it. I would actually have those slides in the backup slides if you're interested. Runtime systems to enable better data mapping, access and sharing control. And we still need to design better infrastructures to assess benefits. Right? Having good infrastructures to realistically assess benefits, for example, for systems that are based on 3D stacking, is actually very useful for development. But FPGA infrastructures, like what I mentioned, are also quite important because it's very difficult in general for software development to happen on simulators. Software development really, in general, needs real hardware. That's one of the benefits of the UpMem system, for example. UpMem released their commercial hardware, and that enabled a lot of software development on processing near memory systems on a particular type of processing near memory mechanism. I believe all of these can be solved, and there are a lot of people working on it. I think we need a lot more people in both research and development and industry communities working on these challenges. Because if you think about the number of people working on these topics, they're increasing. We have increasingly more processing in memory, processing in storage sessions in top conferences. I think this ASPLOS has at least one processing in memory session. HPCA had how many? Maybe three processing in memory sessions, for example. That was not the case about 10 years ago, for example, if you think about it. But still, compared to the set of people working on processor-centric systems, this is still small. The processor-centric system dominates everything today. Okay, that's the mindset part, I think. I think our mindset is dominated by processor-centric, and we should probably change that if we want to change the way we design systems. So in the end, I think we need to revisit the stack with a different mindset. Okay, let me conclude. I think we want fundamentally energy-efficient architectures that requires us to be data-centric or memory-centric. We also want fundamentally high-performance architectures that also requires us to be data-centric. I think I can change this to fundamentally robust, fundamentally scalable, fundamentally secure. I believe they all point us to data-centric, but evidence over there is building. That's why I don't want to put those on the slides yet. But I believe data-centric is a very important part of all of those. And we want to minimize data movement for these systems. Okay, I highlighted major recent advances in processing in DRAM, especially. A little bit of note of emerging technologies. Some emerging memory technologies are very important, I think. Actually, all of them are important to examine in an academic sense. But DRAM and Flash still happen to be the largest players, and it's not clear when an emerging memory technology will emerge. There are smaller market domains where some technologies are actually quite powerful, like in edge machine learning, for example. It could be very useful to have some amount of NVM to do matrix vector multiplication natively in the analog domain. But that's a different talk. And traditionally in our memory-centric computing tutorials, we had talks on emerging memory technologies also. There will be some talks that will touch upon that today as well. So I've hopefully shown you a lot of examples where we saw orders of magnitude energy and performance improvements in using processing in DRAM. There will be more throughout the course of today. And what is fascinating, even more fascinating, is unmodified DRAM chips that you can buy off the shelf are already capable of computation. And I think memory should be designed as a combined computation and storage substrate, as opposed to an inactive storage substrate that we think about it today. For this, the design mindset and flow should really change. Of course, this opens up a lot of adoption issues also. So I think the future is bright, but we do need to keep doing the research and design across the computing stack with a proper mindset and infrastructure. We do need to work on technology. And we also need to, I think, believe in the technology, right? As I mentioned the story of the Tesseract paper, we believed in the technology at the time. A lot of people actually questioned, oh, HMC, where is it going? It doesn't matter for me, right? I think 3D stacking is a technology that will hopefully be enabled better and better over time. Today's incarnation may be HMC, and tomorrow's incarnation may be HBM. Next 5 years incarnation may be hybrid bonding. Next 5 years after that incarnation may be monolithic 3D stacking, right? So technology actually can enable some of these advancements in a much better way also. That also helps the mindset, in my opinion. Okay, so this was our tutorial at Micro. I think Geraldo mentioned some of these, but this is our tutorial at PPOP. So we organize these tutorials, but this is really the first workshop where we invited talks from other folks to have a broader discussion, and you will see that this afternoon. But if you're interested in more of these, or contributing, or attending, or presenting, you can certainly come to ICS. We have the second one, and we have the third one at ISCA. If you're fond of traveling, this is one option. You can travel with Geraldo. Let me finish with these. Basically, we open source almost everything you will see from us, at least in this workshop, but also from others. Other folks are open sourcing their work also. I think this is very good for adoption of the work, as well as enabling the adoption of the general memory-centric systems. You can find a lot of these online. We'd be happy to help if people are interested in working on this. And the papers, talks, and artifacts are also online. I'll thank my research group. A lot of them are here to organize things, especially Geraldo, who has been a veteran organizing these things. You can talk to him. He's on the job market, so he's going to be graduating soon, and he'll be a good catch, probably. But he will finish his PhD at the end of this April. Yeah, not March anymore. Are we in April now? Not yet. Okay, I'm prefetching. Okay, we acknowledge a lot of people who have supported this work. They continue to support this work, and over years. Hopefully, they will continue to support this work also. And these are some faces that you can see, some of which are here. Okay, I'm happy to take any questions right now, or we can also discuss at any time. Yes, please.
So, when you are talking about the more complicated functions, you wish to simulate when you actually need. There must be a limit to at what point it becomes too complex. And you
yeah. So that's a very good question. I don't have an exact answer, unfortunately, because the research on lookup tables is not enough also. I believe we have some research, this Pluto paper, but there should be better ways of doing that, frankly. If you're really like complicated, large bit width, etc., then I think you should really design logic for it. You can decide to put that logic in the logic layer of DRAM, so you don't have to go all the way to the processor. But lookup tables are good if you really want to be efficient with low bit width, in my opinion, today. So if your bit width is like 4, that's probably okay. If you go higher, like 8, 16, probably it makes sense to go lower. But then there might be alternative techniques for encoding data that could be useful for lookup table-based computation that people should examine. So that may change the equation. So bit width in general determines whether you want to actually do the processing using memory or processing near memory. You're welcome. Yes, please.
What is it?
You said memory tiering. So basically improving the systems that use memory tiering. That's right. Yeah, exactly. So I think those ideas are like complementary to processing in memory, near memory, right? Whenever you tier memory, for example, you can do computation in all of those memories also. And maybe you don't need to move data as much, right? People still treat the memory tiering mechanisms from a compute-centric perspective, right? All of that tiering infrastructure, all of that hierarchy, that additional hierarchy, is really serving the processor. Whereas if you think about it, the memory tiering system has a lot of devices that can potentially do computation concurrently, then I think you can actually take advantage of it. So I think a lot of these tiering, also disaggregation, like if you disaggregate memory somewhere else, I get this question a lot also. Then I think it's also complementary, right? If you disaggregate memory, that's good. You're trying to utilize a memory pool for something because you want to optimize cost. You can actually put computation also next to all of those disaggregated systems and essentially take advantage of it. So I think the ideas are complementary. Okay, I don't want to name a single technology. I think CXL is one incarnation of a flexible interconnect technology. I think that's very good in the sense that people are moving to these more flexible interconnect technologies that can enable different things like tiering, disaggregation, or doing computation somewhere else. I believe we need more such interfaces. I'm not saying CXL is, I'm not suggesting CXL is the best interface for this purpose. I believe there are other interfaces. In fact, I think the interface problem that we have is huge in modern systems. There are so many interfaces, right, that are somewhat hard to design. But I think it's a step in the right direction for what it enables. It doesn't solve all of the problems with the interfaces that we have. You're welcome. Yes. Okay. I think it depends. Depends on what you mean by a lot of this technology. Processing using memory may not be easy with the control flow type of applications because it exploits data parallels. But processing near memory, I think graph processing applications can actually take a lot of advantage from processing near memory. So I don't think of it as control flow versus data flow. I think the parallelism that you exploit with processing using memory is bit level parallelism. Yes, you will probably need to parallelize very nicely, but processing near memory is much more general. Like we have demonstrated with the Tesseract paper, for example, with applications that are dominated by a lot of like complex control flow, you can still get a lot of benefits because a lot of your bottlenecks are data movement, for example. Yeah, we can discuss more, but Geraldo will touch into that a little bit more also, like what makes an application more or less suitable. And he will introduce some metrics later on today. And a lot of the metrics are really dependent on the arithmetic intensity, how effective are your caches, etc. Yeah, but yeah, essentially, you can get a lot of benefit on those applications as well. Sure. Okay, one more.
Jason.
Yeah. Yes. Yes. Mm-hmm.
Netless.
Mm-hmm. Mm-hmm. So you're thinking of like a vertical layout of the data, or is that different? Yeah. Yeah, I think yes, a lot of these depend on vertical data storage. And Geraldo will talk about that. You need to think about the data storage in a different way. But yes, I think the way you're thinking makes a lot of sense, basically. How do I optimize the logic in a way that I can do vertical computation? Yeah. Yes.
Were actually picked out more
So it depends. The results that I presented on our work, Tesseract, etc., those are simulation level. But we also have a lot of works that I didn't present that are based on real chips, using, for example, the UpMem company. We have, I think Geraldo will talk about some of those later today, but we have results from real chips as well. And that actually shows benefits on many applications, but it also shows downsides because of the design decisions that are made. So there's a variety of work. There's also other work from real chips from Samsung, SK Hynix, and Alibaba that we will touch upon again later today in the morning. Yes. I mean, I think yes. I think it's possible to support these. Of course, the complexity may increase depending on what you support. Like matrix multiplication, I think a lot of works from Samsung, SK Hynix, they are supporting primitives for matrix multiplication, right? Adding more to support primitives that can be beneficial for all of those workloads is possible. It comes at the cost, of course, right? So people need to make the design decision of actually what to support over there. But it certainly needs to be examined, and I believe there's no reason why they cannot be supported. So there are works actually that look at that in many conferences recently. Maybe Geraldo will touch upon those also. But I'm happy to talk about these. Okay, let's switch gears now. Thank you for the interaction, and I'll leave it to Geraldo. Okay. Just probably take a look. Don't forget.
Okay, so you are officially on the coffee break actually now. So let's come back at 11, and then hopefully they have some delicious food
And good coffee.
and good coffee. I need to make some adjustments.
Okay.
It was a very nice talk on it.
Okay, great. Yeah.
About the DRAM vendor.
Yes.
The memory controller is is located in the DRAM module or in the CPU.
The memory controller is in the FPGA, right?
In the FPGA.
So you didn't have to cut from the board of the memory, cut the chip that is the memory controller. You didn't deactivate it. You didn't deactivate the memory controller that was already in there.
On the where is there? Because like everything's FPGA board, right? In DRAM vendor. So you have the FPGA board, right? And then there is some logic. Okay, the FPGA board might have its own memory controller, but that's not enabled. That we are not using.
You don't use that, okay?
So that the DRAM vendor comes from another OpenVG soft-MC, which is basically a memory controller design. So we instantiate our own memory controller.
So you disable the memory controller of the FPGA, you put your own memory controller.
Yes, and then we interface that
And
to.
then you use the
Hopefully.
use the DRAM module and connect it to your own.
Yes,
Okay,
yes, exactly. Mohammad, is your slides ready?
Yes.
Can you send them to
I'm
me?
going to send you the
upload
final slides. There were some bugs actually.
I upload them? Okay, I didn't. Thank you so much.
Yeah, I took a bit longer, but
But
hopefully
I
it was
think
good.
that was very good actually.
Okay, good. Yeah, I think it was good. And Geraldo is a bit sleepy, so he got rest.
Yes. you may saw that I was working until very late yesterday for the ICS stuff.
Sure, yeah, hopefully they went well.
I hope so. Hope we have good chance.
Yeah, I hope that guy's a champion and even Dappa
Can get accepted.
Yeah.
Be amazing. Oh my gosh, BFO should be very bad.
What?
I'll work so much in the conference. Like it would be so much work I would have to give to talk. It's okay.
What kind of power supply? Like this?
Yeah.
Is there an audio jack here somewhere?
Sorry?
Is there an audio jack?
No. We are don't have an
Outside there is
No, I know the microphone, but there should be an audio jack somewhere.
I saw that behind the house. They were looking
You're looking
behind
for a
the
power
car.
output, basically. Oh,
No,
no,
you're
looking at a power adapter. What is the circuit?
Is it only HDMI?
I don't see any. Let me just. I need to fix some stuff.
Yeah, the system.
What do I need to do?
Is there a
I need
problem?
to.
Did they hear my presentation over there?
But no. The problem is we're trying to check if the audio works, right? And of course, this is not on us. We
Oh, I
we
see.
paid a very expensive
true,
company
yeah.
for this.
Isn't this a
And-
conference center?
Yeah, don't get me started.
Really? For what? For DSN? Do you have a DSN paper?
The security people.
That you couldn't be present here? Was accepted to DSN. Oh, congratulations, Constantino. That's great.
We have the stock actually for a workshop. You can have it.
I sent the email. I suggested that.
No, it's missing, right? One of us.
Yes.
I mean, it has a unique. But I guess you didn't have it. I have.
Whoa, my phone died. Constantinos. Constantinos, when you use your phone, my phone died for webcam really quick. I don't know if it's going to. It's going to work. Why? Why not? It's just join Zoom and I spotlight you.
Yeah.
Just until my charge.
I can do that actually.
Yeah, that's okay. Whoever
Let's see.
is in the calendar invite. Can you join the Zoom? Hello, is there anything? Is there any problem?
So, is it the audio working?
Apparently, yes. Okay. The guy checks and makes place.
You can hear it from the room, right?
This is my audio? I guess so, because he joined Zoom. Yes,
And
yes.
you can hear it from the room.
Yes, exactly. We can double check. Yes.
Perfect.
Thank you so much. Yes. Sure. Should be like this.
Like this or?
Usually it's like this.
Okay.
Then you can change the camera. Thanks so much, Mohammad. But I'm not sure if my camera is now. Oh, yeah. I need to spotlight you. Is it muted? Okay, perfect. And also there here. Perfect. It's very good, Mohammed. It's just until my phone charged. I don't know why they have this thing that only three people need to join, so I can spotlight. Okay. Hopefully everything's right. Can you check the YouTube live stream? Is everything fine, right? Perfect. Okay, so let's continue. That was a very nice talk from Onur. I'm going to try to keep the energy high. Now we are going to get a little bit more specific. So Onur briefly talk about memory-centric computing as the field. I'm going to specialize a little bit in both processing near memory and processing using memory architectures, starting with the processing near memory ones. So just a recap, we are splitting the field of memory-centric computing or processing memory into two different approaches. The near memory is just adding logic close to the memory arrays themselves, and the using memory are going to use the analog operating principles of the memory cells for computing. So as Onur also mentioned, processing memory is quite broad, and we can employ processing memory for many different application domains. Today is quite trendy to employ processor near memory architectures, for example, for transformers, right? Neural networks. And we are going to talk about advancements from industry during this talk that you're going to see that are quite tied to a particular application domain, either recommendation systems or transformers. Okay, so let's get a little bit into a design mindset for processor near memory architectures, where our goal is to move data computation near the memory arrays themselves. And the first question is, how close can you move computation to near the memory arrays themselves, right? As the answer is as close as you want, as long as you are okay paying for the trade-off that comes with, which I'm going to mention next. So that can be, for example, Onur mentioned the Tesseract paper, right, where we added computation, the logic layer of a 3D stack chip, and you're going to see some architectures from Samsung that does something similar as well. They use 3D stack based memory for processing near memory acceleration. Also, a simpler version that is less intrusive is adding logic near the memory controller itself for doing some sort of computation. So this does not necessarily avoid moving data back and forth memory device, because you still need to propagate the data across the memory channel. But what it does is allow you to avoid the cache hierarchy. So in case your application does not benefit from the cache hierarchy because, for example, it does not have enough data locality, you don't need to pay for the energy and latency cost of going through that cache hierarchy if you have some computation control in the memory controller. Another idea is to add the data inside the memory DIMM. So you're going to see examples from Samsung as well that propose some similar architectures like this, where they use those DIMMs called LR DIMMs that have a buffer die, a buffer inside the PCB itself, and they are going to add some computation inside that buffer in the DIMM itself. Or we can move the computation to the memory chips inside the DIMM in a 2D form factor. And again, you're going to see examples here from industry that propose solutions for such architectures. So before I talk about the proper architectures themselves, it's important to highlight that all of those have different trade-offs. It does not come from free processing near memory solutions. And those trade-offs stems from the fact mostly that we are currently designing logic separate from compute over the years. This means that the manufacturing process for logic and the manufacturing process for compute are completely disjoint and optimized for different metrics. Compute is heavily optimized for speed of the transistors, while your memory is heavily optimized for storage density. And as you can see, if you try to design one type of compute with one type of device with the other manufacturing process, you're going to end up with subpar metrics in some dimension of your design. So this is very important to take into account when designing processing near memory architectures in particular. So for example, if we are assuming a 3D stack chip like HMC or a HBM architecture, usually we have some space in the logic die of the 3D stack chip. Just as I recall, those chips are organized as memory DRAM chips, and in the base or in the first layer of those many DRAM layers, you have a CMOS layer that is there for some control and also some PHY interconnects to the above DRAM chip themselves. So Tri-Works have used some of the free space that are available in this logic die to implement computation. However, that space is not for you to do crazy stuff. It's not the memory manufacturer is giving you a free pass to design process memory. That logic die is there to move several of the maintenance operations that the memory controller does in the CPU side to closer to the DRAM chip itself. So there is already some logic sitting there that is occupying space. So the amount of logic that is, let's say, free for you to do computation is quite limited if you don't want to enlarge the logic die. You might want to enlarge the logic die, but then what you're going to have is that you're going to have a design that is not symmetric anymore, which is not necessarily ideal. So this is just some numbers from the era of HMC, where per DRAM vault, which you can think about as a channel, there was around 4.4 millimeters square available of a space for you to put some simple logic. And if you think about, for example, the space that would take you to implement out-of-order execution engine, you might see that this is not enough. So it's very unlikely that you're going to see a processing near memory solution with a very heavy-duty type of processor, like an out-of-order execution engine. At the same time, there is a problem with power dissipation, right? Your logic line is from your 3D stack DRAM chip is already designed with some TTP in mind, so you only have so much power that you can dissipate without changing the power supply for that particular DRAM chip for your compute, which also going to impact the type and the speed of the logic that you can implement over there. Second problem, and this is particular for 3D stack chips, but not only for 3D stack chips, this also have problems for 2D stack chips, is that memory chips usually use passive thermal dissipation mechanisms to take out of this heat out of the circuit to the environment, right? So you don't buy a DRAM DIMM and put a heatsink on top of the DRAM DIMM, right? You can do that if you want, but it just adds cost, right? Primarily, the primary source of thermal dissipation that you're going to find for DRAM chips is passive. And this becomes even a bigger problem if you think about that 3D stack design, where the base die has a computation and the top layers have logic. So how you take out of the heat that's produced by that compute layer to the top of the circuitry and dissipate to the system, right? There are many works on 3D stack manufacturing where people propose different ways of dissipate heat into these stack architectures via myriad of different solutions. For example, you might have a thermal layer in between the memory layers and the compute layers that are designed with some particular materials that can dissipate power. But this is just one of example. But you as a designer need to take into account how much heat that circuit that you're designing inside the memory is also generating. And the third problem, and maybe the most significant one that I mentioned earlier already, is that it's very challenging to manufacture logic using the DRAM manufacturing process, because the DRAM manufacturing process is not tailored for high-speed transistors. And we're going to see this directly impacting the clock frequency of some of the architectures from industry that I'm going to show up later on. Question? So you mean in manufacturing DRAM using logic? Because it goes back to back, right? So if you want to design DRAM using logic, you are going to have a DRAM chip that is less dense, so it stores less. Sorry, it will be fast, but you cannot store as many bits inside that particular chip. And you have to recall that this is a business, right? And the primary business of memory is to sell you gigabits, bits per dollar, right? So they want to maximize their margin by packing as many bits as possible in a piece of silicon. So this is why there are technologies like embedded DRAM that are there that uses CMOS logic to design DRAM chips. They are often used as a fourth layer of caches in high-speed processors, like Intel, for example, has a line of processors that uses these embedded DRAM chips in the SoC as a cache, but you can only cope with some few gigabits of storage for that particular DRAM chip using CMOS logic. So that is the trade-off that you need to pay basically. And there are some prior works. This is very old work actually, but illustrates the point. In this work here, they actually try to do exactly this. They take the DRAM manufacturing process, they manufacture logic using it, and vice versa. And they see that the transistor is slows down by around 21%. Again, this is a very old paper, but the problem is still the same because basically you don't have the capability of having high-speed transistors. There is another problem that is kind of hidden in this third challenge here, which is the number of metal layers that are available for you to round your chip or to round the interconnect in your chip when you're designing memory and processors. So historically, basically, as many metal layers that you have in your design, the more costly your VLSI process is going to be. So you want to minimize that. You want to have fewer metal layers as possible. And historically, DRAM usually uses 3 to 5 at most metal layers for its development, while processors require way more metal layers in the hundreds of metal layers because they have more interconnects. So you need to round those interconnects across the gate using those many metal layers. And if you go to a memory manufacturer and tell this memory manufacturer, please give me 1 extra metal layer because I need to route my pin logic to memory, they're just probably going to tell you that you're crazy because that metal layer costs millions of dollars. So that is yet another challenge. Routing VLSI of the VLSI circuit that you designed for the processing near memory circuitry is very complicated. So basically, you need to take into account all of those metrics while you're designing your processing near memory chip. So it does not necessarily come for free. And you're going to see how this impacts some of the designs from industry later on throughout this talk. Okay, so over this talk, I'm going to mention, and Onur already mentioned those works, 3 different ways of you designing processing near memory architectures. So since processing near memory architectures is just logic plus memory, this is not much different than how you would come about designing any logic in your computer architecture class. So basically, you can design logic in 3 different ways. You can have general purpose programmable cores, right, in order or for the cores. In our case here, in the context of processing near memory, we are going to have mostly in order cores. Again, because having out of order cores inside the memory itself would require you to have modify the power supply change for the particular memory device, would create thermal dissipation problems and would not be as fast as we discussed earlier. You can also have fixed functional units. Think about accelerators, or in your case here, you're going to see a lot of multiply and accumulate units being designed targeting a given application, this application being transformers. Or you can have reconfigurable architecture. So you can have pin coupled with things as FPGAs or cross-grain reconfigurable arrays. And towards across this talk here, I'm going to discuss both works from academia and industry that design processing near memory solutions following each one of those 3 different designing principles. It starts with general purpose cores. So Onur already mentioned the Tesseract paper that we designed targeting graph processing architectures. And even though the Tesseract work was designed having in mind graph processing, what you have in the very end, in the logic layer of the 3D stack chip, is WIMP in order cores. And since those in order cores takes they does not take a lot of space inside the logic die, and you can dissipate, they don't also take so much power, so you can dissipate that power quite easily. You can have many of those in order cores inside that free space that I mentioned in the logic layer of the 3D stack chip, and the others of hundreds. So even though those pin cores are fairly wimpy and simple and run at lower clock frequencies than your autofault core, we can see the system here as a many core system where we have hundreds of simple in-order cores that can use to distribute the work concurrently for a given task. So basically, by using application level parallelism or thread level parallelism, you can overcome the fact that those processors are fairly slow. And you're going to see a similar case for the industry solution for processing near memory architectures. So Onur briefly mentioned this architecture here. This is the UpMem pin architecture from a French company, and was released in 2019. And this was the very first commercially available processing near memory architectures. You can go about and buy their chip or rent time in their Amazon server for you to run your data-centric architecture into those systems. So I'm going to briefly talk about this architecture. This is not a 3D architecture. This is a 2D based processing near memory architecture, which follows a accelerator-centric type of model. So here we are not going to replace your memory DIMMs with UpMem DIMMs. We are going to enhance your system with both your regular DIMMs for memory and your UpMem DIMMs for computation. So following what I mentioned as an accelerator model. So this also can be seen as a loosely coupled accelerator. It's similar to how you couple a GPU to your system, right? You have your GPU with own memory and its own compute capabilities, and eventually you need to offload the code from your host CPU to your GPU and trigger the execution. So the model is quite similar over here. And as I mentioned, this quite resembles the GPU computation. So in terms of the system organization, this is just a pictorial example from the patent that the UpMem company initially released. As you can see here, we have the main SoC, the processor, which is going to be used to trigger computation. And this SoC is connected via the regular DIMM protocol with many DRAM DIMMs. And inside each one of those DRAM DIMMs, you have a regular DRAM bank, here MA, and some wimpy processor with some scratchpad memory, which is used for to store working data. This is just yet another view of the same system. So here we have your host CPU, your regular main memory, and the pin-enabled main memory with the pin chips that I initially mentioned earlier. And inside each one of these pin chips, what you have is, as I mentioned, some 64 megabytes of DRAM bank, which is called MRAM or a memory RAM, and a simple in-order core RISC style processor together with some SRAM memory designed for either as a instruction cache or scratchpad memory. The processor interface with the DRAM banks using a DMA engine. And inside each one of the pin chips, you can have 8 of those DRAM banks coupled with these processors, which are called DPUs. And inside a single DRAM rank in a DIMM, you can have 8 of those DRAM chips. And if you have a 2-rank type of DIMM, you can have twice, right? So 16 DRAM chips. So this is just a view of what you would buy or what you rent from UpMem if you want to use their UpMem pin system. It's not, I'm not doing marketing for UpMem. It's just for academic purpose for you to see what they actually have. So here they have your regular CPU. This is the motherboard, right? You have your regular DRAM DIMMs, but you also have your pin-enabled memory that can do computation. So inside each one of those DRAM banks, as I mentioned, what you have is some DRAM banks and some in other cores. So let's look very quickly at the core itself on the inside the pin chip. And what you have inside the pin chip is some interface, just to interface with the host processor. You have your 64 megabytes of DRAM bank, which is also a DMA engine, which the processor is going to use to move data from the DRAM banks into the working RAM, which is 64 kilobyte SRAM. And then you have a 14-stage pipeline in other pipeline that uses a RISC like ISA that is going to be used to do computation. So as I mentioned earlier, now you're going to start seeing those design challenges being reflected here in the design of the UpMem system. One of the first one is the fact that though that pipeline is fairly simple, if you ever took a computer architecture class, it's likely that you recognize a pipeline like this. Also, the clock frequency of these processors is fairly low. So these processors run around up to 425 megahertz. In comparison, any of our laptops here are running at 2.5 gigahertz, right? And this is a direct impact or a direct influence of the fact that this processor here is designed using a DRAM manufacturing process. These processors are also fine-grained multi-threaded, and you can have up to 24 hardware threaded executed in a GPU. And the 14 pipeline stages that I mentioned are just classic in other pipeline stages from fetch, arithmetic execution, and dispatch. So the UpMem system keep saying is a RISC-like or is similar to RISC instruction set architecture, because it's not necessarily RISC. They have their own instruction set. It's a 32-bit instruction set, and they also have a complete SDK, including compilers and runtime systems designed for you to run your C++ or application, compile that application, and offload it to the UpMem pin system. So this is just some more lectures that we have been conducting in the UpMem. And once it was initially released, the UpMem architecture, we got our hands on it, and we start trying to understand what this architecture is good for. And we're trying to benchmark and see what are the benefits and the drawbacks of such architecture. And Juan, which was a postdoc and a senior researcher in our group for a long time, he conducted a lot of work on first trying to understand what was the key characteristics of this real pin architecture, and also start writing applications for this UpMem pin architecture to showcase its benefits. So our first work was this benchmark suite called PRIM, which was published in IEEE Access, and where we created this benchmark suite with different workloads from various domains, and each one of those workloads are designed to stress different properties of the UpMem pin architecture. This benchmark suite is open source and available here in our GitHub repository, and many works outside Safari as well have used the PRIM benchmark suite as a benchmark suite to understand and also propose optimizations for this real UpMem pin architecture. So if you want to learn more, you're invited to check Juan's lecture on the PRIM benchmark suite. So as I mentioned, initially, once we got our hands on the UpMem pin architecture, our first instinct was to benchmark and try to understand the architecture using the PRIM benchmark suite. But once we understood how we could, what are the benefits of that architecture and its drawbacks, and how you would program the UpMem pin architecture, we start implementing different applications, partly more complex applications to this UpMem pin architecture. So we did, for example, studies on machine learning training for this architecture, where we propose some optimizations to mitigate some of the drawbacks of the architecture itself. For example, I didn't mention here, since the core type is fairly simple, the architecture is mostly targeting integer operations. So if you want to do float point operations and double precision operations in this upmapping architecture, you can, but those operations are actually simulated in software. So they are very low throughput when you're trying to do float point computation. Also, if you want to do high precision multiplication or division, you're going to end up with subpar throughput from this architecture. Again, all of this coming from the fact that the architecture itself is fairly simple. So there are ways of come about and mitigate these issues. And in this work, for example, we propose some quantization and high precision data formats so that we could train classic machine learning workloads in this architecture efficiently. So there are also other works later on in the workshop part of this workshop tutorial. Christina is going to talk about some of the work that she's been conducting on implementing some of the complex workloads in the upmapping system. She's not going to talk about this one in particular, but she did some work on sparse matrix vector multiplications. I also did some work on porting transcendental functions to the upmapping system, implementing homomorphic encryption primitives over here. It's just like a list of the type of workloads that you can accelerate using this upmapping architecture. So you can also do some reinforcement learning, and recently we did some distributed stochastic descended algorithms in the upmapping system, which are used for neural network training. Okay, this is the work that Christina is actually going to talk about in the very end of the workshop, which is her work on implementing graph neural networks in the upmapping architecture itself. This, I'm going to skip this in the interest of time. So this is just to give an overview of a general purpose processing near memory architecture that is highly programmable. I listed all of those works here, not to brag about the work that we do in Safari or anything like that, but to give a sense of the range of what this architecture is capable of. Since this architecture is programmable and is general purpose, you can take whatever application that you have that might be memory bound, write C-like code, compile this C-like code, and deploy it in this upmapping architecture and see if you have performance benefits or not, depending on your implementation. So is there any question related to the upmapping architecture? Okay, if not, let's move to fixed functional units, right? So what is the drawback of implementing general programmable pin architectures, right? The drawback is that you're not using the few amount of real estate that you have inside the memory device at its full extent, right? So for example, here is a plot from one of the papers that Onur mentioned that we did together with Google for consumer workloads. And then the x-axis here, we have several of the consumer workloads from Google that we analyzed in that paper, have Chromebook browsing, video playback and capture from, in that time was Hangouts, now it's Meet, and YouTube, and also some TensorFlow mobile over there. And we understood that some of the functions in those kernels were heavily bottlenecked by memory, so we decided to offload it to PIM. Then the question is, what type of PIM, right? So in this paper, we designed two types of PIM cores. One is general purpose in other cores, here called PIM core, and the other one is fixed functional unit accelerator. So you design one accelerator per function that you want to offload to the system. And as you could expect, if you specialize your hardware to the application that you're trying to accelerate, we can better use that area real estate and extract more performance out of the pin system. So by co-designing the hardware and the software as expected, because this is not different on how you would come about of designing any other type of accelerator, other than the fact that you are nearby the memory, you can extract more performance compared to just using general programmable cores. And as a general guideline, the way that you come about on doing hardware software co-design for processing memory is you take your application, you try to understand if your application is bottlenecked by data or not. So we profile this application, and later on in the tutorial and workshop, I'm going to talk about how we can do this application profiling more easily. But basically, you want to understand, is my application bottlenecked by data? How much is bottlenecked by data in terms of performance and energy? And what are the hardware requirements for this particular application that I want to potentially accelerate in pin? Then you go after you understand fully your application or kernel, you go about doing your hardware software co-design, taking into considerations those hardware constraints that I mentioned early on in the processing near memory design for pin system. Then you run your simulations. I'm going to talk about infrastructure for processing near memory research later on, but you can implement or you can use the simulator that we develop in Safari. You can use Gen 5. You can use your analytical simulator, whatever you prefer, to extract performance and energy metrics for your pin architecture. Here I'm going to showcase, say two, but I'm going to actually showcase only one case for this hardware software co-design, which actually Onur already mentioned. One good example is the work that again we did with Google for the Google Edge TPU neural network models. So basically, Merali and I went to do an internship at Google, and then we start trying to understand their neural network models that they are running at the time in the Google Edge TPU accelerator. At the time, they were mostly concerned about 24 different neural network models that were used across different products for Google themselves. And all of those models were running in the same accelerator, the Google Edge TPU. However, after doing a lot of profiling, we understood that the Google Edge TPU accelerator was fairly underutilized because of the different properties of the different layers and the different models that were running inside this single accelerator. So the first insight that we did from our analysis is that metrics that heavily influence hardware design for machine learning accelerator, like parameter footprint, which is going to dictate how much on-chip buffer you need in your neural network hardware accelerator, or reuse that you can have across the execution of your, this is for inference, the inference for your neural network model was significantly varied across the different models that the Google Edge TPU accelerator needed to execute. And even inside a single model, those parameters were varying. So there was diversity across the different models as expected, because they were running CNNs and RNNs. At the time, RNNs was still a thing. I don't know if this is still a thing because it became transformers over the time. But anyway, they were running models that are known to be compute intensive and models that are known to be memory intensive in the same hardware, and so that the heterogeneity is expected. But even in the same, for example, compute intensive model used, we are seeing significant variance for those parameters that heavily impact the hardware design of your accelerator. So as Onur mentioned earlier, our solution to this problem was heterogeneity. We are architects, we love heterogeneity because it tends to improve system performance energy and fairly use better the area that you might have, the area budget that you might have for your design, right? So to do that, we create these three families of accelerators. Two of them were placed near the logic layer of 3D stack chip, and another one was a compute-centric one. So Onur already mentioned this. I'm not going to explain again. I'm just going to highlight that for all of this work, you need support from the software, so that doing the neural network inference, we can understand the type of layer that you're going to be executed in that particular execution, by having the characteristics of the input layer, and doing the execution on software, we could dictate which layer would move to each part of the accelerator. And we saw during the execution that you might think, oh, now you have two accelerators, right? You execute one layer here, one layer there. What about they communicate? We saw doing our analysis that not very often those layers need to communicate data from one layer to the other, or move from one. In the case, the difficult part was moving from the data-centric accelerator that is in memory, communicating that data with the compute-centric accelerator, which was in the host. Very few amount of times that actually needed to happen. So once the accelerator is centralized in one place, or the layer is centralized in a particular accelerator, the layer would mostly reside inside that accelerator, which is great. So data movement, we are not increasing data movement by having this heterogeneity in the software. So we did all of this analysis for Mensa in simulation, and we saw that by doing so, we can reduce the area cost of the Google HTTP accelerator, while reducing or improving energy consumption and improving inference throughput. In the paper, we also have results for inference latency and for many more of those 24 models, but the plot is very long, so it doesn't make sense to include in a 4x per slide, 16:9. So this is just one example from academia, how you can come about doing a fixed functional unit design for a processor memory architecture. Let's see now examples from industry, right? So industry is catching up on processing near memory solutions, particularly because of a push from the application domain. And since 2021, if I'm not mistaken, memory companies have started proposing processor near memory architectures for varying domains. So this is just an excerpt from Samsung announcement from their initially called film DRAM architecture functioning memory, which uses 3D stacked memory devices for multiply and accumulate units. So this is going to be a little bit different from what we mentioned so far, because we are treating these 3D stacked chips before us. We have memory layers, and then we are going to use this logic die in the bottom of the memory layers to put computation. Samsung did something a little bit different in their design of this film DRAM architecture, which is nice, and they can do because they are Samsung, they are designing the memory. So they took another trade-off. They were like, we are going to cut some of our capacity from our memory device. So you want to keep the same form factor, because Samsung, we want to make sure that my HBM device is still JEDEC compatible. So I could theoretically place this new chip in any HBM capable system. So I don't need to change the interface. To do that, they need to keep the same form factor of the design. So what they decided to do is, let's take out some of the space that you are using for DRAM chips or DRAM banks inside my 3D chip itself, and let's replace that with some compute layers, some compute capabilities. So now we actually have layers of memory. So we have those 4 top layers there, which is regular HBM layers for storing computation. And we have some layers in the middle that are layers that have both DRAM and some multiply and accumulate engines. By doing so, the trade-off here is that this chip is less dense, is not as dense as the regular HBM chip. So if I'm not mistaken, they went from a 8 GB chip to a 6 GB chip. Don't quote me this number, maybe it's from 8 to 4, but I'm fairly sure that's actually 6. So basically, by enabling computation and keeping the same form factor, they had to have this cut on the density of the device, which allowed them to make the device being with the same form factor as the previous HBM2. So this architecture was designed mostly for, at the time, transformers were still catching up. So it was not for transformers, but for regular CNNs at the time. So the pipeline of the pin units that are in that core die is basically some vector multiplier for float point, followed up by adder, because they want to do multiply and accumulate, right? And this reflects on the instruction set architecture of the architecture. You can see this chip can only do very few operations, but those operations are very key for neural network inference. This is just a picture of the die that they have manufactured. So they actually manufactured this. I don't know if you can buy. I don't work for Samsung, but maybe you can call someone and ask. But they usually have demos in industry-based conference. They show around the chip itself, so it exists, at least in theory or in practice. Like they say, it's very hard to say, right? The chip is this size, and then they say that okay, something is inside there, so you believe that is there. It's not a monkey move things around. So this was the initial realization of their film DRAM architecture, and since then they actually created a product line out of this processing near memory architecture. And at the same time, they keep changing the name of the chip. Initially it was film DRAM, eventually moved to HBM film, and the last time was Aquabolt, but it might change again. But what is important here is that they have diversified this product line to encompass different use cases. So in this conference called Hot Chip, which is basically where industry people goes to showcase their product, 2 years ago, they show up 3 new architectures. They are processing near memory architectures targeting generative AI. As you might know, and if you don't know, you're going to know, because there are so many neural network transformer-based talks in this conference. So eventually you're going to learn about the fact that transformers are memory bound in the generative step. So this is just a profiling from their own paper where they show that GenV dominates the generative latency, and this GenV operation is heavily memory intensive. So to solve this issue, Samsung proposed three different processing near memory architectures. So the first one couples that HBM pin architecture that I just mentioned with AMD GPUs in a server, and they show up that by doing so, they can significantly improve performance for transformers compared to just using the AMD GPUs by themselves to do the inference. So yeah, it's 2 times more efficient than the GPU only baseline. The second approach targets generative AI on the edge. So let's say that you want to do something with Apple Intelligence, whatever that's called. Probably that's not going to use Samsung chips, but I don't know, whatever the same version of things are called in Samsung phones. So you want to do inference on the edge, right? So they also propose a solution. The idea here is pretty much the same. The only difference is the memory device is going to change. Now you're not going to use costly 3D stack chips for that. We are going to use what your phones use, low power DDR devices, coupled with some P units shared across different DRAM banks. Again, targeting neural network inference for generative AI. And as you can see, the hardware is fairly similar to the one for the HBM1, right? It's some float point multiplying and adder engine targeting the GenV portion of the transformer inference. And again, they show up some performance numbers and where they see that they can significantly improve performance, and also potentially more important for edge devices significantly reduce energy consumption as well when using run inference on the edge. Third, let's say that you want to scale out the system. A known problem for, especially for training for generative AI, is that it becomes quickly not only a memory bound problem, but also a capacity bound problem. So you need to have many memory devices so that your TV cache fits inside the memory space of your chip, right? So they also propose a solution having that in mind. Here they are using CXL expander, someone asked CXL earlier, to either add computation at the CXL controller itself, or add the memory chip inside the CXL memory device. They were a bit, they were not so descriptive on the design over here, but they show some initially results showing that using this CXL processing near memory architecture, they can significantly improve energy efficiency and throughput compared to just having multiple GPUs in the system. So this is from Samsung. This was a big market for them, but it's not only Samsung. Other memory manufacturers are also working on their own solutions for processing near memory systems. And this is from SK Hynix, another memory manufacturer, where they propose these AIM chips. And again, the idea is fairly similar. They will also want to accelerate neural network inference. The main difference here is that they are not using, they are not using 3D stack chips, neither low power DDR chips. They are using GDDR6 chips, which are usually used for graphics. The architecture, since they are targeting similar kernel, is fairly similar. So they have a multiplier and an adder tree, and accumulation and activation function engines inside the DRAM bank, near the DRAM bank, and also some supplementary buffers to move data around across those different processing elements inside the DRAM chip itself. So as Samsung, SK Hynix also have a product line out of this AIM architecture. So this is the original one. They were simpler. The new one is just called AIM-X. It's just an improvement on top of this initial 2022 architecture. So this concludes the fixed functional units pin solutions. Is there any question related to that? Okay, if not, let's talk about very briefly reconfigurable architectures, right? So what we cover so far is we can implement team processing near memory using programmable cores, the up-mapping architecture, fixed functional units, those approaches from Samsung and SK Hynix. But you can also do something with FPGAs, for example. So in this FPGA from here, for example, in this FPGA board, you can use some coherence interconnects, like in this case was the CAP2 interconnects to connect the FPGA together, couple it together with, in this case was a IBM Power 9 PC. And you can use this combined system to implement some particular computation in the FPGA's side and offload that to a close by high bandwidth memory. So we did that for in this narrow work. I'm not going to get into detail here, but basically we took weather modeling, which is quite big in Switzerland, and we implement or offload that to this combined FPGA plus IBM processor system. And since the HBM, the FPGA has tightly connections to HBM chips, we could accelerate the architecture. So academia also has something similar related to FPGAs. So this is another approach from Samsung. It's called IXDIM, where they have these DRAM DIMMs here. Those, as I mentioned, are LR DIMM chips, where we have a buffer inside the DIMM itself. And inside this buffer, oops, wait, yes, they can implement some sort of reconfigurability because it's basically some FPGA logic sitting there. They use this reconfigurability in this initial IXDIM paper to accelerate reconfigurable recommendation systems, but it's not, since this is reconfigurable, you can do whatever you want. So other works have shown that you can use this IXDIM architecture, for example, to do things like sparse length sum or database operation using this IXDIM architecture. So we have more lectures with more details on all of those. And I just want to show up, this is just the same slide from Onur, and it's fairly old. But I just want to highlight that when I started my PhD 6 years ago on processing in memory architectures, this didn't exist, and people actually were like, why you're going to do work on this area which is way too futuristic to come up with, actually. So it was 6 years ago, thinking about the processing memory chip was something that we were discussing for the next 10-15 years. But now processing memory chips are real, they are there, they are in the market. This is just a landscape for major players, but there is a myriad of startups that are banking on processing near memory solutions to accelerate data critical applications. So we expect this to just boom more and more. Actually, last year I was in this industry conference called FMS in Santa Clara, and processing near memory was a big topic over there. One of the keynotes actually were talking about their solutions for their PIN solutions for a neural network inference. So we're expecting to see more and more of those real processing memory chips targeting the market as we progress, which is great for all of us, but especially for me because I need to find a job very soon. So that is very nice. So is there any question related to processing near memory? Hopefully that was clear. So in case if you want to do research on processing near memory architectures, what type of tools you are going to use, right? So if you have a fab, your life is simple. You just implement the chip and then you pay 2 billion or 2 million, I don't know how much is a chip, and then you run and you test. That's great. In case you are in academic solution or you just want to test your idea, I'm going to talk more about this later on. But we have come up with this simulator based on ZSIM and Ramulator called DAMUVSIM, which enables you to quickly prototype both programmable PIN systems, also as fixed functional unit PIN accelerators, and evaluate things as performance and energy of that particular accelerator versus regular CPU-based system. So the simulator is available online, and also there is a benchmark with that follows up with the simulator, which I'm going to discuss later on. It's not only from Safari. If you want to test the HBM PIN solution from Samsung, they have their own simulator available. It's called PIN Simulator, which is, if you type this on Google, you're going to find like 10 different approaches. But these slides are there. This is the official one from Samsung. And if you want to test things from the UpMem architecture and you don't want to pay the UpMem company to use the hardware, there is this excellent simulator called UPimulator that actually was awarded best paper in HPCA 2024, where you can actually use the write your application, deploy your application in the simulator, and also do modifications, architecture modifications to the simulator, hence to the hardware, to see if such architecture modifications would lead to performance. So if you want to conduct research on UpMem, this is an excellent starting point. And this is the paper that I just mentioned that best paper award. So this concludes the processing near memory solutions. Is there any questions related to this? So if not, I'm going to very briefly talk about processing near memory, probably using memory. Sure. You can. We did some initial analysis of the simulator. You can do some performance analysis out of the simulator that I'm info. It's not very. I hope no one from Samsung is there, but I hope it's not very well documented. So you might take some. The learning curve might be a little bit high for that particular simulator. It is heavily based on DRAM sim 3, I guess. So if you know DRAM sim simulator, you have better chances of like dig deeper and like figuring out the simulator. And there are more documentations in that one for sure. So, but yeah, it is. You can also measure performance out of the simulator. Any other question? Okay, so I'm going to talk briefly about processing using memory. Okay. Okay. So in the interest of time, I might speed up things a little bit. So bear with me, because I want for sure Mohammad to give his talk next, and also for us to have lunch. But this topic that I'm going to talk next is my favorite topic related to processing memory at all. One, because it's why my PhD is related to. memory chaining. This is very nice. Okay, so now you're going to use these operating principles to start doing computation. And you're going to start very simple. You're just going to start with moving the in the RAM row copy. So giving one source row. So the ones that are horizontal or vertical? So the what is vertical here is the sys amplifier. So this box here is a two back-to-back inverters connected together. Sorry? The vertical one, yeah, this box here.
No.
This one here?
Sub-row decoders.
This one here?
Yeah.
Okay. So this row decoder here is not just one big row decoder. It's a hierarchy. It's a hierarchy of row decoders, because if you have to design think about how many rows you have inside your DRAM chip that has 16 gigabytes of data, right? If you make the math, a lot of them. So what they do to minimize the cost of the hardware is to design a hierarchical row decoder. So there are many levels of decoding that happens, going from a chip to a bank to a subarray and to a MET. So this is basically a piece of this row decoder, or the other one, because it's hierarchy. So yeah, it's just yet another row decoder. Okay, so we are going to start with the in-DRAM computation. You're going to start fairly simple with in-DRAM row copy. So let's say that I want to copy the source row to the destination row without involving the CPU at all. So Onur already mentioned this. What we are going to do is a sequence of back-to-back activations. So the first activation it operates exactly as I mentioned in the background. The source row is brought to the local sys amplifier. Then, which is not possible, is a violation of the DRAM protocol, we activate another row, which is the destination row. This differential sys amplifier here is stronger than the capacitance on the bit line over there and in the DRAM cell, because they need to amplify the signal, right? So since this is a stronger circuit, the data that was previous latch and amplify overrides the data that is in the destination row, hence copying the source row to the destination row without involving the CPU at all. And as Onur mentioned, this is actually possible with some reliability aspects of it in real commodity off-the-shelf DRAM chips. Okay, this is fairly simple. Let's do a little bit something more complicated. Let's do a majority. So let's say that I have 3 rows, source 1, source 2, and source 3, and I want to compute the majority of 3 of all of the cells involved in all of the DRAM rows. So here the majority of blue, yellow, and blue should be blue. So I activate the main difference here is that I'm going to activate the 3 rows at the same time. So when I activate the 3 rows at the same time, those 3 DRAM cells simultaneously perturbate that local bit line that I mentioned earlier. And again, since this box here is a differential sense amplifier, this is going to pull up the voltage level to the majority of the voltage level stored in the 3 DRAM cells at once. So here in this case, this is going to pull up my voltage level to all blues. As you can see, this is a destructive operation. Since all of the DRAM cells are connected at the moment that I activate them, the data that is initially stored there is lost. So if I want to keep the data, I need to copy it first to another place. So by doing this, I can do majority of 3 operations. And as Onur mentioned earlier, in this paper that we presented in HPC, it's a summary of 2 papers. We can already do a subset of those operations in commodity off-the-shelf DRAM chips by violating DRAM timing parameters. I'm not going to get into this. The next thing is, okay, we do in DRAM copy, in DRAM majority. What if I want to do a in DRAM addition, right? So since I can compose different in DRAM triple activations at once or in a sequence, I can actually implement the adder. So let's say that I want to implement this rip carry adder here. using those triple row activations, right? What I do first is I take any header implementation. So here is a RIP carry header, and I convert this RIP carry header to majority not representation of the same circuitry using some equivalence, and I optimize the circuit as well. Why? Because what I'm fundamentally doing when I'm activating 3 DRAM rows at the same time is a majority of 3. So why would I stay in a Boolean representation, right? Now what is left for me to do to implement that in DRAM addition is traverse this graph node by node, issuing the triple row activations as needed. So I go to the first majority node here. It involves rows A, B, and carry in. I activate the 3 ones at the same time. It's going to be the majority of blue, blue, and yellow. It's going to be blue or 1. And then in this new row, this carry out row, I'm going to have 1, which is the result of the operation. Then I move to the next, the majority node, which activates A bar, so negated of A, B, and carry in, and which is going to be yellow, blue, and yellow, and it stores the data in the temporary row, which is going to be the majority of that. It's going to be yellow. I didn't mention not here, but Onur already mentioned that how we do not, right? So we take the output of one side of that back-to-back inverter and we route it back to the DRAM cell. So hence you have not operation. So in the commodity of the shelf DRAM chips, this is true. But we modify, here we are modifying the circuitry. So we actually reroute into the same. So finally, we go through the final majority node, which involves activating A, the negated previous majority output, and the other previous majority output is which is going to be a row carry out bar, temp, and A, which is going to be majority of yellow, yellow, and 1, and blue, which is yellow. So in the very end, I have one row full of carry outs, which is 1, and another row full of sum, which is going to be 0. And if I read this vertically, I'm going to have 1, 0, which is the addition of 1 plus 1, which is 2, exactly what I expected. I don't know if you notice, there are 2 things that are very important from this execution model here. First, this is bit 0. So I did the example here for 1 bit. So if I have 2 bits of data, I need to do this twice. If I have 3 bits of data, I need to do it 3 times, and then so on and so forth. If it's a multiplication, it's worse because the number of operations for multiplications scales quadratically with the bit precision. But if it's addition, I just go 1 bit at a time. Another thing that maybe is not clear from here is that I have a vector here with as many elements as DRAM columns, right? So everything here is blue or yellow. So I have as many elements as columns that I have in the DRAM subarray. But if the elements here, all of them are 1 bit each. So if I have elements that are 2 bits, those elements are going to be stacked. It was a question that was asked earlier. They are going to be stacked inside the same DRAM column. So let's say that this, as I mentioned here in the cout, I don't read this horizontally, right? I read 1, 0 vertically because the data needs to be vertically out so that I can propagate the carry that is generated from this majority gate to the other majority gate without changing anything on the local sense amplifier. So basically without connecting this guy to this guy over here. So this is 2 very important properties of this substrate. One is uses a vertical data layout for data, not a horizontal data layout. So you need to transpose the data if you want to keep both in the system. Second, this is bit serial. So the latency of your operation is going to heavily depend on the bit precision of the computation that you want to execute. This is not a question, yeah? Question? Yeah, yes. Wait. Maybe I get to. Yes. So basically, we have a work that studies different type of headers and modifying this approach so that we can improve performance. So there we check bit parallel headers as well. But the problem with bit parallel headers is that at some point you need to propagate, like the thing scales logarithmically, right? But eventually you need to move from one depth to another in the header tree, and that translates to inter-subarray data movements, which are cheaper than doing anything from the CPU, but it still requires you to go through row copies, and that incurs latencies. So depending on how deep that tree for a bit parallel header gets, that is going to directly impact the latency overhead that you're going to have for moving those propagate generate bits around in the substrate. In the rank, yes. You don't have to, but you operate. No, you can have everything operates in one rank actually, because the granularity is a rank. The minimum granularity that you can operate is in a DRAM rank, and then in this DRAM rank you have many DRAM chips. But all the DRAM chips are activated at once. Yes.
So for us to do parallelization, for example, to do two full ladders at the same time, we need to do one in the one run, and another on the another run.
We are going to get there. Yes, this is one way of doing that. There is another way of doing that. But here I'm just talking about the same header. Is the same header implemented in two different ways. One way is using bit serial rip carry header, and the other one is using a bit parallel, I don't know, conga stone header, something like that. So we evaluate. So this, what I just proposed here, is called SimDRAM. My papers have very similar names to each other, so it's hard sometimes. Where we implement 16 complex in-DRAM operations using that same approach that I mentioned, including multiplication, division, ReLU operations, and we use that to accelerate 7 real-world applications like databases and bitwise neural networks. And Onur already summarized the results, so I'm not going to go through them. We see good throughput and energy savings, and also end-to-end performance depending on the number of DRAM banks that you use for computation. Because what is very nice about this model that I just mentioned here is that you can have as much compute throughput as DRAM banks that you have inside a DRAM rank. And every single DRAM column becomes one independent bit parallel. You can see it as a SIMD lane, right? So in a single DRAM subarray, you have 64,000 SIMD lanes. You have 64 DRAM subarrays in a bank, 16 banks in a DRAM chip. You can have 2 ranks, and you can have as many channels as you want as well in the system. So this keeps scaling up. So you can scale up that computation as you scale the capacity of your system, which is fairly nice, right? And hence you can, in the end, even though the bit serial latency in the individual bit serial latency might be high, you might the throughput of the system is very large, so you can overcome that, hopefully. So this is the work that presents in ASPLOS SimDRAM. So Onur already mentioned this as well. This is very nice, but this can cause some problems. For example, as I mentioned, the granularity is a DRAM row, right? 65,000 elements. How often do you write a loop that you go for I equals to 0 equals less than 65,000? You don't do that, right? And it's not only about that you don't write the loop like that. If the loop is not a multiple of that, you're going to end up in underutilization as well, because you need to fill all of that DRAM column at once, all of that DRAM row at once, because all of that DRAM row is going to be activated during the computation. So you cannot partially activate the row. You activate everything or nothing. And that's the problem. Then this also generates some other problems related to programmability, because you can only, I don't know if you saw, pay attention to this in the presentation, but what you are doing basically is, in the example of the addition, right? I had two vectors and I generated a third vector as output. What if I have one vector and I want to generate a scalar operand? So I want to reduce. There is no connections across columns, so I cannot do that reduction. I cannot move data vertically, right, across the different columns. And also programming the system is fairly complicated because you need to do a lot of data mapping, data allocation, and alignment so that things fit correctly. So we solved this in MIM-DRAM. I'm going to skip this and go here in the interest of time. Onur already presented this. The main idea here is to use fine-grained DRAM access for activation, for processing DRAM computation. And fine-grained DRAM basically segments that global word line that I mentioned in the background with some isolation transistors so that I can access individual DRAM mats inside the DRAM subarray. And now I can expand this to many DRAM subarrays in the system. Here is not in scale, but actually what we have inside a single DRAM subarray across virtually across the DRAM chips is that you have around 128 of these DRAM mats. So if you only use, if you don't do the segmentation, if you only use one mat for the process using DRAM computation, your utilization is going to be 1/128, which is very bad. It's very low. But if you can use the computation across, control those 128 DRAM mats individually across the DRAM subarray, you can make much better use of the substrate. Onur, again, I already mentioned this. For a single DRAM operation, I can allocate as many mats as I need for computation. And if I have any other DRAM mat that is free, which is likely the case, I can use those DRAM mats to do another operation. And now is the case that we have two additions operating completely independent from each other doing the computation, because the control is segmented now. So I don't need to, I can control them individually. Yes, so there are some latches, like I'm not showing the full design here. We need some latches to latch that address, so it propagates the decoder and everything. So each one of those mats here, they actually have an isolation transistor and a latch to latch the address. So the address can be fed to this particular local decoder. And also the channel is shared, right? So the control in the memory controller becomes a bit more complicated, and we have the design for that in the paper, because I need to tell the DRAM chip the bus is the common address bus is shared in a given time, activate this mat, latch that data, and then the next cycle, now it's time to activate the other match that has this address with this data. So there are some it's complicated, but at the same time it works like a dance. It's very nice. It becomes like a very classic VLW machine, you know, like from the 90s, where you have so many control signals that you need to communicate and make sure that everything goes around at the same time. It's very similar to that. You can see this machine as something like that. Another nice thing is that you can move the pieces of data across the different DRAM mats using that global sys amplifier that is shared across the different DRAM mats in the DRAM subarray as well, hence enabling reduction. And as Onur mentioned, and this is just a feature of Destiny, I don't know why this happened, but it is the case. The number of SIMD lanes that you end up having in a DRAM mat is on par with the SIMD lanes that you have in AVX 512 processors. So we can just map one AVX instruction, of course, with the appropriate changes to it, to a process using DRAM operation that we would execute inside the DRAM met. So there is a design in the hardware and the software. I just want to briefly mention this. So someone asked about the address, right? So there is this row decoder latch here is exactly for that purpose, because I need to latch the address until that row is activated in that other match. So I can send another request to a completely different match at the same, not at the same time, right? But concurrently. So on the software level, what is interesting is that to be quite frank, when I started doing this MIM-DRAM work, I really like compilers, and I really want to dig into LLVM a little bit. So it was my excuse to go through the LLVM code base and learn a little bit. So that's the part that I like the most about this work. For us to map codes to the substrate, we use the LLVM auto-vectorization engine that takes a loop in your application and auto-vectorize that. So we changed that auto-vectorization engine because it uses a cost model to dictate the best vector width for a particular vector instruction. But here we don't need a cost model. The cost model basically takes into account things as a register spilling, for example. But there's no register spilling here. There's no register. Everything is DRAM cells. So you don't need to take into account all of those. So remove that, and also vectorize to fit as many DRAM mats at once for a single process using DRAM operation, because that simplifies the control. Also, you have some metadata embedded to the process using DRAM instructions, so that in the hardware side, we can allocate accordingly the appropriate DRAM mats during the execution. So I know, for example, which two processes using DRAM operations can execute at the same time, or which two needs to execute it one after the other because there is dependence. And finally, we generate instructions to the binary to port to the substrate. So we evaluate MIM-DRAM in the G5 simulator. I'm not going to talk about this. And we saw significant performance improvement and throughput improvement as well. Onur already summarized the result. I'm not going to go through them again. So we are running late. As I said that I was going to be quick, and I was not quick. But if you allow me 5 more minutes, I would conclude this part. All of this is very nice, very good. However, there is still at least 3 more problems with the substrate. So the first one is, I'm keep talking about bit serial computation, right? And usually you write like integer, blah, blah, array, and then when you do that, you're not necessarily thinking if your data needs 32 bits to be represented. You're just like, the data structure that I have available for me is an integer, I go for it. But since this is a bit serial machine, if I'm not using that, if you tell the engine, do a 32-bit computation, but actually you're only storing 4, and I'm going to have to go through those 32 bits one by one, even though I'm just computing something relevant for the first 4 bits. The remaining is useless in a bit serial machine. So one of this problem is that if you naively employ a bit serial execution model from machines that are used to be bit parallel, you're going to end up having a high latency execution for the bit serial computation, because you're computing over, this is called narrow values that have a lot of zeros or a lot of ones that are not helping on the representation of the data. So this is just an example of what I just mentioned. This is 12 workloads, and in the x-axis, those are box plots on the minimal bit precision that you might need to fit the data for that particular application. And as you can see, very rarely you actually use 32 bits. You need 32 bits to represent the particular computation that you want to have. In fact, most of the time, you have a lot of those narrow values here that you could completely ignore when you're doing this process using DRAM computation. This is not a new thing. There are a lot of works that design register files, for example, or compression schemes that are leveraging this fact to improve cache capacity, for example, or improve energy in the register files. But we are going to use this old observation in the context of bit serial processing in memory computation. So yeah, so in the case here, you could reduce the bit precision significantly, hence improve performance. So the second problem here is we are doing this computation across many this in DRAM computation, right? Activation pre-charge, or activation pre-charge to implement that adder. So this is just another view of the same adder that I mentioned earlier. It's just rotated. And if you have two DRAM subarrays, you can use those two DRAM subarrays to compute the data that's for that particular adder, right? However, there is a smarter way of doing so. You don't need to serialize the computation, because the only moment in time that, let's say that you have 2 bits, the only moment in time that the data from those 2 bits needs to interact with each other is the moment that I propagate the carry. So before the carry propagation, I can execute everything in parallel. And once the moment of the carry propagation happens, I move the carry to the appropriate place and I continue my life. So this significantly saves time, reducing the latency of doing those in DRAM activations and in DRAM triple activations and row copies for the particular operation. So you are not so much tied to a throughput execution anymore if you reduce the latency of an individual operation, for example. And the third point is, even if you do all of these that I just mentioned, still, if you want to do something like multiplication at high precision, like 32 or 64 bits, just the sheer fact that the latency scales quadratically with the computation is going to incur a lot of latency penalty for the substrate. However, there are other data representation formats. For example, this is quite an old one that is called redundant binary representation, where we use 2 bits to represent one particular data element instead of 1. And by doing this particular representations, data representation, you have nice features. For example, carry does not need to propagate across many levels of your order, for example. And also the operation latency is independent of the data precision. So once the idea here is, if you have to do something that is very high precision and very costly in this substrate, just move out from this regular binary representation, go to another data representation where such operation does not is not impacted by the bit precision of the computation. So by combining these 3 ideas, we have proposed this work called Proteus, which is I love 3-step stuff. It's a 3-step framework that first have different implementations of different bit serial and the bit parallel processing using DRAM operations to do computation, and each one of them have different trade-offs in terms of latency and the bit precision. Also, engine that doing the execution of the application tries to identify what is the minimum number of bits that I need to use to represent a given input vector, so that I can adjust my process using my bit serial execution or my bit pair execution of the processing using the RAM operation to just that amount of bits. So I don't compute over sequence of 1s and 0s that are not used from computation. And also we have a selection unit here that figure out all of those different trade-offs and plus the information related to the data that you want to compute on top of, and selects the best suitable processing using DRAM implementation to do the computation in DRAM. So by doing so, we can significantly improve performance compared to that SIM-DRAM model that I mentioned earlier, and also improve energy efficiency. So this is this work, Proteus. And in the interest of time, I'm going to take questions. Is there any question? Yes. So in the initial SIM-DRAM work was just with the summation. in this work here in the Proteus, we also investigated other implementations to see what was the difference in latency and trade-offs and throughput, basically. So it's not only the classic one over there. Yes. Yes. The reliability. So in some of our papers, we have some analysis like that. And also that is very important is depending on how much you violate, you end up with different operations. And like, for example, for the copy, if I recall correctly, for the first activate, you don't violate, because there are two, right? For the first activate, you don't violate the timing. But for the second one, you aggressively violate the timing. But if you want to do triple active, like Boolean operations, you need to quickly violate the timing between the for both of the activations. So yeah, there are some, we did some initial analysis of related to that, and it's not in this paper, it's in those DSN and HPCA papers. Okay, is there any other question? Otherwise, I think I'm going to skip for lunch. So this was processing using DRAM. We are going to talk about flash still when you come back from lunch. So maybe our schedule is going to be a little bit shifted, but it's very nice to give a perspective that this is not only DRAM based, like you can also do this in other dominant memory technology as well. So I see you at 2 right after lunch. Hopefully there is still food for us. Okay. Thank you. You, you just to read out?
You don't know, but
Thank you. Unfortunately, no. I was going to introduce Onur, and then I realized that he was going to make a joke. Right. Thank you.
working, I can. But there's no obstacle. It's minus 1.5 for sure. And then late this time, I think it comes to DSP.
And you don't have problems with live stream.
That's major. The other room, like, around here.
Yeah, I'm going to set up correctly.
Can we ask someone? You're gonna trade it on here. Air quality is not very good. I don't think this is working. Okay, they can do it.
What is restriction?
That work?
The audio.
Do you have an audio problem?
I don't think I have problem. So
I don't suddenly do it.
okay, that's cool.
So you have an
I have no problem.
Okay, great. If there's anything that can help.
Faz. Yeah. Then I got used to it. I need to move the microphone. Can you check it? So you know how to operate a computer.
Yes, so everything's okay. Perfect. So why do I hear myself? Okay. Welcome back, everyone. Hope you had a good lunch. I still hear myself. Okay. Not from there. Hello, hello, hello. It stopped. I think it was my phone. Sorry. Welcome back. The desserts were very good. The coffee was not so good. Now you're going to start with the workshop part of this mixed workshop tutorial. And we are going to have a series of very nice invited talks. So the first one is by Hamid. He received his bachelor's degree in computer engineering from the Shiraz University in 2019, and his master's in computer science and architecture from Shahid. I'm going to botch that. University in November 2021. So in August 2022, he joined the chair as researcher assistant, and he works on high-level compiler frameworks. Like every time that I say this, I butcher the name MMLAR, and optimization for data and computation mapping onto highly heterogeneous systems with mainstream CPUs, FPGAs, SRAM, DRAMs, and emerging NVMEs and accelerators. So today he's going to talk about one work that is also a talk here in ASPLOS, right? Sometimes later during the week on Thursday. So feel free to join the talk over there as well. And feel free to ask questions over here. So thank you so much and welcome. And sorry, please install this. Perfect. Okay.
So, hello everyone. Thank you, Geraldo, for the introduction. My name is Hamid Farzaneh, and I'm a PhD student at TU Dresden. And today I want to give a summary of our works around improving the programmability of compute in memory and compute near memory systems. So, as we heard in the talks before, there has been a lot of proposals for in-memory computing systems that try to address the memorable problem of the von Neumann architecture. But at the same time, it has been a very common practice to categorize these systems into two separate groups, as we heard from Geraldo and Professor Mutlu. They were using the terms processing, using memory and processing near memory. We also use the same similar term in our works, compute near memory and compute in memory, compute near memory for processing near memory and compute in memory for processing using memory. To recap again, the idea behind compute near memory is to let's try to put some small processing elements close to where the data that is being stored, and then we program these processing elements in order to apply the computation on the data that is being stored in the way that we want it to be. So architectures similar to such as Samsung Film DRAM and OpMem are based on this idea. On the other hand, in compute in memory, we try to use the memory itself or do some small modification within the memory to enable to do some computation on the data. Architectures such as techniques such as Ambit or devices such as memory stores for doing matrix vector multiplication or contrastable memories for doing similarity search-based operations have been used based on this idea. Although these devices are very different in what do they do and how they actually perform the operations, but from a very abstract view, we can see some similarities in the operations that are being offloaded, meaning a lot of these systems share actually the operation that they can, the abstract operation that they can accelerate. And also, in the end, we are dealing with the memory. And because of that, from also an abstract view, in these two separate groups, the compute in memory and compute near memory, the programming models of these systems are somewhat similar. And at the same time, there hasn't been an established programming methodology that can address all of these systems. To address this issue, we designed Cinnamon. It's a compiler framework based on another compiler infrastructure called MLIR. It has a hierarchical flow similar to the architecture that you can see, similar to the figure that you can see at the bottom. And it accepts applications in different abstractions, such as linalg for linear algebra kernels, torch for torch kernels, and TOSA for tensor operations. And throughout its flow, it can do domain-specific or device-specific optimizations, and ultimately generate optimized code for the selected target. I said that the Cinnamon is based on MLIR. In MLIR, we have some building blocks that are reusable for different purposes. And you can see these rectangles in the middle that are these building blocks. In MLIR, they are called a dialect. A dialect is a group of operations for a specific purpose, and also it includes optimization related to that group. For instance, here we have affine. Affine is a dialect for representing loops. The loop operation. It includes loop operations, and also it includes loop optimizations as well. Or in here we have linear, that stands for linear, that is for representing linear algebra operations, and also the optimizations related to that. So in Cinnamon, we use the same idea of the dialects for the CNM and CIM purposes. And we implement a set of dialects, and we added to the base MLIR, the blue ones that you see here, and we can divide it into 3 different stages. At the first stage, we have CINM dialect. That includes the operations that are ultimately going to be offloaded on our target. It covers operations like gem, gemv, histogram, and similarity search operation or bulk bitwise operations. And also it includes optimizations that are going to be performed on these specific abstract operations. So far, nothing very device related, just abstract operations. At the second stage, we have CNM and CIM dialects. These are used for implementing the abstract programming models for the underlying category. And ultimately, in the last stage, we have the device-specific dialects, such as opmem for opmem and memory store, and other architectures as well. For instance, specifically in opmem dialect, we have the device-specific operations that are necessary for copying data between the different levels of the memory. So how does it work? Imagine that we want to design a matrix multiplication for our opmem machine. Geraldo talked a lot about how the opmem works, but implementing such an application, if you want to implement such an application for opmem, you will be dealing with a code like this. You have to use their own C interface, and you have to manually address the different memory and how the interactions between the hardware threads are going to work, and how to copy data between the host and the device, and so on. But if you want to use the highest level of Cinnamon, you would, since the gem operation is already available at the CINM abstraction, at the CINM dialect, you can express the same kernel by using just a single line. And you would just pass it the input operands, and then you would use the result of it for the rest of the application. The mapping of this application, mapping of this kernel onto the device is going to be handled by the compiler throughout its flow. The only thing that you need to do is you need to specify, for instance, how many DPUs do I have, or how many tasklets between per each DPU do I have, and how many DIMMs do I have, and that's it. The code generation is going to be done by the compiler itself. This one? Yeah.
Instead of writing all of that full.
Yeah. So no. That was an example. That was one representation of an in a specific language. This is a anything. Yeah, but things that are supported by the compiler, right? Yeah. Well, the compiler, for instance, supports torture script as the current version that we have. You can also use the other, I think, whatever that that can be converted to these representations. We can support throughout another flow, and there are a bunch of front ends that can convert your input application, for instance, one language, and to these representations. Yeah. So now that example was for upmem. If now imagine that I want to use I want to generate the same kernel, same gem kernel. Now this time for instance, a memory store crossbar. For the upmem, as we saw earlier in the flow, if I want to generate code for upmem, I have to go through the CINM to CNM to upmem. But now this time, if I want to generate code for memory store, I have to go CINM, CIM, then memory store. Meaning for both cases, the starting point is the same. It is the CINM, which translates to same input code, same input application can be used for both targets. But the only difference is the parameters that you pass to the compiler to like do the tiling and generate code for your target, and that's it. So in our evaluation, we showed that by using the enable optimization, the device-specific and domain-specific optimizations of Cinnamon, we were able to generate code that are faster than the baseline implementation and manual designs. And this was for the upmem target, and for the memory store crossbar, we were able to reproduce the results of the previous software frameworks for that target. Yeah. So the optimization that we are implementing, I was going to discuss it during the final presentation, but in summary, the optimization that we have implemented are figure out what is the best access pattern for different kernels, for instance, to reduce the number of, for instance, DMA accesses, to read and write accesses, and also if based on how many DPUs, how many testers do I have inside the DPU, I need to select the correct size of the DMA request, so it would be the least amount of contention between the tasklets. That's the sort. But this sort of things, this is somewhere between the domain-specific and device-specific optimization. Yeah. So I will be presenting Cinnamon in a bit more detail on Thursday at 2:30. Yeah. Hope to see you there. So so far, for the targets that I've discussed, the memory store crossbar, and for upmem, what we wanted to implement, what we wanted to offload was a matrix vector multiplication. And in the input application, I was also explicitly expressing a gem operation, meaning there was somewhat a one-to-one mapping between what it was expressed in the input application and what my hardware was ultimately going to accelerate, a gem operation. But this is not always as easy in all of the targets. So for instance, in the case of content-accessible memories, my device can do a similarity search operation. But in a typical program, like a torture script, this is not, you don't have a similarity search, explicit similarity search operation that can be like, that is going to be executed. But instead, the way that you would express a similarity search operation is like the figure on the top right, meaning it would be similarity search operation is going to expressed as a sequence, as a flow of operations, such as, for instance, a matrix transpose followed by a matmul followed by a top K. But the gist of this, the summary of this is, previously, so in some cases, in easy cases, I have a one-to-one mapping in the input application, the input language, and what my hardware can do. but sometimes there is not an explicit one-to-one mapping, and it can get really easily really complicated as you have like different in the same category. You have different types. For instance, in CAMs, we have TCAM, MCAM, and ACAM, and they do the search in different ways, and they are trade-offs of accuracy and performance between them. And also the similarity search operation is not a simple single operation, similarly to GEM, but instead you have different matrix in a similarity search operation. And these was the sort of things that we wanted to, and now this time address. So the order that I'm presenting the works here are in the exact order that in which we implemented them, meaning we started with Cinnamon 2 years ago, and then we did the C4 CAM, and which I'm going to talk about. But the order in which they were published was not exactly the same. So this time we extended Cinnamon to address these sort of issues. In summary, was not having a one-to-one mapping in the input application, the input language, and what my hardware can do. And now we extended Cinnamon, and since we were targeting specifically CAMs, we called it C4 CAM, a compiler for CAMs. And from abstract, the flow is somewhat similar, but with some modifications. And the main parts are a new dialect for supporting CAMs were added, and also for addressing the input language problem, we extended the CINM, the highest level, this time. So how does it work? Imagine that we wanted to express the similarity search using a flow of operations. At first, what the compiler does is it captures the operations that might be accelerated, might be able to be accelerated on the target. And then it does a set of pattern matchings to figure out, is this actually supported by the target? What the target specification that I give to the compiler? It checks if this actually can be offloaded, and also if I remove these operations, if I replace them with the new things, I shouldn't break the whole application, because some of the operations that you are capturing, they might have some side effects on the other parts of the application. And if you remove them, if you replace them with something else, it might break it. So it shouldn't. And then the rest of it is similar to other flows, meaning you do domain-specific and device-specific optimizations based on your target, and ultimately you generate the codes. And in evaluations, we show that we were able to reproduce the previous implementations of the applications for CAMs, and we showed that also using the optimization that was enabled that was enabled in C4 CAM, you could use the compiler as a mean to do design space exploration, meaning figuring out what is the best configuration of that hardware for my application. So far, I talked in the hardware about the hardware that I talked about. Their mapping process of figuring out what is the best way to execute this kernel on my hardware was somewhat easy. Meaning, for instance, imagine that you have a GEM kernel, big GEM kernel, and first, in order to fit it on on an OpMem machine, because OpMem is you have a small processing elements called DPUs. You have to break down the application into smaller pieces that you can put on the small DPUs. So, but because of the constraints that were implemented by the hardware, this mapping process was somewhat simple. What I mean is, since there is no direct communication, there is no direct mean to communicate between the DPUs, it doesn't matter that much in which order that I actually execute the operations. Meaning, it doesn't matter. Should I execute this batch of kernel, this batch of small gems, or should I execute another batch? It doesn't matter, because you cannot communicate between the DPUs. So these constraints were actually enabling us to do this mapping process somewhat simple. But the mapping of the input application to the target is not as easy. For instance, imagine, so far I talked about memory store crossbars for doing matrix vector multiplication. But there is also another way to do bulk bitwise operation in this device. The technique is called the scouting logic, and the way that it works is you modify the sense amplifier, and then whenever you want to do an operation, you enable multiple rows, or 2 rows, and then when you are reading the results, reading the output of that sense amplifier, the result is already there, meaning the result of performing an operation between 2 inputs that are stored into two different rows. So now you are dealing with the hardware that works in a very, very specific way. So and for instance, if I have some data on this row and I have another data on this row, I cannot when I want to do some operation, I enable this row, and then read the result here. But at the same time, I cannot do another operation on this row and this row, because that just doesn't work, right? And also, the inputs should be aligned, meaning the data that you want to do, for instance, and on the data, on some data that is here, the other data should already be here and not here, meaning they should be on the same columns. So this sort of constraint that is forced by the hardware is going to make the mapping very complex very easily, and what you need to do ultimately is to figure out what is the for instance, if I have this kernel on the left, which is a bit weaving kernel used in databases, and it includes just a bunch of bulk bitwise operations on some operands, on some data, you have to figure out what is the best placement of the operand and the operations on my memory based on these constraints. And this is the sort of things that we try to address in our work Sherlock. And finally, with the output of this placement and the schedule is going to be a bunch of instructions that are going to execute the same kernel. And what we did was we came up with a method that the input would be a graph representation of the application, and then figure out a cluster of operands and operations that can be properly placed on the memory, and then with minimum interference with each other, and it can and try to maximize the parallelization of the operations. And ultimately, we show that compared to the naive implementation of a kernel on this sort of hardware, it can perform much better. And also, we enabled some optimizations that transforms the input application in some way that improves the performance, but also with some accuracy loss. Yeah. So in conclusion, the in-memory computing systems have shown promising results to address the data communication problem. But at the same time, for these novel systems to go mainstream, we have to address the programmability and accessibility issues of them. And frameworks and compilers such as Cinnamon or its extensions are a step in that direction. Thank you. Yeah. Okay. So the thing is, it depends. This is a very general question, and it depends on a lot of variables. So, for instance, if I imagine that I have a gem kernel, a huge gem kernel, the input is defined, but the way that you would partition the space of this gem kernel is going to be translate into how much data am I going to communicate between the host and the device. And properly doing the partitioning of the kernel is going to affect your data communication. And these are the sort of things that are being addressed in Cinnamon. So, but in general, for there are other ways that you can change the that there are other optimization that also can impact the data communication. Like if I do if I rewrite the operation with new things, I can also change how the data, how much data is going to be transferred. Yeah. Yes. Yeah. Yeah. Thank you. Yeah. From the house. Yeah. Definitely. Yeah. 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 So the constraint that we had in OpMem, for instance, where if we look at in the hierarchy, do I have it? Yeah. So this is where OpMem were implemented, and the constraint that we had from the hardware should be implemented in here. But higher level shouldn't care about if I have I might have a mean to communicate between the DPUs, for instance, or I might not have. So this level, the CNM level, for instance, can at this level of implementation, and also we have mentioned this in our paper, you can have actually architecture. It can support architecture that enable communication between the hierarchies. And the way that we have represented is, let's imagine I have I have an imaginary shared memory between the DPUs, for instance, between the processing elements, and you can communicate using this shared memory. In the OpMem case, this memory doesn't exist. Yeah. So we can support such a hardware, such a target in Cinema. Yeah. Is there an optimal tile size? It depends on the input application. Yeah, so we have been working on another thing called the cost model that tries to predict, like, if I have such a kernel, what would be the execution time, and what would be the execution time. And throughout our experiments, we figure out there is somewhat a range of optimal tile sizes. Like we know that some tile sizes doesn't make any sense, but there is a range of optimal tile sizes that for most applications would make sense. Yeah. Sure. It is. Yeah, yeah. No, it uses the real hardware. Yeah. So you have to add that support at the moment. Yeah. You mentioned the hardware about memory. Yeah. So we were using we were using simulator from our collaborators, but unfortunately that part they haven't open sourced it. Yeah. CNN and C. So this is no, you are. Yeah. Yeah, so you are not forced to use like everything, like you selectively. I think so. Yeah, in the future, probably we would have a heterogeneous system that you would have to use like a combination because, like for instance, opmem is not good at doing gem, but it is good at doing other stuff. Like at the same time, memory store you can only do it. It is very good at doing like gems, so it makes sense to have a combination.
Actually, so we are starting seeing the literature works that mix P, P bronze using memory and near memory. There is a paper for transformers called TransLib, TransPin, that actually does exactly that. They do the map part of the gem on like DRAM like substrate that I just mentioned, and then the reduction step using a process near memory solution. So it's a combination of both. And if I'm not mistaken, there is one of the industry-based solutions that add logic for like process near memory approach that I mentioned. They also do some sort of support of in-DRAM row operations in the sense that I mentioned. Similar, not exactly the same, but similar to what I mentioned earlier. So, yes, those things started developing quite disjoint, but slowly they are like merging into a single thing. So thank you very much for the speaker. Sorry for the context switch. Ah, you change the presentation? Sorry, there is a on-demand update. Ah, perfect. I use this Safari. I'm not good. So how does okay, I will try. Mohammad, can I use your photo again? Okay, so the next presentation is from Theoharis. Sorry, sorry, my Greek. He is currently a student at the National Technical University of Athens, in the Department of Electrical and Computer Engineering, where he now completes his master thesis. So he's going to hopefully start a PhD soon. His academic interest lies in circuit design and simulations with a focus on analog and mixed signal circuits and their applications. So his master thesis, which I believe is part of the work that he's going to present here, specifies leverage DRAM circuitry to analyze the summation operations and investigation of its speed up. So feel free to start. Oh, this is your microphone. Okay. You just click it over here. You can just put it like here. Oh, thank you. It should stay. And then is you okay?
Yes. Hello, everyone. My name is Theoharis Diamandidis, and I'm a current student in the School of Electrical and Computer Engineer in the National Technical University of Athens. my work focused on harnessing processing memory techniques for accelerating some operations in FPGA and DRAM architectures. Firstly, I would like to make a summary of this work. The problem we face nowadays is that modern systems are processor-centric. This means that we have a repeated data movement between the CPU and memory. When we want to process some data, we have to call them from memory. And this causes reduced speed for this processing, and especially for some operations. Our goal in this work was to accelerate some operations by utilizing the computing memory approach, and especially computation using memory. The key idea was to utilize the simple logical operations such as AND or NOT operations in order to move toward more complex functions like the full adder. The key was to develop an M-bit full adder on actual commercial DRAM hardware. And in order to do so, we adjusted the timing parameters that and how many idle cycles we sent between two different commands in the DRAM. And in order to achieve the summation of n-bit operands, we used FPGA and DRAM coprocessing in order to achieve high accuracy. The key result was that we managed to achieve an acceleration by a factor of 12 for the addition of many operands. Here's an outline of my work. First, we will present some of the background that was already mentioned. We present the limitations that we faced during our work and the methodology we followed in order to solve these problems. We will present our experiments and the results we observed. And finally, we will make conclusions about those results. So let's start with the background. Here we see the DRAM module that our computers use nowadays. It consists of different DRAM chips that is shown with the black box. Those DRAM chips also consist of several banks that connect to the chip input-output in order to communicate with our CPU. Each bank consists of the sense amplifiers and the subarray, and the subarray itself consists of different DRAM cells. In the same row, we call them the DRAM row, and is activated by the word line. This DRAM row is connected to the sense amplifiers via the bit line, which is a parasitic, which also holds some parasitic capacitance. So the DRAM cell consists of an access transistor, a capacitor, and is connected with a bit line. In order to activate the access transistor, we send a signal of supply voltage in the word line. The access transistor then comes into triode region and operates as a resistor, and connects the cell capacitor with a parasitic capacitance of the bit line. This allows charge flow from the one capacitor to the parasitic capacitance, depending on the initial values. The bit line is always when we do not violate the timing parameters in half of supply voltage, and when the cell capacitor is charged in supply voltage, then charge flows from the capacitor to the bit line. Because the parasitic capacitance of the bit line is much larger than the cell capacitance, we observe a slight increase in the voltage of the bit line. We'll now present the background of the logical operations we used in order to achieve the full adder. As we also mentioned, we use the bulk data copy, which allows us to copy one row to another using the sub-amplifiers. Basically, as we explained, is we activate one row, and by violating some parameters and activating another row, we manage to copy the source to the destination. We also use the frac operations. This means that in DRAM modules, the cells in the DRAM cell, the capacitors in the DRAM cells do not hold charge which is only ground or supply voltage, and we can also store a charge that is in between of these values. We focus on storing a voltage of half of supply voltage. We also use the many row activation and the majority of 3 in order to perform the logical gates and OR. The contribution of these works relies on that we offer a simulation in order to observe the timing parameters we need to violate, and we use the schematic level in the cadence suite in the technology of TSMC 90 nanometers in order to see how much time the sense amplifier needs in order to charge the bit lines. We also developed an M-bit full adders where M is 1 to 16. And we also offer a proof of concept in order to achieve a summation of many operands using FPGA and DRAM coprocessing. We evaluated the success rate and the accelerations we get for multiple scenarios. So the problems we faced is that we have some physical level limitations. This means that bit transfer between 2 different columns we cannot use bit transfer between 2 different columns. And this means that we cannot use shifting and propagation of the carry out in the summation. Moreover, in the same subarray, we cannot use the NOT operation without changing the hardware. In order to overcome these problems, we used column merge architectures where both the numbers and their bits are stored in the same bit line. And also, in some steps, we must calculate the complementary values in order to achieve the full adder, as we will explain later. In architectural level, logical operations for the same full adder cannot be conducted in parallel. And we cannot also use many operands because the subarray has a limited rows. In this case, was 512. Lastly, the results of each operations, for example, when we use and or overrides all the rows in the groups of rows that are activated simultaneously. In order to overcome this problem, we use bit serial arithmetic and utilization, and we utilized as many groups of rows as possible. For the summary of many operands, we use DRAM and FPGA coprocessing, and we executed each operation in different group of rows. We will now present the methodology we follow in order to complete the full adder. Firstly, we estimated the timing parameters of the sense amplifier for the charging and discharging the bit lines on the simulation level. And this is the schematic we followed. It's basically consists of 2 NOT gates that are connected in positive feedback. We identified the boundaries of the subarray that we will perform the logical operations. Because different subarrays are separated by the sense amplifiers. We explored simultaneously opening rows in order to make a majority of 3 operations. And lastly, we evaluated the M-bit full adder with n operands. We used design space exploration for the evaluation of the M-bit full adder with n operands. and we used different banks, utilized the random subarrays in each banks, and experimented with the timing parameters and the patterns we used to add. Our goal was to maintain both high success rate and also achieve acceleration for the sum of these operands. But this was a trade-off between these two goals, because when we tried to reduce the timing violations, we watched that there was a reduction in the success rate. In order to build this Mbit full adder, we used the DRAM bender that was developed by Ataberk Olgun and it offered us fine-grained control over the DRAM commands, the timing parameters, and the temperature. Basically, they developed their memory controller on the FPGA that controlled the DRAM module that was connected there. We will now present the experiments that we conducted and the results we got. Firstly, we're estimating the timing parameters of the sense amplifier for charging and discharging the bit lines. With the capacitors, we symbolize the parasitic capacitance of the bit line, which is almost 10 times larger than the cell capacitance. This transistor, the inverters have positive feedback, and this is basically the sense amplifier. The transistor MP1 and MN3 are used for the sense amplifier to go in power down mode. When enable is high, then enable B is low, and basically the sense amplifier is cut off the supply voltage and does not operate. The inverters have a positive feedback, which means that a slightly difference between the two terminals that the capacitors are connected drives the voltage to VDD or ground. Another interesting circuit that is used is the pre-charge and equalization circuit. The transistor MN5 and MN6 are used to pre-charge the bit lines at the voltage which is symbolized with V pre, and is used in half of the supply voltage. The transistor MN4 is used for the stabilization, and when there is a slightly difference in the voltage at the drains of MN6 and MN5, then current flows from MN4, which equalizes the two voltages and stabilizes the circuit at half of the VDD supply. The result we get is that in order for the sense amplifiers to charge the bit lines, there is a delay of 4.2 nanoseconds. We also conducted a Monte Carlo analysis that was about both mismatch and process variations. And we can see that for different sense amplifiers, they may be 1.5 nanosecond delay for them to charge the bit lines. So not all sense amplifiers will behave with the same way for certain timing violations, and this is why we don't have the highest success rate. In the next step, we identified the boundaries of the subarray, where we will perform the logical operations. In order to do so, we stored zeros in the whole memory, and we chose a random row R1, and store all ones in this row. Then we perform a row copy operations between R1 and R2, where R2 is another row that we will loop and read the data from R2. If the data are the same, but we have a percentage above 70%, this means that these two rows are in the same subarray, and we can perform logical operations between those two rows. We found that there are 512 rows in a subarray and 32 subarrays in each bank. In the next step, we explored simultaneously opening rows for the majority three operations. We noticed that by activating two rows in quick succession, we have simultaneously activated activation of many rows. For example, when we activate row A, and then with a timing violation, we send a precharge command. And after that, with again a timing violation, we activate another row. Then many other rows are activated also in the same subarray. By writing a pattern and then reading the whole subarray, if we read the same pattern, then we know that these rows were activated simultaneously. However, we couldn't spot groups of rows that can perform majority of three because there were no three rows activated simultaneously. We watched 2, 4, 8, and 60 rows that can be activated. So in the next step, we implemented the 1-bit full adder. We used this schematic of the full adder, and in order to overcome the limitation, we store all the operands in the same bit line and their complementary values. We also calculated the number of the logical gates which needed, and they are nine a group of 4 rows. There are 4 rows because we will add 2 bits every time. Then we decided which group of rows will be used as these gates in the subarray, and store the results of the logical operation in another row in order to maintain the initial values. This is an example of what we did. For example, if we want to make an OR gate between A and B bar, we have these operands in the rows 251 to 260. And we also have stored all ones and all zeros in order to know which operation we will perform. With the storage of all ones, we perform OR operation, and with the storage of 0, we perform AND operation. So we're in the same subarray, when we can now choose the group of 4 rows in order to perform a logical operation. Here we will show an OR gate. We row copy A to row 12, B bar to row 13, and all ones in the row 15. In the row 14, we use the frac operation because, as we said, we couldn't activate only 3 rows simultaneously, and we have to neutralize the 4th row. So we used the frac operation we mentioned in order to store the half of the supply voltage. We performed the row copy by using 30 memory cycles because we row copied 3 rows. The frac operations, we performed it 3 times in order to achieve the value as close as half of the supply voltage. And this cost us 12 memory cycles. And lastly, we performed the logical OR by utilizing this sequence of commands. We activate, precharge, activate. We left 2 idle commands, and then again precharge and 2 idle commands. In total, we used 50 memory cycles for just a single logical gate. In the next step, we saw the results override all the rows, and as we can see, if you take the OR gate, it's the same in all the rows. And now we can copy one of those, the result in one of these rows to the next group of rows that will be used. In the next step, we evaluated the M-bit full adder. In order to achieve this M-bit full adder, we noticed that the say out will be used as input in the next bits for this full adder. So we will have to compute the complementary values of the dotted gates. This means that we now don't need 9 group of rows, but we have to use 15 group of rows in total. So the total memory cycles that we used in order to add M-bit, two operands with M-bit is given by this equation. The alternative solution that was mentioned is this, that can compute the full adder with just 4 group of rows. It is 4 because we have to calculate also the negated value of the first majority of 3. But we decided to proceed with the other schematic because we wanted to test DSP applications and used Boolean algebra to perform the full adder. So the valuation of the M-bit full adder showed that the success rate is reduced from 80% when we add 2 operands with 1 bit to below 30% when these operands are with 16 bits. Moreover, this this figure shows the rows we need in order to add the 2 operands with different bit length. From this figure, we can see that there's a linear equation, obviously, and the bit length that the operands may hold is no more than 128 bits. In the next step, we evaluated the full adder with n operands, and we wanted to check how many operands in the same bit line can we store with different bit length. The equation is given by this, the number of n is equal to the number of operands, and is given by solving this equation. We can see that for 8-bit operands, we cannot add more than 54 operands in the same subarray. So we decided to evaluate a more specific, a more special case of an 8-bit full adder. In this figure, we show how many memory cycles we need to add different 8-bit operands. And we can see in order to add 32 8-bit operands, we need more than 45,000 cycles. This is why we propose the DRAM FPGA coprocessing architecture. So what we basically do is read from the DRAM by 8 bits per row and store them in a ping-pong pipeline in the deliver. In the deliver is basically a buffer that will write it as rows and read it as columns. The one in the deliver is first written. The first one is written, and then we proceed to write the second in the deliver. The result is the result chosen is chosen from a MUX and is accumulated to produce the summation. This happens in the FPGA. The speed up we gain is given by these equations, where, for example, when we want to add 10,000 numbers, then gives this number. The small n gives the numbers that we store in each bit line, and B is the number of the bits per operand. In this case, it is 8 bits. We can see that for 1,000 numbers, we have no speed up gain. And as we increase the operands that we want to add, the acceleration is increased. However, the more the numbers we store in the bit line does not mean that we also have more acceleration. For example, for 10,000 numbers, if we store 8 numbers in each bit line, gives a better acceleration from storing 16 or 32 number in each bit line. The conclusion is that for small numbers, for a small number of operands, there is no acceleration if we use the summation in the DRAM. And for this to make sense, we have to use the summation for larger amount of operands. We also see that increasing the operands in DRAM does not offer acceleration in every case. For example, in the 10,000 operands. And however, we have the high error rates. We saw that in order to sum 16-bit operands, we have below 30% success rate. However, we run a simulation with MATLAB where we chose random operands and produced bit flips in each operand that was random. While summing these operands many times, we saw that the actual sum has a less than 3% difference from the sum that gives the proposed solution. In the future work, we have to explore the multiplication operator in order to achieve DSP applications. For example, a matrix multiplication with 100 rows and 100 columns is one good case which can be implemented. I would like to express my thanks to Professor Onur Mutlu for giving me the opportunity to work with the infrastructure they developed, and to the PhD candidate Olgun Ataberk. Thanks for your attention. Any questions? Oh. Okay.
So what type of DDR?
DDR4.
DDR4?
Hmm?
And how many chips?
One.
One chip.
Yes. So we good and
No, but like I guess now the hard work definitely is to write down the algorithms and like the codes for the embedder and start the testing, and then like just like replicating the same test many times to make sure that you're
we use the for loop. We stored the random numbers and we performed the sum operation. And then we saw the results we get and make a summation of the success rate. That's why it was so low.
Yeah, my point was that like now you already did the hard work, and then it's just like replicating to more DRAM chips to make sure that to have error bars and make sure that like you maybe for a particular DRAM chip is this bad, maybe for another DRAM chip from another die revision.
We only had one DDR4 chip. We didn't have. I was working from my country, yes, remote, and I couldn't change the DDR4 chip.
Just bother with my. And I have another question. The test rate, how was it defined? Do you remember the metric?
Yes. For example, we stored two different random numbers. We calculated the sum using high-level language like C++. I used C++. And then I perform the logical operation with the DRAM commands. And then I went bit to bit and saw which bits were flipped.
Okay.
And then I counted that there were. Yes.
I think that's very promising. Like it's like there is still a lot of work to be done for sure. But it shows that you can do something, right? It's not just like generating random data, because in the end, for low bit precision, as you show, you can actually have quite high
Yes, yes. Yes, if the bit flips were random, and if the bit flips in the DRAM module does not happen because of some reason, because of the different cell capacitance and completely random, then yes, we may have good success rate if we sum many operands.
Thank you very much. Thank you very much again. So you have another speaker now. So Christian is a software engineer with 8 years of experience in emerging computing architectures and low-level performance optimizations. Since 2023, he has been working with Huawei Research Center in Poland, focused on the implement of processing memory architectures and optimizations using just-in-time compilers. Oh, that's very cool. Prior to this, Christian spent 6 years at Intel, where he specialized in computer runtimes and work on features such as bootable command lists. That's very nice. So take the stage, please.
So my name is Christian. Now I work in heterogeneous memory software lab. And together with my teammates, we investigated UPMEM because we recently got really interested in PIM and also processing near memory because of many problems that can be solved, especially memory band problems. And today you can see 3 people from my group here. You can see Maciek, Tadek, and Paweł. And without further ado, let's start, and I'll tell you what problems we faced when we are developing kernels for UPMEM. So you've already got good explanation what really is UPMEM. The only thing I would like to point out is that the system that UPMEM sells is a 2-socket system, and we've got 1 channel with DRAM and 5 channels with UPMEM on each socket. Right. And in this presentation, we'll focus on simple things, addition and multiplication, and we'll see what's the baseline performance of those operations and how much we can speed them up. So here we've got simple code snippet. It's like you can see really simple loop where we either perform reading from WRAM, then we add a scalar or multiply by a scalar, and then write the result back. And here are the results. As you can see, there is a big difference for int32 multiplication, but it's something we expected because it's not natively supported. Actually, it's performed by just shift and add. So I'll talk about it later. But what really brings concern is the performance gap between the int8 addition and int8 multiplication. It's really big, like 64%. And we started to wonder why, right? It should be because we saw in instruction set of the UPMEM that there is an operation for multiplying. It should only take 1 cycle. It's here, mul SL SL. So we take lower part of one 32-bit array register and the lower part of the other register, and we should get the result in 1 cycle. So what really happened? So we, once again, we got this code, we disassemble it, and we have seen the problem. This call here, mul SE3. That's the call to this int32 multiply and add. We also saw that there are some other problems with UPMEM compiler. Mainly loops are not being unrolled at all. And when we force unrolling with pragma unroll directive, sometimes it starts to unroll the loop so much we run out of instruction memory. Yes.
Do you think that is because the the RAM is so small.
Yes,
and
yes.
They don't want to unroll and like screw up stuff.
Yes, because this int32 operations, right? There's a lot of instruction because first they swap to get the bigger part in one register and the other in the other, and then they perform 32 mul steps, right? So if they unroll it like 10 times, there's not. Yeah, exactly. You can only hold like 4,000 instructions, right? So here's this sheet that I was telling you about. So as I said, first we swap to get the bigger one in R0, and we perform move steps. So basically, we shift one register right, then check if there is a one, and if so, we take the value from the other registers and shift it left. How much to the left on which step we are, right? Basic step. We wondered what happens. So we check with different n's, with different value of n in the loop, and of course all of those examples before were also compiled with O2 or O3. Actually, all of these results are from compilation with optimization O3, and we found out that the behavior of this code, the behavior of code generated, depends on n. For n smaller than 28, everything was fine. Function was inlined, a loop was unrolled, and correct instruction was used. When we went higher, up to 39, the function was no longer inlined. We saw that there was a call to the update function, the main function, but inside the update function, everything was fine. It was unrolled, and we had the correct instruction. But as we went higher with n, or used a variable, the function was still inlined, but there was no int8 multiplication. There was this call to mul se3, so the shift and add. And now let's talk about the optimizations we did for int8 and int32 multiplication. So for int8, for starsers, we just use correct instruction. As you can see, this already brought the performance from like 30 mega operations. Those are the results for a single DPU, from like 30 megaops up to 80. Then we added unrolling, and as you can see here, it went from like 80 to 130. And then we wondered, okay, but we are still loading it just by 1 byte. So what if we load the data by 4 bytes or 8 bytes? And as you can see there, here's the example for 4 bytes. So we are loading a 4-byte value, then multiplying the low part by scalar, then high part by scalar, and we're shifting 16 bits, and once again the same thing. For loading 8 bytes, it's basically the same. We just do it 2 times more. And as you can see, with loading 8 int8s and using correct instructions, we get more than 5 times speed up versus the baseline code generated by the compiler. Okay, so that was int8, and let's move on to int32. In int32, we wanted to replace the shift and add with our custom implementation based on int8 multiplication. So we divided the numbers into 4 parts, where x0 is the least significant part. And we just perform normal arithmetic multiplication. We skip over the terms higher than 2 to the 32 power because we only care about the result, 32-bit result, right? And this fast operation with unrolling, here we only could unroll 64 times. If we just left it at pragma unroll, we got the error, not enough DRAM. So that's why it's x64. We got almost 2 times speed up versus baseline int32. And basically, unrolling really helps a lot on this platform. Especially when we are doing not a lot of operations in the loop, because loop itself is pretty costly. So when we are doing like a single operation, then it's worth to unroll. And we can use the pragma unroll directive to force the compiler to unroll loops for us, so we don't need to do it manually. And here are some speedups for different operations. As you can see, for addition, we get like 2 times speedup, 100%. Not 2 times speedup, but we are 2 times faster than original. And let's revisit our numbers. So blue bars are the baseline numbers, and orange bars are the numbers we got after our optimizations. So as you can see now, multiplication of int8 is even faster than addition. Weird, right? And multiplication of int32s is still slower, but
Is it because of the
what?
Is it because of the unroll factor? Because int32 could also be int96 support. It should be
The addition is almost the same for int32 and int8, right? It's the same.
Yes, yes.
Yeah.
So that factor is coming from unrolling.
Unrolling, yes, yes. Because the same operation for addition is just for int8 and int32. 16 tasklets, yes. 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 If you have a smaller number, it will finish faster, right? Because it's doing bit shift, and if the number is 0, then it stops. Values, random values from the minimum up to the maximum, and we did 10 runs of that with 1 warm-up before getting the results. And but still, we got 2 times speed up over the baseline with int32 multiplication.
I like
Exactly.
So loop unrolling can move ISP, but so I wasn't expecting that much.
Me too, but that's I just explained to myself it's because the loops are pretty costly. Like it's 5 instructions and 1 instruction, right? If we are just doing 1 operation, but actually we are doing like 3 because load and store. But those will be like amortized by different tasks, right? So.
Yeah, I want to add something. I think I agree with intuition, because it's like it's what we actually observe in our works for compiler support stuff for the free benchmarks or as well, right? Because like this architecture, it's mostly compute bound, right? If you think about it, because arithmetic, okay, memory is cheap, but now compute is so costly because the frequency of the processor is so slow.
Yes, it
like,
completely inverts. Yes. Yes.
So like whatever you save, whatever instruction you can remove, it leads to this, which is a different way of thinking, right? Because like we usually tend to take it for granted, right?
Yes.
Like, what is 3 instructions in a processor out of all the processors
Yes,
that run at 5 gigahertz? It's nothing.
Yes, even like when developing kernels for it, I rewrote some of them to assembly just to get just less register usage, just less stack usage, because other instructions are there's a big difference. Yes, and now let's compare those results we got to the server grade CPU. So those results we saw earlier were for 1 DPU, and the whole system, we've got 20 DIMMs, each with like 8 banks on a chip, and 8 of those chips on a single rank, so 64, and we got 2 ranks, so 128 multiply by 20, yeah, 2560. And in blue bars, we've got like the base UPM performance. Orange ones are our improved performance, and red is Huawei's server grade processor, Kunpeng 920, with total of 128 cores. And as you can see, those results make it seem that UPM is a viable platform for performing computations. We even think that it's a good platform for AI workloads, albeit if we use integer quantization, right? Floating point operations are a lost cause on UPM. They are really slow, but perhaps new hardware may emerge or something. But for integer operations, it looks really good. As you can see, for int8 additions, we are faster 1.5 times, and we are up to 2.6, and integer 8 move completely out of the chart. One times one baseline up to 6.5 times faster than the CPU, and with int32 additions, we went from 5.2 times the speed to 10.4, and int32 multiplication is still not bad. It was even faster in baseline, but at 1.9 times, and we went up to 3.5 times the speed of the CPU server. And now let's switch gears a bit from simple operations to simple memory transfers. So first, let's talk about transferring data from host to PIM and vice versa. We'll focus on DPU prepare transfer and DPU push transfers, which are operations that basically perform scatter and gather, but I don't want to use that terminology because it's reserved for something else in UPM. But basically sending a part of a buffer, a different part of a buffer to each DPU. And there is one constraint that transfer size and symbol offset need to be a multiple of 8 bytes. And we get an error otherwise when we try to run the DPU push transfer if that's not the case for the buffers we prepared. And we need to put extra care if there is a reminder, like we've got a buffer which size is not a multiple of 8 bytes. So we need to line it up in order to send it to UPM. Maybe it's not a problem when we are sending it, but when we are reading it and if our buffer is small, we will write after it. So we'll perform data corruption. So it's an important thing to keep in mind. And transfers from MRAM to WRAM and from working RAM back to MRAM. We use those functions MRAM read and MRAM write. And here's only one caveat that will result in error, maybe two if we count the maximum transfer size, that the transfer size needs to be a multiple of 8 bytes, and it must be at most 2 kilobytes. And we found a problem when we were writing a kernel that when we were looking at results that something was off by a few bytes. And then we found out that this operation silently aligned down the address to 8 bytes. So we started to look more into documentation, and we found that there is MRead unaligned and MRAM write unaligned functions that will help us, but they required more than 300 instructions, and it was pretty costly. So we tried to just do it ourselves. And where is it used? Like in simple matrix vector multiplication, right? If our metric is stored contiguously and the row size is odd. So here's like the example. So basically we check if the address of the buffer we are trying to access is aligned to 8. If it's not, we align it down and just read 8 more bytes, and then just move the access pointer to get to the right place where we want to be. And that saves us 300 cycles. And now let's talk more about optimized data transfers. Here, once again, we've got our system. So we've got two-socket system, as you can see, two CPUs, and on each CPU, we've got one channel with two DRAMs and 5 channels with each with 2 UPMEM DIMMs. Because we only have one channel with DRAM, it can become a bottleneck, right? Because it's 3200 and we've got 5 2400 UPMEMs, so mathematically we could hit the limit of our DRAM. And also one thing to note is that in order to write to UPMEM, we need to transpose our data. So it's a process that heavily engages the CPU. And one thing that we found out is that allocation is not NUMA aware. There is no way to specify a NUMA node on which we want to allocate our rank. And we found out that there is a significant variance, around 12% in memory transfer speeds with normal allocations. And so we developed a simple API extension to allow for the allocations. Basically, we modified DPU alloc ranks to take in NUMA node as a parameter. And inside of the allocator, we just checked if the DPU is connected to the NUMA node specified. If so, we allocate it. If not, we search for another one. And here is the code, for example, that I'll show you in a minute. So we allocate the buffer, we allocate the ranks, and then we transfer this buffer to the DPU. Okay, and in our example with NUMA, we create 2 buffers, but they have the same size. In first example, and in the other, I mean, each part is half the size of the one from before, and we allocate ranks on one NUMA node and on the other. And here are the results. Dotted lines are the baseline, and contiguous lines are our results after optimizations. And blue line is the writing from host to PIM. And as you can see, there is a big difference in performance for a small number of ranks. That is because in UPMEM, in the default way, the DPUs are allocated first from a single NUMA node and only then from the other. And because of that, when we try to write from the second socket, we are basically bound because we only use one socket. We do not divide it equally between 2 sockets. So when we allocate it properly, we get much better results. And one thing to note is that we almost approached the top performance we got because we tested the performance for our DRAM modules, and combined, our throughput was around 30 gigabytes, and here we get around 23 gigabytes per second. So pretty good utilization. Yes. And just to summarize, as I said, we can't trust the UPMEM compiler yet. It can generate bad code, and we need to perform unrolling ourselves or use the pragma unroll directive. And just a little extra care with those simple optimizations really give us huge gains. But we can still do good optimization for int32. It's not as spectacular, but still 2 times faster. Yes, and the cheap performance that we've seen makes it a viable system for testing workloads. And when it goes to data transfer, NUMA awareness is really important. If you have any questions, you can contact me at Christian Chmielewski at Huawei.com. And thank you very much for your attention. Do you have any questions?
That's very cool, actually. My question is, did you inform Huawei people, Olgun people that they need to improve?
Not yet. Not yet. We hope that there would be some upman person here.
It's just like it's like a lot of you like went bit by bit and like figure out the thing, which is very cool. But I hope they know those things that they can improve over time, because it shouldn't be right.
Yeah, it shouldn't be this.
Yes.
Yes, exactly.
Very, very nice.
Thank you very much.
The microphone. Sorry. There's time someone left the room and stay. So I guess we are we are going for the coffee break, and then we come back at 4. Christina, how are you doing? Let me just mute this.
Yeah, let's fix. It's easy, like, you know. So the slides I don't understand it. It's only.
Let's see what's going on. I don't even see my Zoom anymore. We need to stop presenting.
Hi, how are you? Good to see you. Hopefully you came to the conference. Yeah, that's nice. Nice to see you in person.
And the camera. Ah, the spotlights appeared.
So, oh, okay. Where is the camera exactly?
Is there, and why is not is like that?
So, okay, okay, that one.
So it wasn't spotlight.
But you need to turn it.
Spotlight.
Right.
And then at some point, I turn the spotlight.
I kind of like this.
Christina, very nice. And the camera disappeared. How are you doing? Long time no see.
Let me ask something.
Of course. Let me just mute ourselves so
Okay. Well,
Sorry? Because I forgot to go to ETZ and pick it up. So usually Ataberk bring those things, but he's not here today this time around. Yeah, everything was in the backpack, but there was the lecture, and then is everything fine, Mohammad? Everything's okay. Can I just quickly use your phone? Thank you very much. So welcome back, everyone. We are going to continue. We have 3 more talks today. This first one is going to be for a From Safari student. So it's Yantal. She received her PhD quite recently in computer science from the University of Chinese Academy of Science. She earned a bachelor degree from Denkai University in 2019. And from 2023 to 2024, she conducted research under Professor Onur Mutlu as a visit PhD student at ETH Zurich. So her research focused on processing memory and energy efficiency accelerators, and she has received several publications, awards for her contributions to this area. So welcome, Yuntal, please, and take your time. Thank you very much. Thank you for your phone.
Okay, hello everyone. I'm Yintal. Today I'm happy to share our work here. It's PAPI exploiting dynamic parallelism in large language model decoding with a PME-enabled computing system. And so first, I would like to give you an overview of this work. We observed that the large language model decoding have different and dynamically changed computation and memory bandwidth at runtime. So however, we find that the existing heterogeneous PME-enabled system have 2 shortcomings. The first one is they only imply the static scheduling that will fail to dynamically cater to the changing kernel demands. And also, they only support one type of PM device with a certain computation and memory bandwidth. Therefore, our goal is to design a heterogeneous system that can cater to different and dynamically changing computation and memory demands. And our key idea is to enable online heterogeneous task scheduling on heterogeneous architecture. And therefore, we propose our new computing system called PAPI. It has a dynamic large language model kernel scheduling to the most suitable hardware units, and also with a hybrid PM to meet the diverse large language model kernel demands. And finally, we find PAPI outperforms a state-of-the-art PM-enabled large language models computing system and a pure PM system, and outperforms by 1.8 times and 11.1 times respectively. So here we go. Let's start with the background of this work. First, I would like to give you a case of large language model inference. There is an example. To be specific, we will have 2 stages. One is named profiling and the other is decoding. In the profiling stage, we will encode all the informations from the input request. Just like this, we have 4 input tokens here, 70 PhD, and we use the LLM to process the information to get the first output token. After that, let's go to the decoding stage. In the decoding stage, we generate the output tokens one by one or in parallel. So in this stage, we just leverage the last output token at to generate the next token, and we iterate the cycles until all the output tokens has been generated. So let's go to more detail about the large language model structure. Basically, it consists of multiple decoders, and in each decoder, we have multiple kernels. Let's say the yellow one, you can think it as attention kernels. And also we have the pink one, it is the fully connected kernels. For the attention kernels, all the parameters are encoded from the input tokens. Therefore, they have different data across different requests. And for the fully connected FC kernels, the parameters usually pre-trained by LLM training. Therefore, it can be used for all token generations. Okay, so we just mentioned that we can decoding the output tokens in serial or in parallel. So what's the serial decoding? Here is an example. In this case, we can generate the tokens from request A one by one. And it is obvious that we can only receive the low hardware utilization and also low throughput. So that's not good. Therefore, people provide parallel decoding to overcome these issues. For the parallel decoding, people can decode the tokens of one request in parallel, just like this figure shows. The two yellow upper tokens are from request A, and we process them and generate them in parallel. And moreover, we can even to decode different requests in parallel. You can see the green token and the yellow token are from request A and request B, and we can generate and process them in parallel. So for the first decoding technique, we can name it as the token level parallelism, TLP. And for the different requests in parallel, we can name it as the request level parallelism, RLP. So that's very important since we will use it after the slides. So the parallel decoding can achieve high hardware utilization and also high throughput. That's very good. So there is a question that is, do TLP and RLP benefit all the kernels in large language model decoding? So to answer these questions, let's go to our next section. Let's characterize the large language model and to see what will happen. So basically, we find three key observations, and we will present them one by one. The first one is that we find the large language model kernels have varying computation and memory bandwidth demands across different TLP and RLP configurations. And also for the second observation, we find the memory bound kernels exhibit a varied computation demands depending on the kernel type. And third, we find large language model kernels have dynamic computation demands at runtime. So let's get started from the first one. We just analyzed the rootline model of the large language model kernels with different TLP and RLP configurations. And you can see there are the rootline model on a GPU system. So we can see this figure. Some of the FC kernels and all the attention kernels are memory bound, but the other FC kernels are compute bound with the different RLP configurations. And also we have the same situation with the different TLP configurations. Therefore, the first observation is there are varying computation and memory bandwidth demands across different TLP and RLP configurations. And here I would like to give you some reasons why they have different demands with parallel decoding. When we implement the parallel decoding for FC kernels, it can leverage both TLP and RLP. It is because fully connected kernels can be leveraged and reused by all the tokens generation. Therefore, it is obvious that when the TLP and RLP has large values, we will have a compute bound fully connected kernels. However, for the attention kernels, it can be only processed in serial for different requests. It is because different requests need different attention kernels data. Therefore, the attention kernels can only benefit from TLP, which is much smaller than the RLP usually. Therefore, the attention kernels can be only memory bound. Okay, so now we know why the FC kernels and the attention kernels have very different demands. And let's go to the next observation. Now let's only focus on the memory bound kernels. You can see in this figure, the attention kernels, the yellow one point, has very small arithmetic intensity. It's much smaller than 10 flops per byte. However, for the FC kernels, it has a much bigger arithmetic intensity. And also with the different TLP, we have the same conclusion. Therefore, you can see the memory bound kernels has different memory has different computation demands depending on the kernel type. Okay, so next we find the parallelisms vary dynamically in the real-world scenarios. And here I would like to give you an example. Let's say the RLP, it is decreasing at runtime when we use the static batching. Let's see, we analyze the decoding cycles of requests in one batch, and as you can see this figure, when the decoding cycles increase, the request number is decreasing. Therefore, the ILP decreases. And not only for the RLP and also for the TLP. And here we give a lot of reasons for why these parallelism levels are dynamically changing. And you can see more details in our paper. So based on this analysis, we find the large model kernels have dynamic computation demands at runtime. And we invite you to check all the analysis in our paper. So next, let's look at a state-of-the-art approach. This approach is a heterogeneous PIM-enabled computing system for large model inference, and it has a computation-centric, it has a memory-centric computing device with a computation-centric device. And usually, we map the attention kernels to the PIM-enabled device, and we map the FC kernels to the computation-centric device. So we find there are two shortcomings for this state-of-the-art approach. The first one, they imply the static scheduling, and it will lead to suboptimal performance across different parallelism levels. And the next, we find that this approach supports only one PIM device with a certain computation and memory bandwidth capacity. Okay, so let's get started from the first one. We just mentioned that the state-of-the-art approach typically takes a static scheduling, which is assign all the attention kernels to the memory-centric device and assign all the FC kernels to the computation device. So this scheduling is good for the memory-bound attention kernels since they are always memory-bound. However, that's not good and will fault for the FC kernels that switch between compute-bound and memory-bound dynamically. As we mentioned before, in the roofline model, you can see the FC kernels and the memory FC kernels can be memory-bound or compute-bound dynamically and differently. So therefore, the static scheduling leads to suboptimal performance of FC kernels across different parallelism levels. Okay, so next, let's go to the second shortcomings. In the previous works, we find they only leverage one type of PIM device with a certain computation and memory bandwidth. However, the memory-bound FC kernel and attention kernels we just mentioned, they have varying demands of computing and memory bandwidth demands. Therefore, this approach only supports one PIM device with a certain computation and memory bandwidth capacity is not good for the FC and attention kernels. Therefore, our goal is to design a heterogeneous system that can cater to the varying parallelism levels in real-world inference with different and dynamically changing demands. And next, let's go to our key ideas. To achieve our goal, we hope to enable online dynamic scheduling on a heterogeneous system via online identification of kernel properties in logical model decoding. And so we propose the PAPI. PAPI is a new computing system design with two components. The first one is a hybrid PIM unit. It can cater to different parallelism levels for the FC and the attention kernels. And also we propose dynamic LLM kernel scheduling to cater to the varying parallelism levels. Okay, so here is the PAPI's overview. You can see in this figure, first we have a PAPI's system. And in this system, we have two kinds of PIM units. It's a hybrid PIM unit, and we have a scheduler to execute the dynamic scheduling. So let's see how to implement PAPI in more detail. Okay, here is the overview of PAPI architecture. We have three components. One is the high-performance processor and the attention pin devices, and also the host CPU. Let's go into more details about the high-performance processor. In the high-performance processor, we have a scheduler to execute the dynamic scheduling and two kinds of computing units. One is PU's processing unit, and the other is the FCP. So when the FC kernels compute bound, we will assign the FC kernels to PUs, and when the FC kernels memory bound, we will send them to the FCP. Therefore, the FCP and PUs can cater to the different compute bound and memory bound FC kernels. And next, let's go to see the hybrid PIM units. In hybrid architecture, we have two kinds of units. One is FCP and the other is attention PIM. FCPIM is placed in the high-performance processor, and for the attention PIM, it is distinguished from the high-performance processor so that we can add more attention devices as you want to increase the memory bandwidth and the memory capacity as you want. Okay, so with this design, the hybrid PIM units cater to memory-bound kernels with different demands. And here are some details about the two PIM units. For the FCPIM, it has more floating point units per bank. Let's say, here you can see, for each bank, it has 4 FPUs. Therefore, it can provide higher computation capabilities. And for the attention PIM, it has more bank groups per bank stack. As you can see, compared to the FCPIM, it can have 4 bank groups per crystal channel. Therefore, it can provide higher bandwidth and also capacity. So now we have two kinds of computing units for FCPIM kernel executing. And how can we do the runtime scheduling? Before we do the runtime scheduling, we require the initial part. We need to identify the memory boundness threshold through offline iterative evaluation. And after that, we will execute the runtime scheduling process. It will have 3 steps. First, we will monitoring the parallelism levels, let's say the RLP and TLP. And once we find the parallelism levels change, we will execute the arithmetic intensity predictor to estimate the FC kernel's arithmetic intensity, and then compared with the memory boundness threshold to see if the FC kernel is memory bound or compute bound. Okay, so after that, we will schedule the FC kernels as we just compared to map the FC kernels to FCPIM or PUs. And here I would like to give you an example to see the process of dynamic scheduling. Let's assume that the memory boundness threshold alpha is equal to 4 in this case. And first, we will generate some alpha tokens cycle by cycle, and here are 3 cycles. We always monitoring the TLP and RLP, and since they didn't change, so the estimated arithmetic intensity didn't change. And then we don't reschedule the FC kernels, and we don't have any new mapping results. But after that, when the first cycle, you can see here is the EOS token, the end of sentence. That means the first request is finished. Therefore, the RLP changed from 5 to 4, and the estimate value changed to 4. Since it is still larger than, since it is equal to 4, so we just still mapping it to the processing units. And let's go on for the 5th cycle. In this cycle, you can see there are only 2 requests are still working. Therefore, the TLP, therefore the RLP becomes to 2. And in this time, the estimate value becomes to 2. And it is smaller than the threshold. Therefore, we just map the FC kernels to PIM units. And we will execute the very similar process cycle by cycle until all the output tokens has been generated. Okay, so let's evaluate copy. In this evaluation part, we evaluate PAPI's performance and analyze and energy with multiple simulators. And we have 3 baselines. The first one is a state-of-the-art LLM computing system, Ataberk, and a GPU plus HBM PM unit, and also a PM-only computing device. And we have 3 workloads, which are very popular transformer-based LLM. And we evaluate them on the solid dataset with 2 different tests. So here are the performance analysis. As you can see, PAPI can provide speed up by 1.8 times, 1.9 times, and 11.1 times compared to the 3 baselines. And here are the energy results. PAPI provides energy savings by 2.42 times, and 0.15 times compared to the 3 baselines. Okay, so we have more details in our paper. Let's say the PAPI's heterogeneous design, the runtime scheduler, sensitivity, and the speed up of SCP, and also the time breakdown. So you can find all details in our paper. We invite you to check. And finally, let's conclude our work. In this work, we find 3 findings. The first one is that there are varying computation and memory demands across different parallelism levels. And also the memory-bound kernels exhibit various computation demands depending on the kernel type. And also LLM kernels have dynamic computation demands at runtime. Therefore, we propose the PAPI. Our key idea is to enable the online dynamic scheduling on a heterogeneous architecture. And finally, the key result shows that PAPI can improve both performance and energy of the state-of-the-art baselines. And these are all for my talk today. Happy to take any questions. Sorry? I see. The thing is that if you execute both the attention and the FC PM on the PM device, you will see the attention will only cost about 1% of the total execution time. And you can check this performance execution time breakdown in my paper. Then you will see the attention kernel will cost very less time. Therefore, we only focus on how to speed up the FC kernels. Yes.
So my question is how general that
yeah, I got it.
Also for which system?
Yeah, we
how much we are dependent on the architecture when you want to calculate the
yeah, thanks. We just use the same configurations with our evaluation to do the offline, let's say, to do the offline identification. And with this process, we execute the FC kernels with different TLP and RLP to see which TLP and RLP it can have a better performance on the PM units, and which TLP and RLP can have a better performance on the GPU platform. And it has a value for to as the threshold, since if the TLP and TLP plus LP has a much better value, it can works well on the memory-centric, on the computation-centric device like GPU. And if the value is much smaller, it can provide a better performance on the PM device. That's how can we identify the memory boundness value. Yeah. We all the attention are executed on the PIM device. So we use the PIM device as the KV cache. Yes. Very good question. The thing is that, between the attention, first, the high performance processor is only for the FC kernel's execution, and the attention kernel is for the attention kernel execution. Therefore, they only require to connect with the attention vectors, right? So the vector can be very small. Therefore, we can only use the general interconnection, let's say the PCIe, something else, to do this, and it won't be the bottleneck, time bottleneck. Yes. Yeah, but you can also use something else like CXL. Since we only care about the processing unit speed and the FCP, we require them have a high-speed interconnect, since they have to move the weight parameters from SSP to the processing unit, and it is a lot of data movement. Therefore, it needs a high-speed interconnect. But for the high-performance processor between the attention device, that's okay.
Okay, now we are going to have online talk, and it's a perfect time to change because CXL was just mentioned. Let me just see how I should do this.
Hi, Geraldo.
Hello. I can hear you. Great. Maybe I just need to make this sound louder. If I find my Zoom screen. So when I click on back to meeting, when I go back to the meeting. That's weird. Just 1 second. I'm having difficulties.
Oh, sure. No worries.
I guess once you become 30, you cannot do completely. My entire screen is shared. Okay, let's go. Increase the volume. The loudest speaker ever.
Maybe we can have a test. Is the voice on?
We can hear you well now.
Oh, okay. Thank you.
Let me just stop with this. It's just so many moving things at once. Oopsie. Okay. It's true. Okay, hopefully didn't break anything. Okay. Okay, now you can hear me.
Yeah.
Perfect. Let me quickly introduce you. So Yufeng is a PhD candidate at the University of Michigan, advised by Professor Ritu Das, which is on my PhD committee. So I need to be very nice to him. Prior to University of Michigan, Yufeng obtained his bachelor degree from Zhenjiang, I don't know how, sorry, University in 2020. His research focused on computer architecture, hardware, software co-design, near memory processing, quality of service optimizations. So he's have been developing hardware and software solutions on accelerating larger scale emerging applications, such as precision health and generative AI workloads. So without further ado, we can get started.
Yeah, thanks so much for the introduction. I'm Yifeng Gu, and it's my great honor to present our recent work, PIM is all you need, a CXL-enabled GPU-free system for large language model inference. This work was done under the collaboration between University of Michigan, ETH Zurich, and Intel. We open source our artifact on this GitHub link below. So we all know that large language model has reshaped people's lives in various areas such as text, audio, video generation, coding assistance, intelligent agent, and so on. Currently, the inference actually takes twice carbon footprint than training on language models. So in this work, we focus on the inference. So we can see the API cost for large language model inference has been increasing very fast, whereas across different tasks, like from text to audio to reasoning and to video. So this figure shows the cost for 1 million output tokens. So currently, LLM inference is deployed on GPU servers, which is very expensive. However, the GPUs are underutilized on LLM inference when compared to the prior ML models. Why is GPU underutilized on large language model inference? So we can first see how large language model inference work. When user sends a prompt, each token in this prompt are converted to a vector, and then these embedding vectors are processed in parallel by multiplying with the model weights. Then in the decoding phase, these new tokens are generated one by one in an autoregressive manner. So in this process, the tokens cannot be batched as they're in the prefill stage. So the decoding stage dominates the end-to-end large language model inference. In the decoding phase, when we generate each of the new token, it goes through a series of transformer blocks. Each transformer block is composed of fully connected layers, followed by self-attention and then fully connections. When batching multiple queries during this inference process, it actually occupies a large GPU memory capacity. In this example, we serve Llama 70B model, so we can see that around 140 gigabytes are used to store the model weights, and the other, so KV cache also occupies a large memory capacity, especially with the batch size increasing. So here we can see with 4 A100 GPUs, it can provide 320 gigabytes of memory. With 128 batch size, it will exceed the GPU's memory capacity. With the context length increasing, these trends will become more obvious. So the recent model can not only support 4K context length, instead they support from 128K context to 1 million or even 2 millions in the most recent large language models. So here we can see from 4K context to 32K context. The maximum supported batch size on the 4 A100 GPUs decreased from 128 to 16 and can decrease to a smaller number. So when we batch multiple queries, the fully connected layers can be batched. However, the self-attention layers cannot be batched because they operate on user-specific KV cache. So the self-attention has to be processed in a sequential manner. In this case, the large language model inference actually operate on a low operational intensity. So this gym operation dominates a lot of ML workloads, which has a high operational intensity. But this does not happen on large language model inference. So in gym operation, we can see this in this example, two operands have 4K by 4K matrix. And when we conduct the matrix multiplication, each operand actually operate on two operations for both multiplication and addition. So we also need to fetch all of this data from the DRAM. Each value in this example, we use BF16, which occupies 2 bytes. So based on this formula, we can see the operational intensity for this gym operation is 2000 ops per byte. A100 GPU can provide 156 ops per byte when we divide the peak BF16 compute throughput by its peak off-chip DRAM bandwidth. Well, in large language model inference, as I explained before, the maximum supported batch size is limited by the GPU memory capacity. Meanwhile, the self-attention layer cannot even be batched. So the input operand will only be like 16 by 4K or like between 4 by 4K to like 32 or even 128, which is much smaller than the left example, the 4K by 4K input matrix size. In this example, the operational intensity drops to 16 ops per byte, which is much smaller than the GPU's operational intensity. That's why the current advanced data center GPUs are underutilized on these large language model inference tasks. So how can we efficiently serve large language model inference with such low operational intensity? Because operational intensity is determined by compute throughput and memory bandwidth. If we can increase the memory bandwidth that hardware can support, then we achieve a low operational intensity. So although GPUs provide a high peak memory bandwidth by HBM, like 2 terabyte per second, processing in-memory technology can provide a even larger bandwidth. With one GDDR6 PIM chip, it can provide 32 terabyte per second peak bandwidth between the DRAM bank and processing unit. In this way, with a high memory bandwidth, it can efficiently support the low operational intensity characteristic of LLM inference. But with such PIM technology, the processing unit occupies extra area and resources. So even so the memory capacity it can provide is decreased. There are some examples for the industry protocols which sacrifice different proportion of memory density. However, the large language model requires a huge amount of memory capacity. With Llama 70B, 4K context, and 128 batch size, it requires 450 gigabytes of memory capacity. With 140 gigabytes on model weights and more than 300 gigabytes on KV cache. This is Llama 270B, but the more recent large language models have even larger model parameters and increasing context length. So they will require more and more memory capacity. In order to support such large capacity on the capacity limited processing in memory technology. We apply the CXL network to interconnect multiple PIM devices. So each PIM device can, in this example, in this work, we apply GDDR6 PIM. Each device can provide 16 GB of capacity. With this scalable CXL interconnect, 32 devices can aggregate half a terabyte of memory capacity, which is enough to support the large language model inference task. In this work, we propose the CENT architecture. It is composed of a whole CPU, a CXL switch, which interconnect 32 CXL device. Each CXL device contains a CXL controller, 16 GDDR6 PIN modules, and PNM units. And we'll explain the detail for each of the components in the subsequent slides. A full transformer block contains various operations, but PIN module can only support vector and element-wise multiplications. These operations account for 99% of the total operations in the transformer block. However, there are some other operations, like the remaining 1%, as shown in the orange blocks in this figure. They cannot be efficiently supported by PIM modules. If we want to support them in the PIM, we have to increase the processing units area, which is inefficient in the near bank design. So we operate this on the processing near memory accelerators, which also located on the CXL device, but outside the PIM modules. They can support the vector additions, reductions, exponents, and we also deploy RISC-V cores to support special functions like divisions. So in this way, we don't need to offload these rare operators on either CPU or GPUs, but can process them within the CXL device, which can save a lot of inter-device communications between the device and either host or GPU. So here is the near bank processing unit, which has a similar architecture as the AIM prototype. So the processing unit fetches 16 values from the DRAM row buffer and the other 16 values from the global buffer. And they operate on a max reduction tree. So each value fetched from the global buffer and DRAM row buffer first are multiplied, and then the 16 multiplication results are accumulated through this reduction operation. Well, the processing near memory units include the RISC-V cores. So this is the first module shown on the top left. So we have 8 2-wide boom core. They can support a very flexible range of operations. So if there are future transformer block architecture proposed, like different activation functions and different rotary embedding functions, and they cannot be supported by the current PIM module or these accelerators, then RISC-V can support them anyway. There are also vector addition operators and reduction tree and exponent processors. These exponent processors are designed to efficiently support the softmax operation. So on the CXL device, it starts from fetching instructions from a 2 MB instruction buffer. After decoding, they are sent to either the PIM modules or the PNM accelerators. The intra-device communication are enabled through a shared buffer, which can move data between the PNM units and PIM modules. The inter-device communication is handled by the CXL port, it will pack the fleets and send it to the destination device, or receive fleets from the other device and unpack them. So here is the CXL port architecture as I mentioned before. The top shows the host or remote PIM device, and the bottom shows a local PIM device. If we want to send the data to other PIM device, this data are prepared and packed to a fleet and sent to the destination device. And the receive process is on reverse. It unpacks the fleet and store the result to either the shared buffer or DRAM banks for further computations. Our inter-device communication utilize different instructions. So the peer-to-peer communication is done by send and receive. We propose new instructions, multicast, to achieve new communication primitives, the multicast and gather. In multicast, each device sends data to several different neighbors, which are conducted by the receive instruction. For gather, one device collect data from several different devices by the send and receive instruction. So these new primitives can efficiently support the model mapping, which I will introduce later. The flexible model mapping strategies can provide more design space exploration, for example, when we balance the inference latency and throughput. We explore two different types of model mapping. One is pipeline parallel, the other is tensor parallel. In pipeline parallel mapping, each transformer block is deployed on a single device, and each device can actually serve multiple transformer blocks. The inter-device communication only happens between two neighboring transformer blocks through the peer-to-peer communication. When multiple prompts are served, they can, like in a pipeline parallel manner, it can maximize the serving throughput. While the tensor parallel mapping allocate each transformer block to multiple CXL device, which minimize the serving inference. It will utilize multicast and gather primitive that it mentioned in the prior slides. So in this way, this different mapping strategy can be combined together to strike a balance between the serving latency and throughput. Our evaluation methodology include the performance, power, and cost model. In the performance model, it starts from the workload mapper and trace generator. The traces are sent through a remulator-based cycle accuracy simulator, together with the CXL communication analytical model. Our power model utilized the micron DRAM power model and the synthesis results for the PNM accelerators. We also model the cost of the PIM design because it's much cheaper than the GPU system. We use 10 times of the DRAM cost to estimate the PIM cost. For our custom design, we consider the NRE cost, die, and packaging cost. The evaluated sense system has 32 CXL devices. It is compared to a GPU system with 4 A100 GPUs. The sense system provides around half of the peak compute throughput than GPUs, but 64 times the peak bandwidth more than GPU baseline. The sense system also provides a much lower total cost of ownership. which is 2.4 times lower than the GPU baseline using an owned TCU. If we consider the rental TCU, there will be more times of saving because the cloud provider actually has a higher price on the GPU rental than the owned price. So here we can see the throughput comparison between the synth system and GPU. This chart shows the normalized tokens per second on synth and on the synth system across 3 different llama models with different model size. These experiments are conducted with prefill tokens of 512 and 3.5K decoding tokens. Synth system achieves an average of 2.3 times throughput than the GPU baselines. Considering the 2.4 times lower hardware cost, the synth system can achieve a 5.2 times more tokens per dollar when compared to the GPU, providing a more cost-effective solution. And the throughput speed up on the decoding phase for the synth system achieves a more advantage on the longer context length because the GPU baseline can support a lower batch size when the context length increasing, and then the GPU utilization can be even lower. But Synth does not have this problem. Meanwhile, when we compare the latency, the query latency between Synth and GPU, Synth achieves a much lower query latency when compared to the GPU when they have a similar throughput. So Synth system can provide a better user experience. This chart shows the latency breakdown on the Synth system between different hardware components across the different parallel mapping strategy. The first line shows the pipeline parallel equals to 80. That is the highest pipeline level. So in this case, the query latency is the longest, but it can provide the highest serving throughput as well because there are 80 queries can be processed in parallel. The other pipeline mapping strategy is a hybrid between the pipeline and tensor parallel. The bottom one shows the pipeline parallel equals to 1, that is the full tensor parallel, so which achieves the lowest query latency. However, there is only one query can be served at the same time. We can see the pin module dominates the query latency. And the first highest pipeline parallel mapping has almost no CXL communication latency because it only has peer-to-peer communication and no multicast and gather. When we increase the tensor parallel, the pin module will there will be more pin modules utilized at the same time. However, the CXL, PNM, and host CPU latency cannot be scaled with the tensor parallel increasing because the total amount of resource here are actually a constant. For the CXL latency, we can see it increased from the first example, from the first instance to the last one because more tensor parallel means more CXL communication between different devices for multicast and gather. This chart shows the scalability study. Our main evaluation shows 32 CXL devices in the Synth system. And here we can see if we increase the device count from 16 to 128, how the throughput can scale and how the device utilization differ on these different configurations. The left chart shows the throughput. So basically, the throughput scales well with the device count increasing. When we have more device, we can apply more data parallel. So the prior pipeline parallel and tensor parallel actually have a single copy of the model weights. But if we have more device, we can have multiple copies of model weights, which can serve more data parallel options. The right figure shows the device utilization. For example, if we have like 37 devices, which cannot be evenly divided by like the number of transformer block, then the device utilization can drop. But basically, the device utilization can achieve more than 70%. To conclude, we observe that when serving large language models on the GPU, it requires a large memory requirement. This results in a limited batch size on the GPU. Meanwhile, the self-attention cannot even be batched. So both factors makes the large language model inference have a very low operational intensity, which makes the GPU utilization low. To solve this problem, we propose the processing in-memory solution, which provide a high bandwidth between the DRAM bank and processing units near the DRAM bank. We also design a hierarchical PNM design to serve the entire transformer block on the local CXL device to avoid any operation on the expensive GPUs. To achieve the high memory capacity requirement, we use the scalable CXL network to interconnect multiple PIM devices. And finally, achieving more than 5 times of the tokens per dollar, providing a more cost-effective solution than the GPUs. And please check our paper and artifact for more details. Thank you all for listening, and I'm welcome for any questions.
Thank you very much for the great talk. Do we have questions in the room? No questions? Okay. Just a sec. I need to move the microphone.
Thank you. So I have one question for this. Which CXL version and which iteration the PCIe did you use for this research?
Yeah, thanks for the question. So we target on the CXL 3.0 because it can well support the inter-device communication. And we target on the PCIe 6 for the performance evaluation. And for the visibility of the CXL switch, we refer to a current commercial PCIe 5.0 switch, which can support like up to 72 ports and 144 lanes. So for the feasibility, we refer to the commercial switch, but for the performance evaluation, we target on the CXL 3.0 and PCIe 6.
Thank you very much. Any other question? So thank you very much again, the speaker, and then we're going to head up for our last talk. Thank you for joining from the US. I don't know what time it is over there now, but it's either too early or too late. But so thank you so much.
Yeah, thanks for the hosting.
Everything's fine. Ah, yeah, yes. Yes, I'm just going to, don't know what I did here. Something funny. So, we are heading to, I'm listening to myself. Or let's talk from this workshop. So this is Christina, a fellow Safari member. And I'm just trying to find her bio because it's very long. So Christina has received her PhD from the School of Electrical and Computer Engineering from the National Tech University of Athens. I'm going to skip some parts because it's very long. She's currently a postdoc researcher at the University of Toronto, advised by Professor Gennady and his research group. She's also with the Safari Research Group and Professor Onur Mutlu, and her research interest includes the intersection of computer architecture, computer system, and high-performance computer systems. She has several publications and awards, and her research of of all of those topics. She's also a member of the ACM, ACMW, and the Technical Chamber of Greece. And just a warning, apparently her mom is watching over YouTube, so be very nice with Christina, please.
Okay, thank you for the introduction. I will also send greetings to my mother. Okay, so today I will present our work PyGym. Okay, so let's start with the summary. So here in this project, we basically study graph neural networks, and we analyze them in modern computing systems. These is a very important machine learning models that are used for drug discovery, social network analysis, and recommendation systems. So we found that these machine learning models have basically two types of kernels, and the memory-intensive kernels dominate the execution time significantly, and they are bottlenecked by the memory bandwidth in processor-centric systems like CPUs and GPUs. And as a result, we explore the processing memory design for those models. We design an easy to use library for real PIM systems so that we basically tackle the data movement problem in memory-intensive kernels of these models. PyGym has different key ideas and benefits. First, it executes heterogeneous kernels of graph neural networks in the best fit hardware. The compute-intensive kernels are running on processor-centric systems, while the memory-intensive kernels of the DNNs are running on the real PIM devices. Second, it provides high performance because it enables 3 levels of parallelism, because we need to trade off the data transfers and the computation costs, and we trade off this by enabling an adaptive parallelization approach with various parallelization strategies. And we adapt this parallelization strategy to the different characteristics of the input graphs, because real-world graphs have different characteristics in terms of the non-zero patterns. And finally, we enable high programming ease because we expose this implementation with a very high-level interface, that is a Python interface. And we also expose a lightweight tuner so that we basically adapt automatically the parallelization strategy, and we don't need the programmer intervention to enable very high performance. So overall, PyGym provides high performance and energy benefits up to 3.7 and 2.3 respectively over state-of-the-art schemes, and significantly improves the resource utilization on a PIM system compared to using PyTorch on a GPU system. And it is also open source. It is already available on GitHub. So let's start with motivation, the background and motivation. Graph neural networks are widely used in many important applications. Some of the important applications are drug discovery, recommendation systems, and fraud detection. So the graph neural networks comprise multiple layers, and at each layer we have 2 execution steps. The first step is called aggregation. It is basically a step where we multiply the sparse matrix. The sparse matrix represents the graph with a dense matrix, which is basically the feature matrix. And the second step is called combination. In the combination, typically there is a small neural network that is comprises basically from various computational kernels, which are typically dense matrix multiplication kernels, and they are regular kernels. And these basically these two execution steps are repeated in every layer, and there are multiple layers on the graph neural networks. So this part, basically the aggregation step, corresponds to a sparse matrix multiplication, and we analyzed these two steps on a real GPU system, that is a high-end GPU and RTX 3090 GPUs. So we found that the aggregation step of the graph neural network layer takes almost 90% of the inference time. It dominates the performance and the execution time, and it is also bandwidth bound, while the combination part, it tends to be a very compute intensive part. Yeah, the aggregation step is bandwidth by the memory on this particular GPU that we use. So we explore the solution of using processing memory in order to tackle this problem, this bottleneck on the memory-intensive kernels of GNNs. Here we experimented with a near-bank PIM system. A near-bank PIM system has one core per each DRAM, for each bank, for each DRAM bank. Each PIM core is located close to a DRAM bank, and they can access, the PIM core can access data located locally within the DRAM bank. And there are multiple PIM-enabling memory modules that are connected with the host processor. The host processor can be either a CPU and a GPU system, and it is also basically connected with standard memory modules. So in this near-bank PIM architecture, the PIM cores have significantly higher memory bandwidth compared to the host cores that are either the CPU or the GPU cores. So let's dive into the details of our design. So PyGym is a library to deploy graph neural networks on real PIM devices, and it has 4 key components that I will explain in details next. And it is also open source. So the first component of PyGym is called cooperative acceleration. And the key idea here is that we run heterogeneous kernels on the best fit underlying hardware. So this means that the combination step of the graph neural network is running on the host cores, which are either the CPU or the GPU cores, while the aggregation step, which is basically the memory intensive step, is running on the PIM cores. And these steps are continuously repeated, the one after the other, because we have multiple layers on the graph neural networks. So the key bottleneck that we need to basically tackle here in this execution is how we move the data between the two execution steps. When the combination finishes, we need to get the output that is passed as input on the aggregation step. And once the aggregation step finishes, we need to take the output of the aggregation step to be passed as input on the next combination steps that are repeated continuously. So in order to basically minimize data movement and also achieve high computation efficiency, we propose a second key component in PyGym, which is called parallel fusion. With these components, we balance the computation with the data transfer cost. And also we provide different parallelization strategies in this scheme so that we tackle different real-world graphs that have different characteristics, diverse characteristics. So the key idea of PAF is that we have 3 parallelization levels. First, we group the PIM cores in clusters. So we have multiple PIM clusters. And when we have multiple PIM clusters, we need to parallelize the aggregation, which is basically the sparse matrix multiplication. So in order to parallelize this, we use edge and feature level parallelism across the PIM clusters. In the second level, we have different parallelization strategy within a PIM cluster. We use vertex or edge level parallelism between the cores within the PIM cluster of one single PIM cluster. And finally, each PIM core can have multiple PIM threads. So we have a different parallelization strategy, again, between the threads within a PIM core. So the key idea is that we have enabled 3 levels of parallelism and different parallelization strategies at each level. so that the first level of parallelization strategy will reduce the data transfer costs from and to the PIM-enabled memory modules. And the second and the third level of parallelism will reduce the computation costs, basically it's the compute balance between the PIM cores. So we basically provide a strike, and we strike a balance between data transfer costs and computation costs in this sparse matrix multiplication kernel. So next I will describe different parallelization strategies that we use across PIM clusters within the PIM cluster and also within the PIM core. So across PIM cluster, we enable basically edge and feature level parallelism. So here I have a sparse matrix and we assume that we have created 4 clusters. So in this case, we split the sparse matrix vertically. And this is basically translates as an edge level parallelism because we have 4 clusters. The first 2 clusters have share the same edges, a part of the edge, a small subset of the whole edges of the graph. And the cluster 3 and 4, they share the same edges. And this is basically a part of the whole and available edges of on the whole graph. And then we also split the input feature matrix vertically across the cluster. So this enables feature level parallelism because each vertex of the graph has a feature vector. And here you can see that the cluster 1 and 3, they share exactly the same features, but the cluster 1 and 2 have different features per vertex. So this approach basically creates partial results whenever we run the sparse matrix multiplication on the PIM cores, and these partial results are merged to the host cores by the host in order to get the final output of the aggregation. Then we have a different parallelization strategy within a PIM cluster. Here we have multiple PIM cores and 1 cluster, and we need to parallelize the sparse matrix. And in this case, we split the matrix horizontally. So here we can balance the vertices across the PIM cores. Each core here processes 4 vertices. Or we can also balance the edges across the PIM cores. So here each core basically processes 10 edges, 10 non-zero elements. Then we have a similar parallelization strategy between the threads of 1 single PIM core. Again, we split the sparse matrix horizontally, so the threads can take either the same number of vertices, like 2 vertices here, or we can also balance the edges. So here each thread takes 5 non-zeros, and we have they have exactly the same number of edges to process. So in this particular example, we also need to enable synchronization between the threads because the threads have a shared memory model whenever they access the DRAM bank. So we have enabled different synchronization schemes like either coarse-grained logging and also fine-grained logging. So the second challenge that we need to tackle is that the real world graph different characteristics, different non-zero patterns, and this is basically something that it is taken into consideration on the path component that I described. There is no one-size-fits solution on the best performing parallelization strategy across all different graphs. So this is why we have enabled different balance strategies in the path parallelism so that we tackle this diversity across the real code graphs, and we are able to provide the highest possible performance based on the particular characteristics of the input graph. So the challenge that we need to solve then is how to tune the best performing parallelization strategy for each particular graph, for each unique characteristics that a graph has. This can be done manually by the user, but in order to avoid the programmer intervention, the programmers basically to leave this to the programmer so that the programmer finds how to balance the edges or the vertices within the PIM cores of the clusters or within the threads of the PIM of 1 single PIM core. We don't do this manually, but we have enabled a third component in Python, which is basically a tuner. So the tuner does a small reprocessing step. It takes the real code graph and the real PIM system. It runs some micro benchmarks there and tries to profile the characteristics of the PIM system, like the compute capabilities and memory bandwidth, and also finds the non-zero pattern of the graph. And once this finishes, the tuner directly produces the best parallelization strategies that we can enable on the path. So it automatically finds how we can parallelize the sparse matrix across the PIM clusters, across the cores of one single PIM cluster, and also across the threads, between the threads of one single PIM core. So all this implementation is basically exposed with a very high-level interface, which is a Python interface. So here I have an example code on how to basically perform graph neural network inference. So here in the first step, the user just uses basically creates a graph neural network model which has like 3 layers that are repeated the one after the other. So this is the common Python interface that is used to deploy graph neural network models. And then the user needs to import the library that we expose, that we call it PyGym. And then in the memory-intensive kernel of the inference in the forward pass, the user needs to basically use our API in order to run the aggregation part on the real PIM devices. And the final step is basically the user also has the possibility to enable the tuner. So the tuner basically does a small preprocessing step on the graph and automatically tunes the best parallelization strategy whenever we run the memory-intensive kernel on real PIM devices. So with these very simple steps, you can see that here that basically it is running. We run here the graph neural network inference and this real PIM device that we can use and this device that is already available on the market. And yeah, this library is open source. You can just download it and try to just directly use it on a real system that supports these PIM-enabled devices. So next I will go into the evaluation. So here we use a real PIM system that has a CPU that is connected with PIM-enabled memory modules. And there are multiple of PIM-enabled memory modules. Actually, there are 16 DIMMs, and in total there are 1,992 PIM cores available in the system, and each core can have up to 24 threads. We have evaluated different graph neural network models and also different data sets. And we compare PyGym with these 3 comparison points. First, it is the PyTorch whenever we run the memory-intensive kernels on the host CPU. So it is basically only CPU-only execution here. Then sparse P, which is basically an implementation of the sparse matrix vector kernel. We run the sparse matrix vector kernel as a sparse matrix kernel. And this is a baseline that basically runs the SPMM on real PIM devices, but the SPMM is running as multiple SPMVs. And finally, Grante. Grante is also a real PIM execution where the GNN aggregation is running on the PIM devices, but this implementation is optimized for near-rank PIM systems, while here the system that we have is a near-bank PIM system. And yeah, near-rank PIM systems are not available on the market. They are only in research and experimentation phase right now. So here I demonstrate the evaluation and the performance that we get. We have different graph neural network models and also different data sets. And yeah, PyGym significantly outperforms both the PyTorch with the CPU, which is basically the baseline, and also the prior PIM-based schemes by 3.1 and 4.4 respectively. And here I demonstrate the energy consumption. So in this graph, in this plot, the lower is the better. So again, PyGym, the 2 versions that we have for CSR and Q format significantly improve energy efficiency over both PyTorch and the prior PIM-based schemes. So finally, we also evaluate the resource utilization. So here we compare the resource utilization that we can achieve on a real PIM system with different GPU systems. And we have 3 different generations of GPUs, the 1080, 2080, and 3090. And here we have 2 main observations to do. First, across the GPU generations, we can see that basically the bandwidth significantly improves in the GPU, like up to 3x, and also the peak performance is also improved. And the second observation is that if we compare the GPU and the PIM system, we will see that the PIM system has only, the real PIM system that's available right now on the market has only 1.5x larger memory bandwidth than the GPUs. So it is not significantly higher bandwidth over the GPU so far. So if we take a look at the resource utilization, we make two observations again. So first is that the resource utilization on GPUs on the memory-intensive kernels, the aggregation of the GNNs is very low. It is less than 3% in total in all the different data sets and graphs. And yeah, you can see here that across GPU generations, although the bandwidth that I had in the previous slide here, although the bandwidth has been improved significantly up to 3x, you will see here that the resource utilization has not been improved. It is always basically remains the same, and it is less than 1%. And yeah, so the second observation that we do is that the PIM system significantly improves the resource utilization. So the resource utilization of the PIM system is 9x increase, which is significantly better. However, as I showed you before, basically the PIM system has only 1.5 larger memory bandwidth than the GPUs. With only 1.5 higher memory bandwidth, the resource utilization has been improved by 9x, which is basically a significant improvement and helps a lot to improve the total cost of ownership. So there are many other results and other scalability studies and analysis, and also many recommendations that we have in our paper, which is available on arXiv. And yeah, this is basically the web link that you can download the library. So to sum up, PyGym is a handy machine learning library to improve the performance and energy efficiency on graph neural networks by leveraging processing memory devices and real processing memory devices. Basically, it has many key ideas to improve performance. It runs heterogeneous kernels in the best fit underlying hardware. Then it balances the computations with the data transfer cost by providing different parallelization strategies in order to address the different characteristics of real-world graphs. And then it basically has a tuner that automatically tunes the best fit parallelization strategy without the programming intervention, so that we have very high performance and also high programming ease. So overall, PyGym significantly improves performance and energy efficiency over other state-of-the-art schemes on real PIM devices, and significantly improves the resource utilization over GPUs. And it is available on GitHub. Thank you, and I'm happy to take questions now. So we are basically exploring to extend now the library to support a wide variety of models, not only graph neural networks, but also other models, like even LLMs. Sure. Yeah, that's a good question. So the parallelization strategies that we propose are the key ideas directly apply on all nearbank PIM devices, even the Samsung 8PM. The library right now uses the AppMem API that is available. So, whenever there is a different API on another device, we need to extend the library. So we just use the new API for the new device to run it on another Realcom device. Okay, thanks.
So this concludes our first workshop on memory-centric computer systems. Thank you everyone for joining and online as well for attending. I hope you learn one thing or two. Thank you so much the speakers that came here or were online presenting and submitted their work or for the presentations. I think we all learned something new today, which is great. And I hope to see you in the next one, in either ICS or in ISCA. Soon, I didn't open it yet, but we are going to have a call for presentations as well. If you want to present on the new instance of this workshop, feel free to contact me or Onur. We will be glad to receive your proposal. So thank you everyone again, and hopefully you enjoy your time here. Thank you. Stop this. You want to say something Greek to your mom? Is it still on? Mohammad, I think you are the host, right? Yeah. Wait, I need to.